A warm welcome. Can you hear me? Probably not. I don't know what I have to do. A warm welcome to everybody. Welcome to the premises of Slovenia Academy of Science and Arts. I'm very grateful that the president, Professor Stich, academician, allowed us to use this premise. As you see, it's a very special room, and I hope we'll have a fantastic gathering. I had this idea of giants and forerunners for some time, and then unfortunately pandemia played with me. So a few months ago, in fact around a year, 4 of us got together, or got in touch in fact. Professor Zheng Shi from Nansai University, Professor Pradip Kumar from IIT Bombay, I don't see him, but you're hiding there, from Mumbai, India, and Professor Shanzhen Zhu from Nankai, Tianjin, China. The 4 of us, Scientific Council, unite as very special thing. You would know Shanzhen, I usually call my younger brother, and when people see us, they are confused. But the person that unites us is our dear supervisor that shaped us, that helped us become who we are, Professor Jyoti Chattopadhyaya. He turned a special celebrative number earlier this year, so I thought it would be proper to honor all his contributions or his stimuli, what we usually get excited about, results of your own, results of your student, progress of your students, becoming independent, challenge findings, get together like we are today, and what is most important these days, contribute to friendship around the world. So a warm welcome. I think we'll have a fantastic day. I don't want to take any time. We are here to help you, to assist you with any desire or wish you can have within reasonable limits and our capability. A few technical remarks are in order. Just last minute cancellation. Sandipta Aharia couldn't come. She has a shorter talk. You probably saw in the program, former students have just 15 minutes addresses because otherwise it would be impossible to squeeze in one day. And Marcus, a substitute of Professor Thomas Carell, got cold and he emailed me yesterday morning. So I think that makes it easy in the program because he's the first, he was planned to be, and it's in the program, we couldn't do anything. So we'll just make our lunch break longer. So there will be 2-hour lunch break. I hope you're okay with that, nothing we can do. Those of you that will stay at ANA will meet Professor Carell in Porto Roche later this week. So another technical remark, if you need password, there's this Dvorana, which means hall, Sazu Dvorana, if you need, and this is the password. You can guess what's the year. This academy celebrated 85 years of establishment as this name Sazu last year. But in fact, it started as Academia Operosorum in 1693. So tradition of, nurturing and practicing science and arts and all these things contributing to national identity at the time has been around for many centuries. So coffee break, another important thing of these gatherings will be downstairs. We'll exit the building and first door on the right. The place is called LP. Isn't Professor Stanovnik didn't know, and I think he's frequent in this house. The name is really truly funny. So the only challenge will be to get all of you back. But I got a long whip, so I'll try to. Chairs will have a challenge to bring us back. That's where also lunch will be served. So with this, warm welcome again. Thank you for coming. Some of you came from very far, and we are really honored that you took this effort in these days where flights have been canceled with no reason sometimes. And I wish all of you nice interactions, exciting science, and meeting, as our Asian friends would say, meeting old and make new friends. Thank you very much, and I give the floor to Professor Zhu.
So good morning, everyone. So I'm Chuanzheng Zhou from Nankai University. So I have my PhD with duality, actually from 2004 to 2010. So today we get together to celebrate the duality 75 birthday. So I'm very happy to see every one of you. So today the speakers are most of them are duality's old friends and former students. So I would like to take my time to introduce each one, just very briefly, okay? So the first speaker of this section is Professor Robert Kapteyn. So Professor Kapteyn is an outstanding professor from Utrecht University, and he has high reputation and influence in the field of study the structure and function of biological molecular macromolecules based on MR, right? So today his topic, yeah, so please, yeah.
Good to go. Yeah. Okay. So this is for the next slide. Yeah. Forwards, backwards. And this is the red. Yeah. Yeah. Well, thank you for your nice words for introduction. And well, I'm not used to think myself as a giant, more as a David that can possibly win of the giant, huh? But okay. But nevertheless, let me do my lecture. We are here in Ljubljana. Yeah, okay, no, that's great. That's okay now. Okay, so I will talk about CIDNP, chemically induced dynamic nuclear polarization. And yeah, it is a misnomer actually, because when the phenomenon was invented or discovered, they thought it is a dynamic nuclear polarization effect, but it was not that. That is something else. And it was later found, and I was also working on that, so we found that it is more a radical pair theory and not dynamic nuclear polarization. So anyway, but the name is still the same. Okay, so a little bit of history of CIDNP. Discovery. So in 67, two labs accidentally and independently discovered this effect. This is just an experimental. For instance, Joachim Bargon, he found, and well, you see, the 67 was the publication time, and he found it already 3 years earlier. But he was a student, and his supervisor didn't believe it was a real effect. I mean, and he was not allowed to publish. Of course, in Germany, especially, you as a student, you cannot publish independent of your master. So that was an interesting story, but it turned out to be a real effect. And he found another scientist, Fischer, Hans Fischer. Oh. That's not right, yeah. Oh, that's fast, yeah. That went fast, no. Okay, now, yeah, here, Hans Fischer, and they turned out, he was actually in Zurich, and together they worked out and published this effect. So the effect really is, as you see here, a negative reaction. If you use benzoyl peroxide, then this is benzene, but it was negative. And that was a big discovery at the time. And in the end, of course, this is a thermal reaction, and if the reaction is up, if the benzoyl peroxide is done, then you end up just with the normal line as it stands up. okay? And yeah, so he and Fisher, they worked this out. The second discovery at the same time was a butyl lithium reaction with butyl bromide by Ward and Lawler. And here you see also, here you see this is the normal spectrum and the mass spectrum, and here you see when you put them together, and then this reaction is going on, and here you see some enhanced lines, but also a multiplet effect. A, B are the same proton, okay, because of hyperfine coupling, it is spread out, but it is both emission and absorption in the same proton. So that was also an interesting thought. So characteristics in the first 2 years, Gerhard Kloss found that photochemical reactions in triplet state were different from the singlet state, is opposite. There's many opposite effects, sign changes. And we found that radical recombination reactions were opposite to impolarization compared to the escape reactions, the scavenging, the people. So from the that escaped from the radical pair, and these observations could not be explained by DNP theory that was thought before. And the solution is then the radical pairs. You use the radical pairs, and that was a new thing that people had not considered before. Okay, so opposite in different products. You see here is the here is the radical pair that you get after the decomposition of acetyl peroxide, and you have a recombination product, and then part of this, these two methyl groups recombine, and the others diffuse away, escape, and that is done. These are opposite. So that is the first sign reversal. So here they call recombination, and here enhanced absorption, the escape product. So multiplet effect is I will not talk a lot about that, but in fact you have a multiplet effect. So there's one type of proton can be positive and negative if it is split up by J coupling. So that is called the multiplet effect. And positive is one proton here, one type of proton, the CH2 group, or CH3 in this case, and it goes, now this is CH3, this is CH2, and the same proton can be positive and negative. Okay, so what's the mechanism of it? Radical pair mechanism. That was found at the time I was a PhD student, and I thought this is much more interesting than the subject that my supervisor gave me, and he was okay that I started to work on this. And by doing a lot of experiments, you could first of all see that it is some effect that is not happening in one radical. That was thought, relaxation explanation, but it needed a pair of radicals. That was an important start, and otherwise it had to do with the singlet triplet mixing that is induced by the nuclear spins, and it can be the case that it is faster for beta nuclear spins than alpha nuclear spins, and that will then give the effect. Let's see. We have this again. This is high field radical pair mechanism, and it is a nuclear spin sorting, if you want. Assume that it starts from the triplet state here, by photochemical reactions, for instance. Then the radical pair due to the nuclear spins can go on to a singlet state, where from the singlet state you need for a recombination. A triplet pair cannot recombine. And but to go to the singlet state can be faster for a beta spin than an alpha spin. And that creates, of course, the recombination and the excess spins, so the negative effect, emission. And here, for the escape then, what's left over, the signal must be positive. Okay, so that is in short what happens with CRDNP. There are lots of sign reversals, as I mentioned already. And so here we have singlet and triplet precursors. So that gives a sign reversal here. It starts plus minus, and here minus plus here in the case of the triplet, for instance. And recombination and escape products, as I mentioned, are already in opposite signs. So here the recombination would be negative, and the escape product positive. These are enhancements for acetyl peroxides. Okay, so this is useful because we had a good theory for it, but my students found this very difficult, and for that I devised these simple rules. In fact, that is very helpful. If you see, for instance, for the net effect, you have four parameters for signs, and if you multiply them, then it is either plus, that is absorption, or a minus comes out, and then it's emission. So you fill in just signs, plus, minus, and so on. So here for triplet state is plus, here minus, for a type of reaction product, plus and minus, and here, some in the same radical or in different radicals of the pair. And so if you plug that in, then you get a sign, and you can predict what the outcome is, whether it is enhanced absorption or an emission effect. So that was useful for simple attribution of the spectra. Okay, well, here you see that happening here. Here is the acetyl peroxide again, and you get an emission effect here. That is by these signs. If you multiply all these, there's a minus coming out, and then this is negative. And for the escape product, well, this is for a multiplet effect, and you have an absorption emission, like here it starts with absorption, then emission, and that can be all derived by these signs. Okay. For proteins, well, let's see, first of all, for an amino acid, this is tyrosine, you can see that you have a strong negative effect if you do photo reaction. So you have a dye, and you irradiate the dye, and that picks up a proton from the phenolic group here. Then it is a radical, but if it returns the hydrogen atom, then it's a reversible reaction, but still it is for some time part of a radical pair, and it can give very large negative line. Huh? So, okay, so here you see this for all the amino acids, or that can be published, can be dealt with it. That is, there are only three that will do this: histidine, tryptophan, and tyrosine. And also here you see the corresponding lines that you can respect. So here is a sign reversal that is just due to the different G factor in the case of the tyrosine. So that can change the sign again. Okay, so reversible reaction, photoreaction of flavin with tyrosine. This is indeed this reversible reaction. You excite it by light here, by some dye, And the dye here is usually flavin as we used it. That's a useful dye to excite it. It picks up the hydrogen from the phenolic group here. You have the radical pair now here of the dye and here of the from the subject. And then it is reversible, gives it back the proton, and you see this polarizations. Okay. And of course, you can apply this for proteins, and that can be quite useful if you, for instance, have proteins with that have a site where another molecule will bind. You can see whether it's occupied or not. Would be one application. Here, for instance, you have you have a binding site. Oh, yeah. Here you have a binding site within the hydroxyl group and a phenolic group, and but if there is another molecule sitting here, then it is blocked. So that you can see then by observing the polarization or not. Then this can be this site can be blocked. That would be one application here, and that is shown here. So we have a DNA binding molecule, and here we have when it is absent, you have 2 or 3, in fact, 3 tyrosines. You see these 3 lines are all negative, but if you have DNA binding, then you see only 1. So the other groups are blocked by the DNA as a ligand or as that binds to the protein. Okay. Yeah, and that's an example of that. You have, for instance, the Lac headpiece operator complex. So the operator is the DNA, and so this is the operator, and the Lac repressor headpiece is this are these things, and that binds the operator binds. So this headpiece binds to a very special site at the DNA and controls the expression of the Lac genes or not, or block them. So that's the role in this case, and that was one of the examples that we did. Okay, and well, here's another example of photo-CIDMP of ribonuclease, and well, there's lots of things you can see. Well, I will not discuss all these things, but it's a useful device for studying also proteins and their binding sites to small molecules, to regular sites, for instance. Okay, well, here would be the structure of ribonuclease. It's a bit complex, but you see some of it's now tyrosines that we speak about, and that occurs at several. Oh, what happens? Yeah, okay. And you see that there are several tyrosines here, histidine. These are the groups that can be polarized, but if you don't have block these sites, then it's not possible anymore. So, okay, so what does the radical pair mechanism, and where does it play a role? Of course, we discussed CIDMP, but also CIDEP, so the electron polarization. There you can have an effect of the radical pair mechanism. Magnetic isotopes effects that are studied by these Russian people. Magnetic field effects, delayed fluorescence by Weller. It's a big work in Weller, some 20 years ago or so, 30. Reaction yield, well, this is a Ritmar, yeah, that's a bit exotic. The navigation of birds, that's an interesting one. there are proteins in the brain of the bird that do this also. By light, it can be, they dissociate in a radical pair, and the orientation can be influence the back reaction. And that's how the birds navigate. And that was a very interesting application of this. Huh? Usually we have interesting effects but no applications. But this is in the nature what happens there. And and then also solid state CIDMP and so on. Okay, so that's the end, and I'm happy to answer questions. Thank you.
Let us revisit your medical chemistry and biophysical manifestation of that. So my exact question is, if these radicals are a pair, what is the spin state of these radicals? Are they, in quantum mechanical terms, would you say they are entangled, unentangled?
Sorry?
Entangled?
Entangled?
In quantum mechanical terms, when you separate two spins, remember, because of the overlaps, remember who belongs to whom. Now, in your radical pair mechanism, this entanglement phenomenon that has been found out recently, what is your comment on that? I know you haven't fully done that, but what's your comment on that, about the spin states of these two radicals?
Yeah, we have never discussed this word of entanglement. It is just if you have two radicals and they come together, then they can form a pair. Yeah? Okay, and then you can say they have this possibility of either it's this or this, of course. And but we tend to discuss this in these terms and not use entanglement.
Thank you. Fantastic overview and a special honor that you made it with Jan. And you spelled it properly, which I admire and knowledge. So I was wondering, you showed us some 2D, 1D spectra, and it seems this effect is long-lived. Could we nowadays do fast 2D spectra on this? Could we do 2D spectra, like so fast HSPC and so on? Because you said 10, 12 minutes there. Yeah. So I wonder if it could be exploited in protein.
We tried to do it in 2D also, but you see that if you have a reaction going on, then then it's problematic. If you have not a stable situation, it's usually the case to do 2D modeling. So that is a bit, that is not very useful. It's a bit contradictory. You have a reaction going on, and then 2D should be used for a stable situation.
You might not like this question, but sensitivity-wise, how would you compare it to DNP? Because your sensitivity analysis seems really high.
Yeah,
is it in that ballpark? The same?
Hundreds or so.
Wow, okay.
Yeah, sure. Yeah, of course. When we started a long time ago, it was more important than now, this sensitivity, because now the magnets are fantastic. 1.2 gigahertz and so on, enormous sensitivity. But at that time, that was an extra bonus that you had, that you have a very good, quite strong enhancement of these lines.
I see about 1 minute 30 seconds left, so we better occupy that time. Yes, that's the question, is the time. Now, if you say that you have done that, this radical repolarization, beautiful evidence you presented, but now you suppose thorium to deuterium,
The story was?
if you exchange the proton
Yeah.
to deuterium, the isotope,
Oh, yeah.
and you make a competition now, proton deuterium competition, another given lifetime for realization. You have done anything regarding that line? You get that question?
That's your question, no.
The
Go to
deuterated methyl group,
That's it.
would it become longer lived? CD3 instead of
Yeah,
CD3.
CD3, yeah.
Sorry.
Oh, that's the question, yeah. The three protons, well, of course, they all have the same, they're equivalent. Huh? So it is just a factor 3 stronger, but that is the only effect that you have on a metal group, because the rotation is so fast that it acts as one set of one
Even
set
in the
of
time
nuclei.
scale that we're talking about there?
That's also for the metal. We had a few metal groups that we have.
I think it's still like 5 minutes, right?
Well, let's just wait till we have a little bit of time.
Okay, so please join me.
Okay. Okay, so, okay. Oh, that, yeah. Yeah, okay. Okay, I take this.
I have. Okay. So clearly, I cannot see. Here? Okay. Okay. Yep. So thank you, Senjan Sensei. Thank you, everybody, especially Yanis, invited me to talk about this kind of very honor symposium. I'm very happy to do that. So I usually talk about 2B or not 2B in nucleic acid chemistry. I will talk later, okay, in detail. Oh, my name is Naoki Sugimoto. A lot of people already knows, probably. This is my group. At first, I would like to acknowledge my group member. So very international, came from not only Japan, but also the China, India, and Toronto, and so on. Especially at this work, as Hisae and Shuntaro, I hope in the audience, and Gosh Sensei, and Dipa Sensei also contribute to very nice work. Thanks so much. At first, Yanis said, this giant meeting is honoring 75 years of excellence. 75 years, he already mentioned about Jyoti Chattopadhyay's birth years. So he looks this one. Close to 10 years ago, I attended Professor Stek's 75 years birthday party in Łódź in Poland. So he looks very happy, and his wife, and Jyoti, of course, attend, and Peter Hedin, Mav Carozas, and Janusz Provek, and Richard Adamiak, and me attend. My favorite guy also appeared here. He did this kind of things. It's very funny. He is very good guys. And also my favorite papers, one paper published in the JAX long time ago. So from Chattopadhyay group. First author is very famous now, person is Janusz Provek. This is pretty interesting. So they discussed not only structure, but also the thermodynamics. It said, they discussed delta H values. So one case is they talk about 3.1 kilojoule per mole. The other case, 2.2 kilojoule per mole. They discuss these kind of small difference. Don't confuse them. dimension is kilojoule per mole. We are very familiar, kilocalorie per mole. This difference only 0.2 kilocalorie per mole. It meaning without experimental error. Just kidding, okay? This is very nice papers. And also I found chemical review paper. My chairperson in Shenzhen is first author. It's great. Very nice reviews. So he looks pretty. Shenzhen looks pretty, okay? And profile said, big boss, Jyoti Chattopadhyay, he has supervised 30 PhD students. I think this is wrong word. One word, very important word is missing. He has supervised 30 outstanding PhD students, I think. I'm a very kind person. Okay. My most favorite paper is appeared in Biochemistry 2005 from Chattopadhyay group, because he cited our publications. I love that. So my group doing the canonical structure, duplex, RNA, RNA, DNA, DNA, RNA, DNA hybrid, not only the stem region, but also the doubling and so on. We are doing until these kind of years, okay? After that, my group, I determined, I moved to the subject. So, to the title, to be or not to be in nucleic acid chemistry. I talk about this story first time in 2017 publicly, this title, in Cambridge Symposium. So a lot of people ask, oh, Naoki, you are Japanese, you misspelling. Oh, yeah. I said, yeah. Means every people already knows, in England especially, to be or not to be means from William Shakespeare. Hamlet said, to be or not to be. B-E-B. I'm not William Shakespeare. I'm Naoki Sugimoto. Okay, so this is wrong words. I would like to say to be or not to be. It is not necessary. This audience already know B means. V form, DNA. So Watson Crick published 1953 from the Cambridge Cavendish Institute. Just one page appeared to the April 25th volume in Nature. Just one page. So they show the B form, this one, and A form, this is for RNA-RNA duplex. Of course, this is common sense now. Two important interactions. One is hydrogen bond. The other is stacking interaction. We are physical chemists. I would like to say van der Waals interactions. These two interaction is most important two interactions. This is common sense. All textbooks shows. However, please consider again, this kind of hydrogen bonding and the stacking interaction, and also conformational enthalpy came from the bulk interactions of DNA structure and RNA structures. However, please consider, this is not in vacuum. This one in solution. It means molecular environment interaction also important. For example, counter-ion concentration and hydration, and finally we found molecular crowding effect is most important factors. So I already said my group moved to the non-canonical structure DNAs. For example, this is duplex melting curves. So when you increase the PEG 200 as molecular crowding reagent, 0% to 40%. So increasing this amount, Tm going down. It's meaning we call canonical structure DNA under the molecular crowding condition, it meaning cell mimic condition, destabilized. On the other hand, typical non-canonical structure quadruplex, Tm is increased. It's we call non-canonical structure. But under the cell mimic condition, this kind non-canonical structure was stabilized. This is pretty interesting. For example, in really inside cell, Watson-Crick double helix still canonical structure or not? This is my favorite subject. So at first, we are physical chemists. We have to deviate the equation. What interaction is most important under molecular crowding condition? We published next year, 2004, in JAX. Finally, we found PEG 200, small, not so big one, small crowding agent effect is mainly water activities. This is pretty interesting. So based on this theory, we started do experiment under molecular crowding conditions. For example, duplex I already mentioned, triplex, tetraplex, junction, and so on. All results shows same directions. For example, Hughes-Tin base pair was stabilized. On the other hand, Watson-Crick base pairing is destabilized under molecular crowding conditions. If we are interested, please look at these kind of publications. For example, this one we published 2012 in JAX. This is a long telomere sequence. So terminal telomeres, just one single strand can make this kind of G quadruplex. So title is based on the string structure of long telomere DNA under molecular crowding conditions. So we are lucky. JAX choose our story as cover story. This is chromatin, terminal long telomere sequence, and each one is based on string structure of G quadruplexes. We are very lucky. Next year, Shankar's group published in next year published his title as Quantitative Visualization of DNA G quadruplex Structure in not model system, in really human cell. This is very good. So they found chromatin terminal, this kind of G quadruplex structure. So our result shows under molecular crowding condition, Shankar shows the real living cell, exactly same result, supported same result. This kind of non-canonical structure stably exists in these kind of conditions. So if we are interested in next year, 2014, we published in the Chemical Review and about the effect of molecular crowding effect. So next, big question. What kind of roles a nucleic acid with non-canonical structure playing in gene expression not only exist, but also what kind of role, function? For example, this is transcription case. This is usually, every textbook shows DNA double hex, RNA polymerase going through can make full-length RNA product. Finally, after the translation, we can get the protein structures sequence. So only way, if we have this kind of non-canonical structure, polymerase cannot go through, just pausing and pausing and pausing. So it meaning even we get the same full-length RNA product, due to the exactly time course, this sample amount is much larger than this amount. So this kind of structure controls amounts of productive RNA and finally protein amount. If we get a very extreme case, very stable this kind of structure, this polymerase cannot go through, just arrested. So only we can get arrested short RNA product. It's meaning totally change to the protein sequence and amount and structure. So it's pretty interesting about this kind of play an important role of gene regulation, gene expression regulations. For example, we published in the 2018 in JAX. So he started doing very well. Title is Destabilization DNA G curves by Chemical Environment Change. Not only crowding, but also some other effect is very important during tumor progression, facilitate transcriptions. So we are lucky as a cover story. It says about the cover. So important was is this. The G quadruplex formation in DNA differ during tumor progression due to chemical environment change. This is not only crowding, but also especially potassium concentration change. It meaning exactly potassium concentration in living cell do the play an important role of G coordination stability, and not only stability but also functions. So this shows. And ion channels, it's related, potassium ion channels. This is pretty interesting. Exactly same year, we published also JAX. Shuntaro doing a very nice work, collaborate to big guy, Jan Sprabeck, and Byung-Hyun Kim in Korea's. So recovery of formation function of oxidized G duplex by finite modified guanine tracks. That's a pretty good way. As an abstract, we call this strategy generally enable recovery of the function of any oxidized G4 and therefore has potential for cancer therapies. It's pretty interesting. And also, same year, two cover stories. We are very lucky. Very complicated mechanism, but I like this kind of thing. Looks like Vincent van Gogh's paint. Oh, great, great, thanks so much. So he's also a big guy in London, Professor Stephen in the audience. So I met a few months ago, I think, probably, took a photo. He found a lot of different topology structure of G duplex. So we can try to target this kind of topology, especially this kind of ligand or not. So question, can we regulate the stability and gene expression of G4 having the specific topologies? So we will try. Takenaka sensei in the audience already found, published the chemicals. They, based on this naphthalene diamide, so he made circular one, the other circular one. So he tried to, this kind of effect bind to G4 to stabilization and also start the effect of gene expression. So we collaborate. So it's a pretty complicated story by physical chemistry. So I would like to skip. But please keep remember important one. We call this method is a quantitative study of topology-dependent replication. We call QSTR method. So this one is we compare to relation, stability delta G value, and kinetics, starting effect, delta G double dagger effect. So finally, this one is stability effect, and this one is starter effect, promotion and duplications. So Takenaka sensei found the NDA. We would like to get stability going up, so depression is going up. This is theory. However, his case, NDI, DM, and make the circular NDI2, duplication up. However, stability no change almost. This is even worse. Replication started up, stability going down, so no relations, correlations. So based on our physical chemistry theory, we propose new model system, this one, Pyland one, this one. So please look at carefully. This one is increased. Also this one increased by our theories. We succeeded. Very good stability, very good replication. Collaboration is great. So we published this kind of result. And finally, every time including Yanis group support. So thanks so much. So we published the JAX a few years ago. So this one is topology dependent ligand bind. We can now design any kind of ligand to bind to the G coordinates very reasonably. So I don't want to not only focus the organic compound. I don't care about any compound is okay. So we would apply this QSTR method. Oh, I have to say, Shuntaro, great work. So cover story is this one. It's great. So we are very proud. our research would facilitate the design of new drugs capable of controlling the topology-dependent regulation of gene expression. So now, our QSTR method applied to metal complex, metal ligand. We collaborate with Chris Curtin group in University of Reading, UK. So they found the X-ray crystal very beautiful structure like this. So our developed ligand stabilized antiparallel specifically G4, which was solved by X-ray crystal graft. So next year we publish also JAX. This one's pretty good, very nice. And again, I would like to say, oh, wait a minute. So this one, the duplex, we are interested in today, due to time limitation, I talk about GCA duplex. Also, I motif is very important. So this kind of formation of GCA duplex I motif, before this kind of formation, canonical DNA duplex have to unfold. So very important things. Can we predict the stability of nucleic acid duplex under the molecular cloud or not? So this is very challenging. I'm very excited. So I would like to talk about this prediction method. So a lot of people already know this kind of prediction is we call nearest neighbor model for predicting duplex stability. So Nacho Tinoco, my boss, I'm very sorry he already passed away. UC Berkeley proposed just one page and 3 lines or something like that, published in the Nature's, proposed. So this one is RNA case, CA, GUE, and the complementary sequence. At first, we separate nearest neighbor base set, CGAU, next, AUGC, and the N. And this kind of nearest neighbor delta G stabilization. And this one, additional factor is without nearest neighbor, just first initiation to base pairing. So he proposed delta G total stabilization energy come from the summation of this kind plus delta G initiation value. So stability of nucleic acid duplex can be predicted by nearest neighbor model from the sequence information. So I will talk about a little bit history about this. This is a long time ago, Nacho proposed. But after that, it takes a long time to get really parameter, even high salt concentrations. So Ken Bresler, Rutgers University, published PNS 1986, long time later, and Doug Turner, RNA duplex, University of Rochester, he was my boss. That time I'm a postdoc, one of the co-authors, PNS, exactly same years. After that, our group published not only these things, but also RNA DNA hybrid parameters. So long time later, physiological salt conditions, John Santarcia published in PNS. John Santarcia belonged to the Wayne State University, Detroit, United States, and our group published this kind of low salt conditions. However, physiologically salt condition and molecular crowding effect, our group published NAR and PNS. NAR just one factor, PNS is total factors we published. However, no parameters for RNA duplex and RNA DNA hybrid available with physiological crowding conditions. We already published several years ago how to detect this kind of inside cells, inside organelles, for example, cytosol, nucleus, and the nucleus conditions. So we published analytical chemistry several years ago. So based on this kind of technology, 2 questions appears. Can we utilize NN model, nearest neighbor model, to predict RNA, for example, RNA duplex stability in different physiological crowding conditions? Second one, is it possible to apply NN parameters for predicting in-cell RNA stability? This is pretty interesting. So I will show our result. This one sequence is different. However, if you separated nearest neighbor set, this set, exactly same. So this is what happened. Biologists consider, oh, sequence different, stability totally different. This is wrong. Based on our nearest neighbor model, even the sequence is different. However, nearest neighbor set is same. This mating behavior is very similar. Finally, we get some kind of parameter is very similar. I will show. Please look at carefully. Mating curve. Really, very same. And log CT plot is very close. So this kind of different sequence shows Tm value is very close. And delta G value is minus 8.7 kilocalorie per mole and minus 8.4 kilocalorie per mole. Only 0.3 kilocalorie per mole. Like Yannis' first authored paper discussed about the 0.2 kilocalorie per mole. So this is very nice thing. So oligonucleotide with identical nearest neighbor base pairs show similar thermodynamic parameter in physiological crowding conditions. It means cell mimic function. Not only this sequence, we tried a lot of base pair in the identical nearest neighbor set. All results show nearest neighbor model is valid even in the physiological crowding conditions. So we get finally these kind of parameters for predict RNA stability. You can say this one predicted value, stability, this is measured value. You can see very good relation, linear relation. Especially slope is close to 1. Intercept close to 0. It means we can exactly predict to the measured value. Pretty good parameters. So this one prediction error parameters. So we can compare to other groups diluted and other not physiological sort conditions, this one. So all parameters very comparable about parameters. So we can use our parameters. So for example, we can use not only PEG200, HGUM, EG, HGUM glycol, K is 28%. We can predict based on this theory, minus this sequence, minus 13.1 kilocalorie per mole. Experimental value minus 0.7 kilocalorie. It's very close. Sorry, I will quick. So we published this one, nucleic research last year. So also very nice cover story. So please compare to few years ago, we published DNA. That time, we have only one thermodynamic graph, can see the inside cell. You can see manually. This is theory, delta G equations. And now we have three different, at least three variants, can see the cytosol and nucleolus and nucleus. So it says, our paper, we published something like that. We are very honored. This novel technique may become a global standard for understanding and design specific RNA function in various compartments of different organisms. And also, we are very lucky, we published RNA-DNA hybrid parameter in end of last year, JAX. So now, only our group, has all three parameters can predict to this kind of thing. So coming from tomorrow, Anna, Yannis here's the Anna. So from two doctors from my group talk about now we started to AI work. So title is, first speaker is Hisai, nearest neighbor parameters with AI beyond the experiment, predicting high order structure of RNA with mismatches. And the second speaker is Shuntaro, will talk nearest neighbor parameters mid AI functional prediction of DNA. So please, looking forward to this kind of presentations. So finally, I would like to skip this one. Last year, we published the Spring Nature book. I'm an editor-in-chief. This is not so very important if you are. So finally, this is very important. Instead of Hamlet written by William Shakespeare, please answer the question, to be or not to be. That is a question in the research field of nucleic acid. This is the section. And we are doing the nucleic acid chemistry under the molecular crowding world. So far, my answer is the Watson-Crick world is not enough. If they know this kind of thing, should be surprised. So finally, I acknowledge Janis Private as this is Brett Rake. So thanks so much, Janis. This collaboration is to be continued. Thanks so much.
Now, I can thank you for a lively presentation.
Thank you.
Now, the last slide, and your first slide, same slide. What's the thing? Base pairing. Then on your third slide, you profoundly say about hydrogen bonding and the base stacking, which you did on the duplex, the other stay effect. Beautiful. Question to you. Maybe not a question, I'm begging for a comment. So you have two competing forces. If you just, for a moment, ignore the medium effect. The hydrogen bonding and the stacking. What's stronger? For the self-association of the DNA. Because that questions Watson-Crick. Their deep analysis of the fibers showed is the hydrogen bonding that is the force. Stacking, ignoring that 637 words paper in Nature. Now, your comment.
We already published in JAX long time ago. It's the personal relationship, hydrogen bond and stacking. This is complementary effect.
Which is stronger?
No, it's complementary. For example, help each other. If weak hydrogen bonding case, so stacking help the contributions. Complementary effect. So this is pretty good. Also, I showed not only hydrogen bond and stacking interaction, conformational entry. A lot of people neglect this one. Conformational entry, very different from RNA defect, DNA defect, and DNA hybrid. This is also play an important role in function for DNA and RNA. So we are getting good results. We will soon, I hope, publish.
Okay, so if you have one more question, we can discuss it further.
Thank you.
Next speaker is Dr. Yoji Sangri. So Dr. Yoji is expert in the design, development, and manufacture of therapeutics. So actually he worked in ASIS, right? For
Yes.
maybe more than 10 years, right? And
15, almost.
yeah. And then found the vaccine incorporation, right? So today he talks about the the development of the kilogram scale manufacturing rules for the synthesis of radical RNA and DNA bispecific repeaters. Yeah, please.
Well, very good morning to all of you. I'm literally delighted and so pleased that Yannick and his committee decided to invite me here to be at this amazing venue and share some of our work. So before I take a deeper dive into what we have done in supporting the fundamental of nucleic acid chemistry, it's again a great privilege and honor for me to mention that Jyoti and I have literally a lot of connections Just to, some of the people may not know that Jyoti and I got our degree, PhD, at an institute in India called National Chemical Laboratory. So he was 5 years senior than I was in the same institution. So we had wonderful foundation there. Following that, Jyoti went to do his postdoc with Colin Rees. That was very inspiring for me to see some of his publication and Colin's work. So I wrote to Colin, and he was very kind to accept me as his postdoc. So again, I followed his footsteps back in London at King's. And I was there at 3 years. And of course, all of his work, which Colin and Jyoti has published, we followed on that. And it was a wonderful experience for me to be following his footsteps. And I hope that what I'm sharing today will reflect a little bit of that thought in what I have learned over the years. So what I feel here is that Jyoti is connected to me in more than one way. So I would say that he's a legend in the field, and of course my big brother. We come from the same country, we have the same roots, we have the same way of thinking about science, philosophy, life, and family. So again, I take great honor in being here, and I'll be here until the very end. So please catch me anytime. If there's any questions, comments, I'll be thrilled to, again, talk to all of you. So I don't want to take too much of time in acknowledging what he has done, but as you can see, he has been a wonderful mentor. You heard from Naoki-san that he has mentored 30 PhD students, over 500 publications. I'm not aware of that many people who have really done as remarkable as Jyoti has done. So he's definitely a legend for me in the field, and we, again, are delighted to extend his work in what you will hear next. So what I feel here is that all of us are nucleic acid chemists, and after COVID-19 pandemic, we have all learned a little bit more that nucleic acids can do wonders, save lives of people in many ways. So it's a really fundamental molecule and the chemistry, which we can tackle in so many ways. And where I work is at the very foundation of it, that how we synthesize and assemble these drugs for treating patients. And when you have to treat patients, when you have millions of patients, how do you make the drug in the quantity which you need, in the quality you need, and most importantly, the price point where you need to manufacture these drugs. So again, that's my email address. So if you have any questions, feel free to drop me a line. So today's topic goes back about 10 years in time. And so what we were assigned to do is to manufacture a drug molecule which is called gudadisabine. So it's a decitabine dimeric analog, which is a prodrug of a known drug, which is right on the top there, as you can see. It's a nucleoside analog. It could be a ribo, which is azacitidine, or the deoxy version, which is decitabine. So what people at Aztec Pharmaceuticals in California did is that they designed this particular molecule to enhance the stability and the efficacy of decitabine, which was degrading very rapidly in vivo. And of course, the drug was then given at a very high dosage. So obviously, we were interested in designing something, and that's exactly what they did, is that they made a prodrug of it, where on the 3' end, they attached the natural phosphate connected to a deoxyguanosine. And this drug reached almost to phase 3 clinical trials today, and it's again used for treatment of, as you can see, AML and MDS. So these are, again, drugs which have very nice potency. And as you can see from the mechanistic point of view, you have decitabine going through a triphosphate formation, which is the DCTP there. and gets incorporated into DNA, and then it inhibits the binding of DNM to the DNA. So as a result of that, it works very effectively as a drug which inhibits the methylation, which is not required, which is again not a desired thing to happen. So going into the chemistry, as you can see, the molecule is shown on the left there, which is what we have to synthesize in multi-kilo quantities. It's called SGI-110, and it requires two basic fragments. So one is a decitabine as a phosphoramidite, and the second molecule is the bis-tac DG, which is on the 3' and on N2 is protected with t-butyl phenoxyacetyl protecting group, which is TAC, and that comes from deoxyguanosine, and this comes from decitabine. So as I already mentioned, it has improved cellular uptake. It has enhanced pharmacokinetics, very long in vivo stability compared to decitabine. And as a result of that, it is again crucial for us to make the drug which is of high quality. And this is actually the first presentation for me to be summarizing this work in public audience. And both of these papers just came out a few months ago in OPRD. So again, I would welcome to read these papers. So if you're interested in how we design and synthesize these two molecules, or these two building blocks, as you can see, and assembled gludacetabine or SGI-110 very effectively. So why we want to do this? Again, going back to the fundamental chemistry, decitabine was synthesized back in 1960s. And the reason we wanted to, again, make a prodrug of this is that it is hydrolytically, particularly in presence of water, again, both under aqueous acidic or basic media, it ring opens the triazine ring, as you can see. And it ends up in this formyl derivative. It releases, again, the formyl group there, and it ring opens, and it again anomerizes, as well as it changes into the six-membered ring. And as you can see, you have multiple products which are generated in vivo. So as a result of that, of course, decitabine does work, but it requires high dosing. So the goal here is to avoid all of this happening in real life. And the same thing applies also to the synthesis, that when we are doing the synthesis of the gludacetabine or SGI-110, we have to remember that if this is happening in vivo, it will happen in the reaction vessel when we are making this molecule. So the one message which I want to share with you here is that the moment you expose your decitabine with water, it starts to do these byproduct formation. And as a result of that, you will have an impure drug and less active. So our goal in synthesis was to avoid all of the aqueous reactions. And that's exactly what we have accomplished. So the first task was that we wanted to synthesize decitabine first. There is a US patent which was describing the synthesis starting with the base, which is the triazine. You just do HMDS. You take the deoxyribose, you make the sugar, which is O-methyl. You protect your 3,5 position with parabenzoyl, parachlorobenzoyl derivative, and then you put a leaving group on the C1 position. You do the glycosylation, and you get about 45% yield of your beta ionomer, and then you deblock the protecting group, and you get your product. But as you can see, the yields are pathetic there. It's about 15%. So again, it's a challenge to make these drugs on large scale, as I told you, because it's not stable in water. So our key concern here was that we wanted to improve the yield of these molecules, which are important for us to scale up, and at the same time avoid the use of water. So what we did here, and this is unpublished work, we started with deoxyribose, isolated that, and then, converted into the methoxy derivative. We isolated it here on the 3 and 5 position. The quantitative yield at both steps, we don't isolate the intermediate. We take it straight into the glycosylation, about 70% yield of alpha beta ionomer. We deblock it in a single step. Again, no water, as you can see, all the way after the glycosylation. And we isolate about 22% yield of the pure crystalline compound, which is over 99%. So again, I wanted to add an NMR just to honor Jyoti and Yannick, that we do look at the NMR and it's an important tool. And that's the HPLC of the compound. It's almost 99% pure. So we have the starting material, which is extremely pure. It's a short synthesis, very efficient and low cost. Here then, the next task for us was that can we make the BizStack DG? So we had a research route on our mind, which we thought was a green protocol. I'm sure some of you are familiar, but if not, we'll talk a little bit more about it. That we wanted to do chemistry which is environmentally friendly, because we are doing things in hundreds of kilos of quantities. And we want to do chemistry the right way, where the molecules are made in a manner where we are not utilizing a lot of organic solvents, and we are not creating, again, reagents or using the reagents that are, again, toxic in nature. So we wanted to adopt environmentally green procedures, and of course, enzymatic protocol appears to be the right choice. We published a paper back in 2015 where we were able to demonstrate that you can take deoxyguanosine, exact same compound with N2-TAC-DG, and then if you use the Novozyme 435 Cal-B in THF in about 18 hours, you regioselectively isolate the 5' position with the lovinyl group on the DG there. And once that's done, you then introduce your TAC group on the 3' position, and then you deblock your DMT. So here, as you can see, we did the TAC protection with acid, the t-butyl-phenoxyacetyl acid, BOP triethylamine, again in 16 hours room temperature. Here also means the deprotection of the lovinyl group happens in under mild conditions, in hydrazine pyridine acetic acid in 1 hour at room temperature. So as you can see, all the reactions are done at room temperature. And again, a lot of times means I think people don't realize that in industry means if you're heating or cooling the reaction, you're consuming energy. So think about it this way, means everything has an environmental impact. So here we are able to demonstrate that we can do reactions at room temperature. That again has an added advantage to what we do. So the reason we weren't able to scale this up is that we were using very large volume of THF to dissolve deoxyguanosine. So again, deoxyguanosine is not very soluble in organic solvents, but we were able to do the reaction. But we're using 40 volumes of THF. So again, environmentally, THF at that volume is not desirable when we want to scale up the reactions. So we came up with another procedure where we had the DMT protected isobutyl DG, which is a commercial material. We use it for, again, synthesizing DNA, oligonucleotide. We can deblock the isobutyl group in very nice yield in a single step with aqueous ammonia in autoclave. And after that, you do now protection, both simultaneously your amino and hydroxy group, and almost 90% yield. The same reaction conditions in presence of BOP and the acid were able to drive that reaction. And then you take your DMT off this time under a neutral condition with sodium periodate in 70% aqueous acetone. This work was published by a friend of mine, Ivan Rosenberg, who is in Czech Republic, in Prague. And again, this was the first time we were able to demonstrate that it can be done in multi-kilo scale. So again, we're really pleased that all of these reactions were working at room temperature. But the problem, again, we ran into is that to do double protection with the TAC acid, we're using large excess of the reagent. And that wasn't really ideal for scale up. So we had to, again, modify the synthesis and come up with a plan 3 here to execute these things on multi-kilo scale. We started this time with deoxyguanosine, because deoxyguanosine is easily accessible, it's commercial. We can get these in metric ton quantities. We did, again, N2 protection in almost 99% yield using, as you can see, TAC chloride this time, and we used the Jones protocol. So again, I don't know how many of you have actually run the Jones protocol. Roger Jones, he's still around. He's 80-some years old, but it works beautifully. And we were the first one to demonstrate that, again, you can introduce TAC in tens of kilos of quantity of material. So Jones protocol, when he published it, it was only done in gram quantities. But we are doing this now today in hundreds of kilos of quantity. So again, some of the old work works beautifully, but the one thing which we learned here is that you have to really be careful about the water content. So as long as everything is absolutely dry, you can drive this N2 protection very nicely. And then the following that, what we did is that we installed the DMT on this molecule. And once the DMT was installed, what we did is that we, again, put the tag group on this, on the 3', and then remove the DMT. But what's missing here, perhaps you can't see it on the slide, but I will encourage you to read the original paper in OPRD, is that there are 2 steps which we had to do. The first step was DMT protection, and the second step was the 3' tag protection. So what we decided is to save time, energy, and money, is to do the reaction in one pot. So this is our one pot protocol, which we published again, where you install the DMT in presence of pyridine here, a little bit of dichloromethane, DMT chloride added in 4 portions at 0 degrees, about 1.5 hours, your DMT installation is done. In the same solution, you come back this time, you quench your excess of DMT chloride with a little bit of triethylamine, and then you add, again, your tag chloride and follow the reaction. In less than 1 hour, you're complete with your tag protection. So in one pot, you're doing 2 separate reactions. Just imagine the power of these 2 reactions to be scaled up. So we run this on hundreds of kilo scale today. So again, it demonstrates that if you modify the conditions correctly, you can selectively protect the 5' with the DMT and the 3' with the tag. And once that was done, we again came back to Ivan's protocol, sodium periodate and aqueous acetone under neutral condition. It deprotects selectively your DMT group, and you get your BISTAC DG. We start with about 10 kilos, as you can see, and it ends up in about 6.5 kilos of 99.4% pure compound, crystalline. So that's the type of chemistry we want to do. No chromatography. Remember, everybody does chromatography. In industry, we do not do chromatography because chromatography costs time, money, solvent, and of course, your media or silica gel. So first reported procedure, as I said, we were able to scale up. A one pot, 2-step protocol worked beautifully. We minimized the depurination. So I don't know how many of you have actually done the chemistry, but depurination of DG is a problem. And the moment it sees any acid, it depurinates, cleaves the glycosidic bond, but we're able to minimize that because everything, as you can see, is done at room temperature. It's under neutral condition, and we're able to do these things, again, in a way where we can apply these things to solution phase chemistry, which I'll come in the end. So here is our next building block which we needed. We had decitabine in hand, which we took. I won't go through all of the process development we did. It was almost 5 years worth of work. I'm condensing it in less than 30 minutes or 25 minutes here. But the original work which we did was published again in OPRD. As you can see, this time what we had to do is that protect the amino group with the DMF. It goes in quantitative yield. And once it's done, we come back with the Novozyme using vinyl acetate. And this time, the Novozyme 486 works very nicely in dioxane room temperature. In about 4 hours, your reaction is complete, where you have the 5' selective monoisolation using enzymatic protocol. We don't isolate the product. We do the phosphorylation in the same pot, and then you end up in getting your phosphoramidite, which again, we don't isolate. And we do the reaction monitoring by NMR, of course, P31 NMR, and we follow it by HPLC. So these 3-step protocol, we are doing this on multi-kilo scale, as you can see, and it works very nicely. It gives you the P3 compound. So I don't know how many of you have actually made the oligonucleotide, but P3 chemistry is so amazing. You might hear a little bit from Rakesh Vedu talking about this, is that when you're doing the P3 chemistry, if your compound is only P3, it's the only compound that's going to react because you're doing the phosphoramidite chemistry. The rest is just going to stay there and not react at all. So the beauty here is that if you can make this compound cleanly in high yield, it will react, but all of the other impurities will just stay and stare at you. It will not react, and then you can clean up later on, and that's exactly what we have done. So here is just a snapshot of what we were doing. We screened different enzymes, and that's what we traditionally do. So we took every commercial enzymes, we ran multiple batches, as you can see. It's some of the enzymes we did about 7 to 8 batches to make sure that everything is consistent. From batch to batch, we can make the compounds with the same quality as well as the purity which we need. And as you can see from the graph here, I don't know if it's very clear or not from the back in the room, but as you can see, the acylation goes very rapidly in the orange line there, and the blue line is the starting material, it drops. So we are following the reaction by HPLC to ensure that the reaction is complete, and once it's complete, we quench it and then go to the next step. So we have done these things again with 4 enzymes. The Novozyme 486 was the best one. As you can see, pushing the yield in almost 90%, as well as the isolated purity is almost 100%. So just imagine you can do acylation enzymatically, monoacylation on large scale, and we're doing this on about 10 kilo scale. Next, what we did is that we took our phosphorylated material here, we coupled it with the TAC DG, which I already showed you. We made it again on multi-kilo scale. We're making, again, on an average, about 60 kilo of the product at any time. So it was, again, a key starting material, 99% pure. This material, again, was high purity. They couple in solution, and this time you get only P3 compound, which is the dimer here. We don't isolate this, as you can see. And then we oxidize this. Again, the oxidation is done under non-aqueous condition. Remember, I told you, means the moment you hit water with your triazine ring, the decitabine start to ring open. So we had to be very careful in ensuring that we are not using the water in the downstream reactions also. So both of these reactions are done in the same pot. We do making the P3 compound, doing the oxidation with t-butyl hydroperoxide in DCM at room temperature. Within an hour or two, the reaction is complete. We are following it by, again, NMR, as you can see, and we are using the t-butyl hydroxide for oxidation to minimize the degradation of the decitabine if there was any water. So conventional on DNA synthesis, people use iodine, water, pyridine for the oxidation, which we try to avoid it here. So here, again, the next step was very important because now we have a fully protected molecule. Look at the molecule. You've got DMF, you've got the acetyl, you've got the cyanoethyl, and you've got the TAC. So you've got 4 different protecting groups. And we wanted to knock it all off under non-aqueous condition and ensure that we're getting the high purity material. And we were able to demonstrate that by doing a selective, deacylation or deprotection. We screened all of the bases, and the one which came out on the top is the t-butylamine and acetonitrile, about 10 equivalent. In 24 hours, we were able to show that it's 100% conversion. So we can knock off the protecting group with a decent purity of 80%. I won't spend too much time on this. My time is running out, so I'll go a little faster. It's almost the last slide here. So we have this fully protected material, the dimer. We hit it with t-butylamine and acetonitrile in 24 hours. What happens is that by using the t-butylamine, we're able to get the deprotection of the DMF as well as the cyanoethyl. And the t-butylamine actually makes a salt with the phosphate. And the moment it makes the salt, it starts to precipitate out of the solution. So all you have to do is filter it off. You remove all of your impurities, and all you have is your product as the solid material. And once you have that, you come back and you hit it with sodium methoxide and methanol, with sodium acetate in there, trace amount of water. We had to get it in for the solubility purpose, very short reaction time. And then now what you're doing is that you're deprotecting your TAC groups as well as acetyl. And in the end, you have your godacitabine or SGI 110, highly pure, almost 99% purity. We make on single batch about 6 kilo under GMP. So GMP is good manufacturing practices, again. So for making a drug, you have to do everything under GMP. And this is a toxic material. So we had to, again, have a potency lab where everything is environmentally controlled. So all of these things are done without human contact. It's done, again, under a very stringent condition. We're able to push the purity to the desired amount, which we needed. And again, I would encourage you to read some of the original work which was published for this. So in the end, what we have done, our take-home message for you is that we have environmentally friendly processes, which is the green chemistry. It has significantly reduced the cost of the drug, which is important. And we can now push this to almost a mole scale on solid phase also, which I don't have time to talk about today, but I would encourage you to read this particular book, which is coming out, or it's already out actually a week ago. It's the RS3 publication, Sustainability in Tides. So we wrote a chapter in this particular book about oligonucleotide synthesis. So again, we were able to remove all the objectionable process reagents. It's atom efficient. We are not wasting too much of reagents. So we think that we can, again, have drug to treat AML and MDS, both which are, again, diseases which are important to treat the large number of patient populations. And this work would not be possible if all of our colleagues didn't help. So Sapala Organics is a company which I founded with Reddy over there about 15 years ago. So the team did most of the R&D work. InnovaSynth did a lot of scale up of the BizStack DG. NCK in Denmark did most of the GMP production. And their team, Anestec Pharmaceutical, of course, was the driver in asking us to do the large-scale production of decitabine or SGI 110. And again, all of the key people names are there. And again, I want to thank you all for coming together and listening to the story I had to share with you. So again, incredible amount of work to demonstrate that as a chemist, you can not only make the drug, but you can make it in a manner which is high purity because you're using it for treating patients. So quality is important, and of course the cost. So we're able to achieve all of those objectives. So again, I'm happy. I'm here to answer any questions, and thank you all for your attention. Yeah, we still have 2 minutes.
See how you brought things in the test tube to multi-kilograms per synthesis. It's not easy. I'm a synthetic hand-on chemist. I understand the challenges. For example, these Jones oscillations, which I have used myself with my 2 hands.
Right.
I tell you, brother, it's a full challenge. We have to keep the water out by putting oxygen and nitrogen syringe inside the flask and so on and so forth. And you have done that in multi-kilogram scale. So that's up to you.
Thank you.
And thank you for your kind words.
My pleasure. We learned a lot from you, so thanks to you as well. Thank you. Yes, please.
Go. Okay.
Yes.
Well said. You know me, huh?
I'm trying to remember. Oh, Jose.
Yeah.
He came to San Diego. Right. Of course.
You come back. I can ask you so you can explain why I didn't work.
Sorry, which?
You need dioxide protection of one.
Right.
So you wrote me once.
Right.
So why didn't work? Is this case?
It's because we wanted to scale up. So everything had to be done on very large scale.
Yes.
So it was important that we do things which are scalable. So we have also time factor, which I didn't discuss, that the patients are waiting for the drug. They can't wait for a long time. So we need to do everything at a fast speed. So we take the knowledge which is already there and then apply it. So we'll come back to some of the discussions we had before, but not for this project, for another project. Yes.
So I must leave. But you can discuss it together because this master degree was for the next job.
Okay, all right. Okay. Thank you very much. Good seeing you again. Yeah. Okay, so because I'm impatient, I have to close this section now. Okay. So please go and accept the bonus meeting. Time for the food break. Yeah, so
Please exit follow Anna Maria.
yeah, so please
So if
come back.
somebody would like to use the room for computer something, we have a room here. To be safe.
Not at the moment, thanks. No, I'm good. Thank you.
Well, thank you very much. Appreciate it. So, I want to hear about your G-complex. Your molecule looks promising. It's in phase 1 right now, right? So, if you need large quantity, you can make it. Well, yes, but we can do better. That's the way I feel. I would welcome looking at the once you see the facility, it's not the money. See, what I feel is that what I feel is that you're doing the right plots behind the project. What I feel is that China is not as so from that point of view, it's be watchful about how we dispose of materials when it's made. So in China, pollution has been a serious challenge in the industry. Whereas coming out of the facility, it just looks like a Western lab. By the way, I think China and Malta are working together. See both of them tonight and hopefully
Yeah, welcome back. So we are going to the second scientific session of this meeting, and we have three excellent speakers lined up for this session. And the first speaker is a really giant in the field. He has made an immense contribution in the nucleic acid structure, and I have read many of his papers. Especially I learned quadruplex by reading his reviews and papers actually. Professor Stephen Needle.
Thank you very much for those very kind but quite unnecessary words. That helps, thank you. Can I first of all thank the organisers for inviting me to this great meeting and your lovely city. It's been a real revelation and the weather has helped. Anyway, I'm going to be talking about a journey from chemistry, basic structural concepts right through to where we are now in clinical trial for the agent that we've devised and developed. But before that, let me just say a couple of words about our associations with Jyoti, which go back a very long way to the times when both of us were at King's College, Jyoti in the Department of Chemistry with Colin Rees, and I was in the Department of Biophysics learning about nucleic acids. So at the time we did some structural work together, my group contributing crystallography, he, Jyoti, NMR, and insights into conformation. And when Jyoti left King's, that collaboration continued at least for a while, and I've highlighted one paper which I think is perhaps the most significant of that little group. And at that point, I think we went overtly the nucleic acid way, whereas Jyoti continued to focus on understanding conformation at the nucleotide level to great acclaim, I think. Anyway, what we've done is to start thinking about, and this is not novel, of course, how do we direct targeting to targets that we know may be significant in cancer therapy. Most of modern targeted therapy is, of course, targeted toward proteins, be they kinases or immunoproteins on cell surfaces. Our background in nucleic acids led us to the alternative approach of directly targeting cancer genes at the transcriptional level. Now, of course, there are other ways of doing this, but I'm going to focus today on transcriptional targeting. We're, of course, pretty familiar with duplex DNA. We've seen some examples here already today. And we know that the simple bDNA helix is wound up in progressive layers until we get to chromosomes and to DNA in cells. But of course, DNA and RNA can be much more than merely double helical, as we've already heard. And I'm going to be talking about one form of higher order DNA this morning. And that form can be characterized in most instances by, first of all, primary sequence, by the fact that it's formed by tracts, short tracts of guanines interspersed with more general sequence. And I've got two examples here. First of all, in human telomeres, which may be several thousand nucleotides long, but at the extreme ends are single-stranded. And you can see telomeres are comprised of simple repetitive hexanucleotide sequences, TTA, GGG. In genes, it was, I think, recognized, first of all, in the MYC gene, that similar sorts of sequences can be found. But of course, it was not till we knew the sequence of the human genome and subsequently many more genomes that the totality of this picture of the occurrence of these sequences has really been understood. Well, what do these sequences do? First of all, they can fold up in a way that I'm going to show you in more detail in a second. They can fold up not into two-stranded, but essentially structures that appear to be four-stranded. And this is one schematic type here. The red indicates backbone, and you can see essentially that there are four backbones in that. Holding together, each rhomboid is actually a guanine. And again, we'll see that in more detail in a minute. These structures, we can crystallize them, we can analyze them, we can do NMR on them. Do they actually exist in nature? It was mentioned previously that we can visualize these in fixed cells and now actually in live cells. In fixed cells using an antibody type approach, and this is from the work of Shankar Balasubramanian's laboratory, showing that this reagent, BG4, which has a fluorescent component and is specific for quadruplexes, G4s, lights up when a quadruplex or a bunch of quadruplexes is sensed, because these cell pictures don't necessarily show single quadruplexes. So let's take one such sequence, which is a sequence within the gene of a kinase, the kinase called c-KIT. And this 3D structure was determined initially by X-ray crystallography. Now what I want to show you is how this structure in detail is built up. Each of these first 3 G tracts essentially donates a guanine, and you can see there's also a red indicated guanine from a sequence in between G tracts that donates. Then there's a second G quartet formed this time by guanines from all 4 G tracts, and finally a third. Now, just as base pairs tend to want to stack on top of each other, these G quartets have a propensity to do just the same. And so we get a typical type of quadruplex arrangement, and if you look at them, we'll see more in a minute, one sees always a core of several, between 2 and 5 typically, G quartets stacked one on top of each other. Each quartet is held together very firmly by an array of Hooke's-Steen hydrogen bonds. And outside, holding that arrangement together, is an arrangement of those external sequences in between the quartets, forming loops and other types of structures. Now, this is one sequence. There are many, many other quadruplex sequences implying correctly that there are other ways of forming quadruplexes. There are other topologies, there are other arrangements, some of which look at first sight quite remote from the arrangements you can see here. But they all have in common this core of stacked G quartets held together by external nucleoside phosphate linkages. And here are a number from crystal structures. Bottom right and bottom left are a little different from the massive quadruplexes. Almost all quadruplexes are right-handed, following BDNA, if you like. Antoine Fan's laboratory several years ago showed that a particular type of sequence could actually, under certain circumstances, form a left-handed quadruplex, and that crystal structure is shown bottom left. More recently, Lilia Yatsunik's laboratory has determined the crystal structure of a hybrid left-handed, right-handed quadruplex with a ligand stacked on the end. Again, though, we still see that pattern of stacked G quartets held together by backbones. And in that more complex one, top middle from the KRAS promoter sequence, we can still, if we look a little more carefully, see the same sort of arrangement. Now, what about the occurrence of these, first of all, sequences and structures in cells? Because we must differentiate between primary sequence and tertiary structure. We can write down any sequence that we can imagine that looks like a quadruplex sequence, but it doesn't necessarily form a stable quadruplex. And various groups have evolved ways, as we've heard a little today already, of determining the relative stability and propensity to form stable structures of these sequences. The first thing to say is that these sequences are widely prevalent in the human genome, and the first informatics estimates from my laboratory and from Shanker's were around 350,000 occurrences within the genome. Very large number. It turns out that that number does not represent the total number that are actually actively stable within a genome associated with active chromatin. And moreover, there's a difference between those in a cancer cell and those in a normal cell. And you can see the figures here. They've come down to much more, but still very large numbers. Around 12,000 G4 structures may be actively formed in a typical cancer cell at one stage or other of its life progression, and approximately 8 to 10-fold less in a normal cell. But there's more to it than that. It turns out that the distribution of these sequences is non-random. Instead, we get an overrepresentation in promoter sequences of those genes primarily involved in proliferation. In other words, cancer genes. And we also see an overemphasis in the message, the 5' untranslated regions of those genes, again, cancer-related genes. So let's start thinking about how we might exploit that knowledge of where quadruplexes are within the genome. We've taken the quite recent low-resolution cryo-EM structure from Brad Chair's laboratory of a quadruplex embedded in a longer duplex sequence. So what we see here is a quadruplex in the middle, and we've actually added in yellow a little small molecule. Why we'll see in a second. So we've managed to dock that small molecule into our G4 site, and the G4 site is more or less, as I've described, isolated G4s, stacked quartets with strands surrounding the quartets, holding them together. Now let's envisage a promoter coming along the duplex as one stage in transcription. What we can, I think, easily envisage, and was experimentally found some 20-odd years ago by Hurley's laboratory, is that that structure, that arrangement, is essentially a halt to further transcription. As you might imagine, the duplex is no longer linear, it's kinked. And because of the small molecule, that kink prevails. So this suggested to us and many others a therapeutic strategy to downregulate the transcription of those genes enriched in G4s via the formation of stable G4s with the help of a specific G4 small molecule ligand. So this really just shows the progression of what we've been doing since 1997, when we first described with Lawrence Hurley's lab a G4 ligand having a biological effect targeting a G4, right through to 2023 and 2024. However, once we started thinking about actually developing that strategy, we realized that it was not straightforward. Although the literature is full of instances where labs are targeting, say, the MYC gene with a well-described quadruplex, we felt that human cancers complex human cancers would not be susceptible to that argument because so many genes are involved in the progression, development, and promulgation of complex cancers. And I've highlighted pancreatic cancer as one of those very complex, genetically complex cancers, where if one's targeting G4s, one has to think rather carefully as to what one is targeting. Whereas if we look at some rather rarer cancers, simpler cancers that are driven by a single genetic change, for example, in liposarcomas, and I think in the ANA meeting we'll hear more of that from Sarah Richter, there's a single dominant gene, MDM2, we can perhaps target that if it has a G4, which it actually does. So what we've done is to develop some high affinity ligands for G4s that have essentially no affinity for duplex DNA that can both target multiple G4 genes, because we think we have to be doing that. That's an inescapable consequence of the overall generic similarity of many G4s. But we can also perhaps, in certain instances, target a critical G4 in those cancers that have just those characteristics. So does G4 binding relate to cellular potency? This is cell growth inhibition data for a series of 8 compounds, and we see that those compounds essentially fall into 2 classes. I've estimated DNA binding by melting temperatures, and we can see on the right-hand side of the plot there's a bunching together of compounds with very high binding, high G4 stabilization, and essentially low nanomolar cell growth inhibition, whereas those molecules, related molecules that have almost no effect on G4 stability have a much higher biological response in terms of cell growth inhibition. And this pattern has been seen by many investigators. So we say G4s can differ in primary sequence. They can differ in tertiary fold in terms of topology, in terms of the arrangement of sequence surrounding that core, but they have generic features. And here we've used molecular modeling on a G4 duplex hybrid to visualize how one of our molecules might be binding. Now, because of these generic features, we don't feel that we can fine-tune our designed small molecule to fit exactly the targets that we might have in our complex cancer, where we might have 10, 20, 30 major genes that are dysregulated. So we've used molecular modeling instead to just give us a broad idea of what the best molecules might be. And we've then used cell growth inhibition assays, phenotypic assays, to get us to a point of optimization of those molecules. And we've chosen as our cancer to work on pancreatic cancer. Pancreatic cancer, as most of you probably know, is an exceptionally hard cancer to treat, probably the hardest. It's not susceptible to current immunotherapies. It's invariably fatal within a short time of diagnosis. So it's a serious challenge. And also we know that if we can have a relatively small effect on patient survival, then we would have done something useful. So we started off with the molecule that you can see here, a tri-substituted naphthalene diamide, and by a series of basically classic med-chem, pharmacology, molecular modeling, and crystallographic studies, we arrived at a final compound. I'll show you the structure in a minute, QN302. As with any drug discovery program, you're never quite sure when to stop. Can we actually do better than the one that we've got in our hands? Well, we tried to answer that by right at the outset posing the question, can we actually improve on CMO3 by an order of magnitude? And fortunately, we were very lucky that we were able to do that. So again, you see CMO3 with this rather beautiful structure from tri-UM, and we've docked our compound into there, and you can see in more detail, it fits in quite nicely. This G4 is derived from MIC, but it has been altered. So you can think of this target site as a truly generic G4 site. And this is the structure of the molecule, molecular weight 800. It's the sort of molecule that a classic medicinal chemist would throw their hands up in horror and say, this doesn't look right, this is not going to do anything. Well, it does. It gets into cells very quickly, transported actively, and is active against tumors. Now, this is an in vivo xenograph experiment, and just to focus on 2 points of the plot, the top curve is a control curve, tumors that are growing without any small molecule ligand. The bottom line there is our drug molecule, and what you can see is essentially following the horizontal for 53 days. Dosing was stopped at 28 days, so the effect of essentially stopping tumor cell growth continues well after that 28-day period. Xenografts, though, are hardly human. They're very artificial systems in which a tumor is grown on the flank of a laboratory animal. So we then went to a much more demanding type of system in which pancreatic cancer is produced in situ within the pancreas of an animal, a mouse. And in this case, we can see we're looking not so much for changes in tumor volume, but in sheer survivability. We can see the dark blue line is representing those animals without ligand, the purple line, those with. And you can see that there is a population which survives over twice the extent of the untreated. That's statistically significant and telling us that we do have a molecule of some promise. Now I'm going to skip this just to very quickly tell you that we've used whole genome sequencing to tell us which genes are actually affected, which genes are downregulated. And this is the first set of 12 genes that are the most downregulated. FC represents the degree of downregulation. The first gene, 9-fold downregulated relative to control. So 12 genes there. It turns out all of them have G4s in their promoter region. Now I've just highlighted some of those G4s here. We've started to systematically go through each one, each gene, each G4, one by one to understand its characteristics. And you can see the bottom one is a very, very pronounced G4 molecule, almost entirely Gs. What I think surprised us, gratified us, was looking at the literature of these genes in terms of their prevalence, in terms of their behavior in human tumors. And this data is taken from the Protein Atlas, which is an atlas of prevalence in human samples, typically 150 patients at a time. And what we can see for those two genes that I've highlighted, the genes in pancreatic cancer patients are overexpressed and relate to decreased survival. In other words, to our minds, these are good targets. So we were very pleased to be able to correlate our underexpressed genes with drug, with targeting. So let me, in the final couple of minutes, just tell you where we are now. The compound received approval as an orphan drug in the United States in January 2023, and then went into formulation scale-up and toxicological studies, and was submitted in the end of June 2023 for approval for clinical trials. It was approved 29 days later, and then went into phase 1 clinical trials in November in sites in the United States. Well, those trials are underway, but what I can tell you, and those trials on patients, majority of whom have had late-stage pancreatic cancer, they've failed all current therapies. And what we're seeing is, first of all, at the low doses that we start to use in a typical clinical trial, the drug is well tolerated. And we're not seeing any serious adverse effects to date. We're also seeing that the patients have a good quality of life and that they're able to resume their normal life pre-disease. Encouragingly, we've seen some early indications of stable disease for up to 4 months in pancreatic cancer patients. And if I tell you that gemcitabine is a drug that gives weeks of extra life typically, this is really doing quite well. So it just remains for me to apologize for running over time, and also to thank all those people who've really done the hard work at UCL and a number of other places. And thank you for your patience. Thank you very much.
Stephen, very nice work. I wonder if we can take the lead from Balasubramanian's work, where he uses a molecule which has fluorescence to detect intracellular binding with the quadruplex. Your molecule should have some fluorescence, looking at the polyaromatic character. Yeah. So have you used that as a tool to determine that how many sites your molecule is binding in that target site? Can you quantitate it?
We can. We haven't done that yet successfully. What we have done is to use his antibody to see the effects in cells. And it's interesting. We first of all see an increase in PG4 antibodies, then a decrease, because this molecule binds so avidly to G4s that it competes off the PG4 antibodies.
I see.
But it's an entirely predictable, quantitatively understandable story. But yeah, there are a number of other things we're doing. And I should have added that the whole genome transcriptional approach was developed with Chambers Lab.
Thank you. So the last question.
Fantastic. You're very exciting, and you're a big encouragement for all of us. I wonder if you can comment on morpholino. Why is it always this planar surface and then it's morpholino at the side? Have you seen specific interactions on morpholino along these linker arms?
Well, yeah. We've got crystal structure data that shows us that waters are
exciting.
Intimately involved. And there's some, not only structured waters, but there's some invariant waters which seem to be in the binding site. I think one can't generalize that because that's just in one G4, but water's for sure water. So you guys need to see the water.
Yes, sure. Thank you. Thank you, Professor Migi. So our next speaker is Professor Leif Kurzboom from Uppsala University. So I knew Leif from my PhD days. I used to go to his lab to do experiment, and one thing I can tell you that he is a hands-on scientist. He used to do experiment himself many times, and also he has done a lot of work on RNase-P ribosome. So he is going to talk about RNase-P work. Thank you.
Thank you. If we can get this working. Oops. You don't see it, right? Okay, thank you. Right. Okay, so thank you for the invitation, and I really enjoyed being here, and this is my second time in this lovely city. And just to tell you, I mean, I've known Yotti since 1978, 1979, when I was a PhD student at the Department of Molecular Biology. But not only that, I knew Yotti from his research that when he came to Sweden at the Department of Microbiology at the time. I also know him from evenings, since I worked as a bouncer. And I didn't throw him out, I let him in to the student nations. And that, I think, was, and we did some talk and when I was standing in the door. But that was really nice. But I think that is, we have traveled a long way since then. And in order to travel, in order to communicate, you need a pair of shoes, right? Communication, you need two. Okay? You cannot just do with one. But the pair of shoes can also represent spread of disease. Okay? It can represent communication between people and coordination between events. Not only that, I think it also can represent, one of my favorites is magnesium. In order to have catalysis in the enzyme that I will, or the ribozyme I should say, I will talk about is RNase-P RNA. You need two metal ions that work together in order to have cleavage of a substrate. So I think that shoes are very important. And a picture or image tells you more than 1,000 words. So I'm very much fond of images and art. And actually I was the chairman of a Department of Art History, although I'm a molecular biologist. Okay? Now let's move on a little bit. Having said that, my research career has been focused on tRNA and in the model organism. I'm a bacteriologist. Molecular biology is working with bacteria, recently mycobacteria. But E. coli has been a model system, and it has taught us a lot. E. coli has 87 tRNA genes, and as you know, these needs to be processed because they are expressed and transcribed as precursors. And these needs to be processed in order to generate mature tRNAs, functional tRNAs. And the enzyme that was actually shown to do this job is RNase-P. And RNase-P was first identified in Cambridge, England, back in the 1970s when Sid Altman was a postdoc there. And it was published in JBC 1972, and then later on it was discovered that it has one protein component and one RNA component. And the question here that relates to this, which was fundamental and profound discovery, that it's the RNA that is the catalyst. You don't need the protein, but you need metal ions, okay? Now, then of course you can sequence and you can do predictions of secondary structures, and here you see the secondary structure of E. coli RNase-P, which was at the time referred to as M1 RNA. And you have a 3D structure, a crystal structure that was published 2010. And here you can see the protein component. And here the RNA component, and the blue one is the tRNA in this case. So this is the post-cleavage state, because it's the tRNA that is bound to the RNase P. And this was done by Mondragon and published 2010. So what you do see here is that the 90% of the volume is RNA and 10% is protein. And you can take away the protein. Now, if you then go into the sort of what are the different functions, because the RNase P is built up of different subunits or different domains, so to speak. Now you have what we refer to as the specificity domain, you have the catalytic domain, and then you have the tRNA, and then you have the protein. So if you start here, this is the naked RNA, no protein. And then you go there, so you gain by adding the protein about 30-fold, more than 30-fold in catalytic efficiency. Now then you can go the other way and take away different domains. So if you take away the specificity domain that is important for the interaction between the characteristic T-loop of the tRNA, elbow, then you lose about 500-fold in catalytic efficiency. Then you can go down and actually take away this one and just have a short sequence, and that is still catalytic, but you lose a lot of catalytic efficiency, about 400,000-fold. And this, we sort of narrow it down to 31 nucleotides. And Yotti, you remember 31-mer, right? And the NMR window concept, published 1996. That was Yotti's first collaboration with me on this, that after discussions. And that was published here. So this small RNA, this 31-mer nucleotide long RNA, can actually perform catalysis. But you need magnesium. Now, if you do even further, so you can actually sort of reduce the size of the substrate, you can go down to this size of the substrate. So you still have catalysis. I'll show you some data on this. Now, what about the substrates? They have a pre-tRNA, you can have model substrates, which many people have done, and the one that we have been using is this one, and I show you another one. And then they come from the tRNA, of course, and then you have the acceptor stem stacked on the T stem, and then you have the T loop. And then pseudonode substrates are also substrates for RNase P. Now, what about interaction with the enzyme or the RNase pRNA? Stacking plays a very important role. Now, it anchors the substrate onto the RNA via a interaction with the T-loop as well as this CCA end, but notice that not all tRNA genes encode the CCA. In E. coli, that's the case. In eukaryotic system, it's not the case. And in some bacteria as well. And then you have this A48, which is a conserved residue in RNase pRNA in the bacterial world. But stacking plays an important role. I will come back to that. Now, if you look at the interaction between the T-loop and the RNase pRNA, you see here you have a base stacking platform motifs formed by two intertwined T-loops here. And if you have that without substrate and with substrate, you can see the stacking here continues and here as well. So that is a very important aspect of an interaction between the RNase pRNA and the substrate. And we discovered in the beginning of the 90s that what you have is the CCA end of the tRNA precursor, if it's present, actually base pairs with a sequence in the RNase pRNA, and that is the 31-mer. So these residues here pair with the CCA, and this is the discriminator base. And we actually said that the RNase RNA interaction anchors the substrate, exposes the cleavage site, results in recoordination of the magnesium ions in order to accomplish cleavage. As you can see from the crystal structure, here you have the base pairing between the RCC and the RNase pRNA, and then you have stacking. Okay? Here. So you have stacking on top of this. And if you go to the interaction with near the catalytic center, that is to say where the action takes place, you have this A48. That stacks on top of the first base pair, G+1 C72 in tRNAs, okay? So, and here you have the metal ions, and presumably they are important for catalysis in this case, but it was not shown in that time, 2010. So, what you have here is this stacks on top of that base pair. So, what you do see here is the question, and this I think Yotti directed me to this paper, and it was shown before here. And it's that dangling ends are ordered, correct. And favorable stacking, dangling nucleus to base and neighboring base pair, okay? So that hydrophobic cap, so you have a hydrophobic cap there. What's the function of that? Restricts bulk water access to terminal base pairs, but also inside the helix. And what is the significance of that in terms of cleavage, catalysis? Water acts as a nucleophile, right, if it's activated, or the 2' hydroxyl in RNA. So in order to prevent incorrect cleavage, you cap, so you don't get in. So that is something that I'll show on the next slide then. So what you have in the tRNA structure, you have the discriminator base, which is most often a purine, that stacks on top of the G+1 C72 and make a cap. Now, if you have RNase pRNA, an interaction with the tRNA, the discriminator base is engaged in pairing with the residue in RNase pRNA. And what happens is that the A248 flips in and stacks on top of the G+1 C72. And my idea about that is that it prevents access of water to the interior hydrophobic interior of the acceptor stem, preventing unspecific hydrolysis. So that, I think, is an important aspect of the stacking at where you have the action taking place, that is to say catalysis. Because you need to have correct cleavage in order to generate mature tRNA. So it's not just the kinetics, it's also error. If you make an error, we need errors, right? Otherwise we wouldn't have been sitting here in DNA replication. We need errors. Otherwise we wouldn't have any evolution. Correct? Now, so what you have here is that this is the stacking. This with the stacking interaction plays a very important role for interaction with the elbow of the tRNA. And here you have the RCC RNase pRNA interaction. Stacking also plays a role here by sort of what I see it as protecting the base pairing between the RNase pRNA and the substrate. And you have the stacking and the A248. So if you add on, and this is the recent data from these people, this is Mike Harris' lab, and then you have a leader, because this is, as I said, this is a post-cleavage state. And if you have a leader, that's the before cleavage takes place. So then you have, in this case, a U-1s, A-2s, so cleavage takes place at this position, but you also have stacking here. So this is a very good structure based on cryo-EM. And then you have another one here. So that's another pair because they changed the residues -2 and -1. Now, why is A248 conserved in bacteria, stacking, right? But what we can do here is to determine the activation energy by determine the kinetics on the different temperature, at different temperatures. And then what we discovered was that the A, if you have A at this position, 248, that gives the best or lowest activation energy. And if you replace it with G, U, or C, then the activation energy becomes, in particular with respect to the pyrimidines, then you get increased activation energy. So what you have stackering, anchor the substrate, prevents access of water to the, and thereby unspecific cleavage is avoided. And then you have the activation energy, A248 is the lowest, and stacking A is a better stacker than G and the other ones, right? Now, so this rationalizes why A248 is conserved among bacterial RNAs, pRNA. Now, if you then turn into the mechanism of cleavage of metal ions, when we have now seen to it that we have interaction with the substrate. So this is based on many different labs' works. So you have two metal ions, and one metal ion activates the water that coming from underneath, generating a 5' phosphate and a 3' hydroxyl and at the ends of the cleavage product. Now you can change the magnesium to some of these metal ions, and it works under different conditions. And there is also evidence that there is a metal ion associated with the 2' hydroxyl, but you do not want that one to be activated, act as a nucleophile, because then you get the wrong cleavage products, 2', 3' cyclic phosphate, and you don't want that. So you have to prevent that, and how that is prevented, we don't know at this point. But I think that is something that is of interest here. But what we did use in my world, a little bit of chemical modification of the 2' hydroxyl to change this to 2' NH2 group here, and then we did some pH, different pH titration, and we can see that the site of cleavage shifted from the correct site to the incorrect site, or from the incorrect site to the correct site, dependent on pH. And that is shown here. So, and also it's replaced by different nucleotides at this position. And we actually saw that in our experiment that we came up to the conclusion that the G functions as the guiding nucleotide for RNAsP, and it's the exocyclic amine on G that is important. So that was a short summary of a long story in that sense. But we also know that I mentioned that we have interaction with the T-loop and this part in the specificity domain. And what happens here? We also have data indicating that there is an induced fit. So when you have a correct interaction between the RNAsP RNA and its substrate, something happens at the active site. That is to say, position the metal ions such that you can have cleavage at the correct site. And the interesting aspect of this is that the interaction here affects the conformation here, which we also can see that more distant domains or interactions here, structures here affect what is going on here. But I will not go into that. But just to tell you that there is an intricate network of signaling in this molecule. Now, pseudonode substrates. Nix et al. Showed that this pseudonode is a RNA aptamer. It was in vitro selected for binding biotin. Okay? The resolution is 1.3 angstrom. So it's a very good structure, crystal structure. So what we did was take this generated this pseudonaut. We added a trailer, that is to say this one, so it can bind to RNase P, and it works as a substrate. And the idea here was to see whether the area around or the structure around the cleavage site was affected by, or how that was affected when we changed this residue here. So we did do some experiment, quite many experiments and so on. I will not go into that, but it acts as a good substrate for RNase P. It's not as good as a regular tRNA precursor. Now, what happens if you take this substrate, this structure, and superimpose it on the tRNA in the structure, cryo-EM structure of RNase P in complex with the pre-tRNA? What you see here is the arrow. That's the scissor phosphate that is attacked in both cases. Now, this is the leader that is cut off in the pre-tRNA, but this one is cut off in the pseudonaut. So the pseudonaut substrate binds better to the RNase pRNA, but the transition state, we argue that it's higher, more energy is required to reach the transition state compared to when you have a regular substrate with a regular leader, because that is less organized, but it's organized by RNase P. But this is very organized from the beginning. And you can superimpose it either to the pre-tRNA when you have a pre-tRNA, or you can superimpose it with the structure when you adjust the tRNA. And they are fairly similar. Now, what you can do also is to do some simulations by having an A, U, C, or G. Notably, when you have a C at this position, it cuts at 2 positions. Question is why? Can we do some work there? But what you see here, it's a little bit different. So the distance between the metal ion that induces the nucleophile is roughly the same in these cases, but the configuration around this is different, dependent on the identity of this one. Now, so if you look at the C, it cuts at 2 positions. Either this phosphate is attacked, or this one. We refer to this as M-1, and this as C0. That's the canonical cleavage site. Now, we see this alternative, and it's less prominent, it's lower frequency of that in terms of for the other ones. But we do see a prominent increase in this case where you have C at this position. But when we change pairing in here, this one here, and the idea was that we wanted to change the charge distribution around and near the cleavage site in order to affect the positioning of the metal ion. And what we do see that the simulations goes into this one. Also, the experimental part goes into that situation. So we get less miscleavage or cleavage at the alternative site by changing residues here. Okay? Indicating then that the chemical groups are affecting and the charge distribution is affecting the positioning on the metal ion. Now, give you 2 minutes with a single-stranded RNA. So we demonstrated many years ago that the RNase P does not need this part of the acceptor stem. It cuts at several positions. As I said, if it's single-stranded, it's not capped, what we know today, then you get unspecific cleavage. So that is consistent what I said with the A248 capping of the and stacking on top of the G+1 C72. Now, others have shown that in the presence of C5, what you do see that you have substrates that are single-stranded. Now, also in the Bacillus subtilis system, as well as in the E. coli system, people have shown that. So we took advantage of that because we noticed in the pseudonotus substrate that it was cut in the lead, in what we refer to as the leader, and generated small substrates that were 9 nucleotides long, 8, 7, 6, and 5, They're still cut, but at a very low catalytic efficiency, very low rates. So, and we can also see that this one, because these ones have the potential to might be able to form a double helix or pair such that it's recognized by RNA's pRNA. This is without the protein. But this one, where is it? This one cannot. So we know that it can indeed cut a single-stranded RNA. And if you add the tRNA that actually interacts here, the action is up here. If we add a tRNA, then we alter this cleavage pattern. So then you see alternative sites of cleavage, indicating then, yes, this information here, this interaction induces a structural change, conformation change here, up at the cleavage site, such that it cuts activity. And in relation to RNase MRP, which is a eukaryotic RNase, which is involved in rRNA processing, it cuts single-stranded RNA, that's the substrate. It's involved in the cell cycle, and there are similarities between RNase pRNA and RNase MRP, and this is the single-stranded. And we know the structure of this one, and this is based on Ming Li at Shanghai. So what you have is the MRP, which is this structure, and this is RNase P, and this part, the C domain, catalytic domain, is very similar to the catalytic domain of RNase P. And even the proteins that are associated with RNase P, you can find them in RNase MRP. So there is a coevolution. So, where do we stand? Future questions. Processing dimeric, multimeric precursors. Yes, that's important because we don't have little knowledge of that. Processing of mRNAs. Yes, mRNAs are substrates for RNase P. I don't know about quadruples. I'm open. And, And the ribosome, if it's associated with the ribosome, could be. And then the degradosome, that is to say degradation and RNA processing. And expression and regulation. Those are questions that is needed to be answered and are directed. And evolution. And if you can find this in a recent article, review article, and this is a thematic issue in JBC that was published earlier this year. And it has 6 interesting articles on RNA. And as we know, RNA did it again for this year's Nobel Prize in medicine and physiology. So, thank you. These are the people who have contributed to this. And here we also have a couple of others. And I will acknowledge my collaborator, Venka Kopalan at Ohio State University. And of course, Yotti, for all the discussions and nice lunches with Swedish pancake and pea soup. And if you are fond of pea soup and pancake, in the south, you eat the pea soup first. And if you don't finish your pea soup, you cannot have your pancakes. But in the north, if you eat the pancakes first and then the pea soup. I don't know why, but there is a difference. Sweden is quite long. You know, if you turn it around, flip it around from the north to the south, you know where you end up?
South of Italy.
What?
South of Italy.
No, you end up in Rome.
That's good enough.
Yeah. There are many ways to Rome, you know. Thank you.
What turns out to be interesting is that despite the fact that I've heard you talking on this in several occasions, but every time I hear you, I get a new angle of it.
Yeah.
The new angle that I am discovering this morning is when you substitute 2'-hydroxy with 2'-amino.
Yeah.
The site of cleavage changes. And when you say that, you do not say what is the product form.
product form after when you're subjected to cleavage?
Yes, because the site of cleavage changes when you put
Yeah.
triple amino
Yeah.
instead of triple hydroxy. You say site of cleavage changes.
Yeah, because you have a
Where does it change?
no,
N minus 1, N plus 1?
N minus 1. Because pardon?
What is the product?
The product, I would say, I don't know about I mean, yes, it attacks from the still on the other side, so the 5' phosphate is generated. But you have a NH3 plus, so that would compete. And if you have a magnesium, which is 2 plus, and that would, you know, plus plus doesn't match.
You know, it's like reading a review article.
Oh, yeah.
When you read a review article more than once, give a couple of weeks, read it again,
Yeah.
and you discover that something that you've missed in the first time.
Of course.
And hallelujah, that is science.
Yeah. Making sense of the unexpected.
Yes.
Can I take one more question?
Okay.
So, have you tried 2' fluoro or methoxy? At that dose?
2' fluoro, yeah. Roland Hartmann and his lab did that and published in JBC 2003.
Okay.
So, yes.
Is it similar or?
If I remember correctly, because we have tried several different labs have tried 2' hydroxy, 2', just the proton there, and link RNA, and SH, I don't remember. No, I don't remember. I shouldn't.
Okay, to back up your question.
Yeah.
Was the 2' fluoro down in Hartmann's work or up?
I don't know. I don't know. But what?
Let's thank you for this
Yeah.
wonderful lecture. So our next speaker is Professor Daniela Monteraccio from University of Naples, and she has diverse interest on nucleoside chemistry. I think today she is going to talk about discovery of an aptamer containing quadruplex structures against a protein target. Daniela.
Okay. Thank you. Thank you, Chair, and good morning, everyone. It's a great honor for me to be here today in Ljubljana to celebrate the great scientist and good friend, Professor Jyoti Chattopadhyay. I do thank Professor Janez Plavec and this group for organizing this wonderful symposium, and it was a great opportunity for all of us to really be together and further building this very nice community. So thank you, Jyoti, for being here, and thank you, Janez, for inviting all of us here. This story is about G-quadruplex structures, so we go back to this non-canonical DNA structures. And I will present to you today some recent data from my group at the Department of Chemical Sciences in Federico II University in Naples, Italy. Our university is also celebrating a very important anniversary this year, since it's exactly 800th year since its foundation. So it's the oldest secular university in the world, and we are very proud of it. And the story is about aptamers, so I will present some data. Part of them were already discussed in Tokyo in the International Roundtable taken about 1 month ago, chaired by Professor Naoki Sugimoto and Takeshi Wada. But there are also new parts and new results which are here presented. So, very general introduction. Aptamer is a general term referring to any synthetic short DNA or RNA oligonucleotide which is able to recognize with high affinity and specificity a given target, which can be typically a protein, an enzyme, but also a small molecule or even a cell, an entire organism like viruses and bacteria. In most cases, these molecules are not identified through rational design, but by the procedure which is called SILEX, which is an in vitro iterative selection procedure starting from random sequences, starting from huge combinatorial libraries of random sequences. The interesting thing is that if you look at the literature, there are indeed many aptamers which have been identified and which are really rich in guanines in their sequences. And many guanine-rich oligonucleotides are able to form G-quadruplex structures. So the interesting thing is that indeed this structural motif is very advantageous to build aptamers because in principle G-quadruplex structures compared to duplex structures have twice the number of negative charges per repetitive structural unit, and this can be very advantageous if you have to recognize particularly a positively charged binding site in a protein or an enzyme. But in addition, G-quadruplex structures are much more polymorphic than duplexes or hairpins. And these polymorphisms typically involves not only the molecularity, but also the orientation of the strands, the nature and kinds of the loops, and also the syn or anti conformation of the guanines with respect to the sugar. The entire amount of these variable structural motifs can, of course, build a large number of different architectures which can much better adapt to their target. And this story is part of it being published in this recent work, and deals with new G-quadruplex forming aptamers we have developed against HNGB1. HNGB1 has been really studied a lot in our group. We have first analyzed these systems with a standard annealing procedure, but also we obtained very different results when the aptamers were not annealed, and I will tell you why. So the target is high mobility group 1 protein. It's a very small non-histonic protein associated with chromatin, which indeed has a lot of physiological activity, mainly involved in remodeling of DNA in nuclei. It is characterized by 3 independent domains. And it has been known to actually be secreted in large amounts extracellularly, both passively and actively, when cells are under inflammation conditions. And when extracellularly secreted, this protein is indeed involved in the pathologies of sepsis, arthritis, atherosclerosis, but mainly in the onset and progression of cancer. So it has been recognized a very good target in anti-cancer therapies. So the interesting thing is that you can actually inhibit extracellularly HBG1, and if you find a good inhibitor, then you actually block the interaction with its natural receptor, which is the membrane protein RAGE. And if you block this interaction, no inflammation starts. And HNGB1, I told you before, extracellularly works as a chemokine. So indeed, it's not only causing inflammation, but also promoting many other very pathological functions. Previous findings actually demonstrated that this protein is a DNA binding protein with a specific affinity for distorted DNA structures. In previous works from my group, we also demonstrated that it was able to recognize with high affinity kinked DNA duplexes. But more recently, Bruno Pagano and Giussara Amato from the Department of Pharmacy of my university demonstrated that in pull-down experiments from nuclear extracts, the sequence TEL26 extracted from the human telomere strand, which is well known to form a G-quadruplex structure, was indeed very well recognized, was able to recognize HNGB1. So we had the very important finding that this protein is able to recognize a very well-known G-complex structure. From this knowledge, we actually decided to use TAL26 as the inspiring motive to build a library of G-quadruplex forming oligonucleotides. So basically the idea was to modify the TTA trinucleotide stretches in the middle of the sequence, so to keep the GGG tracts, which are necessary to form a very well stable G-quadruplex. And in the variable positions, we only inserted the A or T, so to avoid the possible formation of other duplex-based structures. And thus, we obtained a pool of 512 different oligonucleotides. We synthesized them, and we analyzed them by Silix, using, of course, HLGB1 as a target, and VGF in the counter Silix process, since VGF is another G4 binding protein, which is very highly abundant in the extracellular medium. And after this process, we actually ended up with a set of 14 different sequences, which were the one having the highest affinity for our protein. Then we analyzed these systems not in potassium, which is, of course, the most abundant cation in the intracellular medium, but in sodium, because, of course, we wanted to mimic the extracellular conditions. And so we analyzed the system in PBS, which is a good mimic of extracellular environment. And we also, as usual, treated our systems under standard annealing. That is to say, keeping the oligonucleotides 5 minutes at very high temperature, and then very, very slowly cooling down the systems at room temperature overnight. But also without annealing them. That is to say, simply keeping the solution at room temperature and diluting the original aliquots in PBS. So the annealed systems actually were analyzed by standard biophysical treatments. So first of all, we recorded the UV spectra at different temperatures and obtained the TDS profiles. And TDS are typically a very well-known signature of a specific secondary structure, nucleic acids. So this is the typical TDS of a G-quadruplex with this maxima and this very diagnostic minimum at 295 nanometers, sorry. And for the annealed aptamers, most of them indeed showed to form a G-quadruplex structure, but two sequences, L16 and L41, not really giving a typical profile of a G-quadruplex. So we supposed, we deduced that probably some unstructured system was present in solution too. Then we recorded the CD spectra in PBS, and as you can see, a set of oligos show the typical CD profile of hybrid G-quadruplex structures. Other oligos show the typical profiles of antiparallel G4 structures, but two systems actually show to be a mixture of parallel and antiparallel, and L16 and L41 gave CD profiles in which probably there was a large amount of parallel G-quadruplex structures plus something else. CD melting experiments were particularly important to verify the stability of these G-quadruplex structures in PBS. As you can see, TAL26, our system of reference, had a melting temperature of 51 degrees, and all the other oligonucleotides gave actually much lower melting temperatures, indicating a lower stability of our systems compared to TAL26. However, in all cases, the stability of these G-quadruplex structures was not that high, indicating that somehow at physiological temperatures, they were not fully structured. Of course, we analyzed the ability to resist enzymatic degradation. So I don't know what happened here. Sorry for this. There is not the indication of our gels. Anyway, when left in fetal bovine serum, our oligonucleotides showed indeed very low resistance to nucleases. The most resistant oligos were the 4 ones, which were actually the most stable in their quadruplexes. So there was a very good correlation between stability to nucleases and thermal stability of the G quadruplexes. In all cases, the half-life times were between 1 hour and 3 hours and a half. That is not a really good result. So at this point, we're not very happy about the behavior of these aptamers because, first of all, their half-life times in serum was not very high, and then their thermal stability was not very high. So we decided actually to analyze the same oligos, but without the thermal treatment as a first manipulation, and analyzed all the systems again by UV, CD, UV melting, native page analysis. So the most striking thing was that the CD spectra of many of these candidate aptamers actually differed a lot if the systems were annealed or not. This was not the case of our reference oligonucleotide TAL26, which you can see keeps the same profile with or without annealing. But with the exception of B6, D40, all the others essentially showed a very important conformational switch from mainly hybrid or antiparallel to parallel G4 structure. And this was the case of all these systems with the red circle. This was not the case of L33, L37. So the conformational analysis was, of course, confirmed by CD melting experiments, showing that those sequences showing the highest conformational change and moving towards a parallel conformation, indeed were the ones having also the highest melting temperature. So the idea was that the parallel G quadruplexes were much more stable than all the other quadruplexes formed by the other systems. And as you can see, the melting temperatures here are well below, in some cases, 50 degrees, and some have 63, 61 degrees as melting temperature. The nuclear stability experiments were also particularly intriguing because there were some aptamers who actually could resist under the same conditions that's before, in 80% fetal bovine serum at 37 degrees, for almost 48 hours. There was, for example, in the case of L12, 40% of the initial oligonucleotide, which was completely undigested after 48 hours treatment. And all the half-life times were indeed much, much higher. Again, the best systems in terms of resistance to nucleases were the ones having the highest melting temperatures of the G4 structure. So again, we had a very good confirmation of the correlation between nuclear stability and thermal stability of the G quadruplex structures. The interaction with the protein was tested with Ilona assay. So we first immobilized the protein in the form of a stag on a copper-coated 96 well ELISA plate. And then we added the biotinylated aptamers. Later on, we added the horseradish peroxidase streptavidin, which of course could take advantage of the tight interaction between biotin and streptavidin. And finally, we added the horseradish peroxidase substrate, which gave a chemiluminescence signal, which was proportional to the amount of aptamer initially added to the protein. So, for the not annealed aptamers, we obtained indeed very intriguing results, because in all cases there was a very high chemiluminescence signals, but some aptamers were much better than the others. And the best ones were here A32, L12, L13, L16, L17, and L41, which indeed were the ones having the highest amount of parallel G4 structure in the mixture which constituted that, and also were the ones having the highest melting temperature in their CD melting analysis. What happened to the annealed aptamers? So the same systems analyzed after annealing with this Ilona assay. Well, under the same conditions, basically the chemiluminescent signal was very low and similar to the blank. So we had actually to increase the amount of initial aptamer added to the protein on the plate to observe some differences with the blank and differences particularly with the scrambled sequences we used as negative control. The scrambled sequence was a 26 mer having exactly the same base composition as 26, but no contiguous guanines, so that no G quadruplex could be formed. And as you can see, there were some good binding here, but anyway, the chemiluminescent signals in all cases was 2 orders of magnitude below the one obtained with our best aptamer not annealed L12 without annealing. So this meant actually that there was a big difference in their functional behavior, not only chemical behavior. The ability to inhibit the protein was at that point measured with in-cell experiments. So we used first of all this kind of cells, NIH333, which are the typical kind of cells used to test the ability to inhibit cellular migration. Since cellular migration is one of the, let's say, basic functions exerted by HNGB1, we wanted to test if our aptamers were able indeed to inhibit and partially block this effect. And to do that, we used this Boyden chamber on the upper layer of this membrane. The cells were deposited, and in the lower compartment, a physiological solution was inserted. So we could measure what is the basal cell migration on the lower level of the membrane. And after crystal violet staining, this is what happens to the lower level, lower layer, sorry. We see some migration, which is, let's say, the 0 level. But what happens if we add the protein in this solution? We have a much higher cell migration. So we measured the inhibition to block the protein upon adding all the different aptamers. And these were our results. We put 100% the effect due to the only presence of the protein. We added 10 nanomolar HNGB1 to our solution. This is the negative control, that is to say the basal cellular migration obtained without any chemoattractant, that is to say without any protein in the solution. And these are the results when we added to the protein also each of our tested oligonucleotides. And as you can see, the scrambled oligonucleotide only gives a very low inhibition of HNGB1-induced cell migration. 1026 is, let's say, more effective than the scramble, but all our aptamers were indeed much better inhibitors than 1026. And there were some aptamers which indeed proved to be much better than all the other ones. Particularly, look at A32, L12, L13, L16, L17, L41. These are exactly the same set of oligos able to form the most stable G quadruplex structures, basically in parallel topology, and also having the highest protein affinity. The interesting thing is that All this data have been obtained with the aptamers when not annealed. So we repeated the same experiments with the annealed aptamers. And in the case of AL12, our best candidate, you see that indeed there is inhibition of HNGB1 promoted cell migration, but the ability to inhibit the protein is 4 times lower. So we actually confirmed our experiments also testing other aptamers of the same set that we have analyzed before. And for example, you see we have here this big difference for L12, but if we analyze the L30, there is no big difference. And we rationalized this difference, considering that for L30 there was no big conformational switch upon annealing. In contrast, L12 was one of the set which underwent the, let's say, more marked conformational switch, going essentially from hybrid to parallel, or let's say the same thing from the other side. We start from not annealed, so when not annealed, the system is essentially parallel, and when we finally annealed all the system, we came out with essentially hybrid G4 conformation. So we really had so many data, and we wanted to better rationalize them. How came that the best aptamers concerning resistance to nucleases, thermal stability, protein affinity by activity, after annealing actually have all reduced activity? And a solution to this clue was obtained by analyzing the size exclusion HPLC chromatograms. By this technique, we could actually notice that the not annealed aptamers in many cases did not show a single peak but 2 peaks. And the additional peak was the one of a dimeric species. This dimeric species was not indeed present in all cases, but the best aptamers in all the conditions I mentioned you before were those having, in fact, the highest percentage of dimeric species. The annealed aptamers only showed monomeric species. And when we separated not annealed L12 into its dimeric and monomeric component, you see that the CD spectra were absolutely typical, the first one of a parallel G4 structure, and the second one, the monomeric one, of a hybrid G4 structure. The KD of the two separated systems were very different. The monomeric was 4 times less effective than the dimeric one. And the two systems, when isolated, were actually very, very stable. So conformation indeed matters. The interesting thing is that the dimeric species, when isolated, was able to completely abolish the HNGB1-induced cellular migration with very, very low KD. So in conclusion, upon annealing, we irreversibly destroy the dimeric species, which are indeed the most stable and most effective ones. This is just a cartoon. We have no idea of the real structure of this dimeric species. But the conclusion of this work is that by SILIX, we were able actually to identify very effective aptamers against this important protein. The dimerization is indeed the key event for these aptamers, and these are spontaneously formed probably in the lyophilized form of our aptamers. And these aptamers can be exploited to develop highly selective agents for both anti-inflammatory and cancer therapies. 2 quadruplexes, G quadruplexes can be better than 1. Ongoing studies, of course, are now aimed at getting more and more structural information about these systems. But we are also designing, synthesizing, and characterizing covalently bound dimers of L12. More stories on G4 forming aptamers are going on in my lab. I want just to conclude by thanking all the people in my group, and mainly Professor Domenica Musumeci, Dr. Claudia Riccardi, Dr. Chiara Platella, who's here in the audience, and Inanna will tell you more stories about G4-forming aptamers, Dr. Ettore Napolitano, Dr. Andrea Riscolo. Of course, all the students, a group of Professor Angela Arcello for the biological experiments, and Dr. De Franciscis and Carla Esposito for the Silix experiments, Italian Foundation for Cancer Research for funding, and of course, all of you for the kind attention.
Very nice presentation, thank you. Have you looked at any other cell types other than NIH3G3, which are quite special cells?
Absolutely, absolutely. Of course, NIH3T3 cells are murine type cells, but these are the standard kind of cells using for standard in the literature kind of cells used for this cellular migration assays. But we also looked at the experiments on A549 lung cancer cells, and indeed we observed a very good inhibition of cell migration also on human cancer cells. So, I mean, these data are also in the published articles, and it's very, very interesting because indeed we obtained an IC50 value of 28 nanomolar with L12 without annealing, not separated, no special treatment, no special manipulation. The best inhibitor of HNTP1 in the literature is a natural tryptophan, which is glycyrrhizin, and its IC50 value is of 50 micromolar. So, I mean, we went down of at least 3 orders of magnitude in activity. Thank you for the question.
Very nice work, Daniel. I wonder if you have considered chemical modification of your L12, because that's what we do with ASOs. So it's been always productive. So I would imagine that you can stabilize with your quadruplex by just taking the right modification.
Okay, yes.
Are you looking into it?
Yeah, thank you, Yogesh, for the question. And of course, it's the obvious idea. You know, I have a synthetic organic chemistry background, so I always think about how we can actually improve nature. The nice thing of these systems is that they are all natural oligos, so no special modification. You just use them and they are active. But we are actually trying to get much better molecules out of it. The thing is that we have no idea about the real structure of the dynamic species. Probably they are not a single one, there are more conformations. We are trying to get more results in the collaboration with Javis Blad, and particularly with Marco Tchaikovsky, because of course if we have a structural information, we can actually design better systems. Because if not, I mean, you know, it could be a plethora of possible modifications. But of course, this would be the obvious thing.
Excellent work. Excellent work. You raised many questions. Thank you. The only thing about conformational variations of conformational deprivation in the linear, did you try to use different materials, different materials? Because pH of the cell is very different than you have in vitro.
Yeah, of course.
Even the cytosine which sends them to the tissue very close.
Okay, also this is a very important question. Of course, you see that the interesting thing of the systems is that indeed, in many cases, there are mixtures of different conformations.
Yeah.
So they coexist. But we have a prevalent one, and without annealing, we have a prevalent alveolar conformation. If you change the solution, everything changes, I can tell you. So we decided to focus on PBS because it's the best mimic of extracellular conditions. But if you go for example, potassium-rich conditions, subject work. So if you also change pH, could be even more different. But we decided to focus on physiological conditions.
So physiological condition, that's the discussion here. What is physiological condition?
Okay, yeah, we fix the let's say.
For example, I read somewhere a paper that you want to do something in physiological condition, you lyse the cell, centrifuge that, collect the supernatant, take that supernatant and dissolve your molecule there, because that supernatant really mimics cellular condition. Then you do the
This is a very, very important sentence. We try it. And then
So in the interest of time, we will stop here. Yeah, so we can continue during the lunchtime. So let me thank all the three speakers for this wonderful session. And let me thank Yanis for giving me an opportunity to chair this session also. We will reconvene here at 2:30. Yeah, after the lunch. Thank you. One co-host at the beginning, somebody missed it. Miller is not coming, so we have half an hour. Enjoy. Fantastic.
Can you keep our computers here?
Yeah. I cannot guarantee it will be there when we come back.
Still on the road.
Good start and continue. I hope you got some good coffees after lunch. Had some time to walk around a little bit, so we are ready to continue our presentations, our discussions. It's a big pleasure and honor to welcome Professor Rakesh Vidhu from Perth. He's world winner, 4 affiliations. Rakesh, we all look at Western Australia as a very encouraging and fast-growing area in the world, and I think I'm proud to all know you and see developments you guys have contributed in this biotechnology area. So the floor is yours.
Thank you very much, Yanis, for the introduction. So before I start, it is my great pleasure to be here this afternoon, and I consider this as an honor to be part of the 75 years of excellence celebration for Professor Jyoti Chattopadhyaya. So although I have not worked personally with Professor Chattopadhyaya, but still I've been very fortunate enough to be interacting with Professor Chattopadhyaya, and also I have read the papers of CARBA, LNA, and all other nucleic acid papers with enormous admiration. And while I was also been working with Professor Jesper Wengel for LNA chemistry, so that's where I came to know more and more about CARBA LNA. So to beautiful chemistry. So I'm blessed to be here this afternoon to be with Professor Jyoti Chattopadhyaya. Thank you so much for the opportunity. So again, Yanis, thank you so much for extending the invitation to be here. So I always consider this as an honor to be working with you. Okay, let's move on. So I have a few disclaimers before I proceed. I come from Australia, western part of Australia, Perth. That's where I work. And obviously, as you know, we are blessed with wonderful beaches and wildlife. And yesterday night, Yogesh said he's been to eastern part of Australia, and welcome you next time welcome you all to be coming to Perth. This is coca. You probably may not have heard enough about coca. Coca is actually exclusive to Western Australia. There's an island called Rottnest Island, and you can take selfie with them. They're wonderfully good poses. I mean, they can pose wonderful picture with you. And that's my institute. Okay, so we all know that our genetic information is stored in the form of a long twisty molecule called DNA. And the information is then passed through our messages called RNA, translated into proteins for various functions of our daily life. And sometimes these proteins are either upregulated or downregulated or not expressed at all, and that could potentially lead to diseases. And traditional small molecule drugs target these proteins in most cases. But we can use nucleic acid-based therapeutic approaches to target the RNA at a very early stage and control or regulate the expression of these disease-causing proteins. And I also like this Time magazine cover, which was published way back in 2001, around the same time as Human Genome Sequences released. So in that, they highlighted that amazing new medicines can be developed based on our genetic material. So as you all know, now we have around 17 different small RNA drugs on the market based on different technologies, mainly antisense and siRNA, and also aptamer. So of these, three of them, if you look at the exon is 51 and y-on is 53 and amount is 45. These were developed in Australia, but obviously came through Sarepta Therapeutics in Boston. So today I would also like to mention briefly about melasyn. And this is my colleague Tim Yu at Boston Children's Hospital, who diagnosed Mila with an extremely rare, ultra-rare disease called Batten disease, mainly because of a point mutation in CLN7 gene. So the reason I wanted to tell you about this story is because the drug from the diagnosis of the disease to the injection into Mila's body all happened within about 10 months time frame. And that is basically what our technology can demonstrate or can do. And we all believe that, so the drugs can be developed much faster these days. So in my laboratory, we develop synthetic small RNA therapeutic molecules using antisense, siRNA, microRNA, and DNA enzymes, and combine them together with a delivery cargo molecules. We use different technologies, mainly nucleic acid aptamers, fatty acids, and vitamins, and also peptides and acetyl-galactosamine to deliver them specifically to the disease sites within our body. And for that purpose, my research group is categorized into three main areas. Some of us focus on synthesis chemistry, therapeutic development, and also drug delivery applications. Ultimately, we focus on their clinical development. So for the chemistry area, we mainly work with modified nucleic acids, and we synthesize a lot of modified oligonucleotides. And as you know, that must be different chemistry. So a number of nucleic acid analogs. So I'll use my laptop next time, but it's okay. So a number of nucleic acid analogs have been developed over the years, but only a handful of them were advanced to clinic. Still, there are significant room for improvement to introduce multiple chemistries in designing these ASOs. Yeah, I can see all of these ChemDraw figures did not come through. So if you look at these 4 FDA-approved drugs for the treatment of Duchenne muscular dystrophy, it's made of phosphorodiamidate morpholino oligomer chemistry. However, there are significant limitations associated with those chemistries. They require to be administered in very high dosages, and that's mainly because of the rapid clearance. Within about 3 hours of administration, about 95% of the drug is cleared through urine, so mainly because of their poor cellular uptake. And as a result, they obviously are very costly, around $300,000 per patient per year. So the PMOs are actually not compatible with conventional phosphoramidite chemistry. So we started out that area by introducing the phosphoramidite variant of PMO. And I started that in 2016, and we published, so yeah, I think I can see the morpholino nucleic acid, which is compatible with the phosphoramidite approach. So using that approach, we have constructed an oligonucleotide in which we have introduced a uridine MNA monomer and constructed an MNA 2' or methyl PS antisense oligo, which is about a 20-mer. And in parallel, we also synthesized a fully modified 2' or methyl or phosphorothioate ASO as well antisense oligo. And then we evaluated their potential to target the dystrophin gene in mouse dystrophin, MDX mouse myotubes. And then we transfected them using lipofectin as a transfection reagent, incubated for overnight, and then we isolated the RNA, performed the RT-PCR analysis, and that's what we find, that both the fully modified 2' or methyl and the MNA incorporated or modified and antisense both induced splice switching, which you can clearly see here. But since the yield of this monomer is extremely poor, and Marv and in collaboration with Professor Marv Puratas, my mentor at the University of Colorado, we have evaluated the potential of another chemistry called thiomorpholino chemistry, but I think I'll jump. So here, none of these chemistries and the oligos will come through. So. Yeah, I've got a laptop there. Is that okay? Do you have your own? Yeah, I'll put it on my I'll start from here. Sorry. So, yeah, in collaboration with my mentor, Professor Marv Carruthers at the Uni of Colorado, we have evaluated the potential of thiomorpholino chemistry to induce splice switching. So the only difference with MNA versus thiomorpholinos is in thiomorpholino, the morpholino nitrogen is directly connected with the phosphorus atom, unlike in MNA, which is NOP, like in conventional phosphates. So so for that purpose, we have used Duchenne muscular dystrophy as a model system to explore the efficacy of thiomorpholinos to induce splicing. DMD, as you probably know, is a serious muscle wasting disorder, mainly affecting boys. Individuals with DMD lack a protein called dystrophin, and there are multiple mutations in one or more exons or deletions of certain exons which really ablate the expression of dystrophin protein. Mainly, it disrupts the reading frame, which prematurely terminate the expression of dystrophin protein. So if there is a spelling error in the dystrophin gene, basically it leads to the corrected genetic messages. So we can use an antisense oligonucleotide that can specifically target the mutation containing exon and delete that segment and reinstate the reading frame, which will then produce partially functional dystrophin protein. And that's what we are actually exploring. So for that purpose, we use antisense oligo fully modified with thiomorpholinos, and we target exon 23 in mouse myotubes in vitro. And we basically constructed a fully modified thiomorpholino antisense oligo of a 20-mer. In parallel, we also used a conventional phosphorodiamidate morpholino oligomer. And we have transfected the MDX mouse myotubes using lipofectin, and we have incubated for overnight. The next day, we isolated the RNA, performed the RT-PCR analysis, and evaluated their potential to delete exon 23. That's the full-length dystrophin protein, dystrophin gene here, and that's gene's transcript basically, and that's the deleted exon 23 deleted product, and this is basically the exon 20 to 23 deletion product today. So if you look at thiomorpholino, TMOs, basically it is very efficient to induce splice switching at a very low nanomolar concentration. Whereas if you look at the conventional PMO, it did not induce any splice switching at all. And that is not very surprising because, the conventional PMO do not transfect very well with lipofectin because of this charged neutral backbone. So in real, basically the PMOs are electroporated. So we also compared the efficacy of PMO versus TMO using that approach. Here again, we find that both TMO and PMO induced exon 23 deletion, whereas if you look at TMO, it might be slightly better compared with PMO. But obviously, electroporation or using conventional lipid-based transfection approach might not be clinically relevant, so we have to really perform a naked transfection using those two ASOs, and that's exactly what we've done. And then here we have incubated that over a period of 5 days without any transfection reagent, and after 5 days we again analyzed the RNA. Here we find that the thiomorpholino could yield some exon 23 deletion product, whereas the PMO could not do that at all. So what if we use the conventional phosphate there, the phosphate variant, not the thioate? In this case, we did not see any exon skipping at all. So here we have truncated the size from the 20-mer to 18-mer to 16-mer, and here we find that all truncated candidates basically induced splice switching, but when it came down to 16 mer, it wasn't as effective as compared to an 18 mer or 20 mer. So we have also constructed a mixmer ASOs. So 3 different types of mixmers, 2 mixmers and 1 basically a gapmer type. And then we evaluated their potential to induce exon 23 deletion. Basically, all of these 3 constructs induce exon 23 deletion, but we found the mixmers were better than the gapmer. Basically, every alternating DNA, TMO, chimera, or the mixmer found to be better. So then we actually compared the potential of thiamorpholino compared with the other negatively charged chemistries which are currently in the clinic. So we have constructed a fully modified 2' O-methyl and a 2' O-methoxyethyl antisense in parallel to TMO, and we have performed very similar experiment. And if you look at the thiamorpholino compared with 2' O-methyl and 2' O-methoxyethyl, you can clearly see that at lower concentrations, TMO is found to be far more efficient compared with 2' O-methyl or 2' O-methoxyethyl. So that again clearly shows that TMO could be a superior candidate to induce splice switching. So how does it equate to stability when it comes to this splice switching efficacy? So we have performed a TM analysis of all of those candidates, and we find that the TMO of TMO is not good compared with other negatively charged or PMO, but still it actually induces efficient splicing. So we speculate that one reason that it works well could be its efficacy to localize in the nucleus compared with other chemistries. So what about its efficacy in vivo? And that's exactly what we've done next. So we have injected the thiamorpholino in parallel to PMO intramuscularly in an MDX mice. About 5 microgram dose in both left and right tibialis anterior muscle, and then after 4 days of incubation, we have culled the mice and isolated the tissue, and we performed the immunohistochemistry, and that's what we find. And here we find that the TMO could induce some dystrophin expression compared with PMO. So based on this initial preliminary data, we have performed a proper IV study. So in this experiment, we have basically 4 different groups. In group 1, it's just a saline control group. In group 2, basically we use TMO and then PMO and 2' O-methyl PS. So we've used 50 mg per kg dose. All of them were administered via IV. So we have actually injected once every week for 4 weeks. And after that, we sacrificed the mice, and then we have isolated the tissue, performed the immunohistochemistry again. And here we find that the TMO could induce nice dystrophin expression compared with the saline control group. And also that was the case when we compared the efficacy of PMO versus TMO, and we found the TMO far better compared with 2' O-methyl. So based on those initial observations and also various other experiments on other gene targets that we've been working, so Marv and I decided to form a company to develop thiamorpholino-based therapeutic molecules. So for that purpose, we formed Progenis Pharmaceuticals. So Marv and I believe that this thiamorpholino could be useful as a therapeutic molecule for drug development or developing potential drugs. Obviously, our objective is we think that it could be far more safer and effective, and we believe the drug could be accessible and affordable for people all over the world. So the foundation technology of Progenis is thiamorphalino, and this is one of the evidence that we would like to show you today. Basically, the off-target potential of thiamorphalino versus all other chemistries that we've done recently. So we have seen that the thiamorphalino candidate did not downregulate a gene that we are targeting, basically IgG4. I mean, they basically only downregulated this gene, whereas if you look at other chemistries, for example, 2'-O-methoxyethyl, so there are, as a gapmer, 2'-MOA gapmer, that basically 1,823, so, and that is the case also for the upregulation. And also with PMO, you see the same trend there. So it indicates that it could be a better molecule. We're still in a very early stage, so lots of experiments needs to be done. And that's the recent data. I mean, zebrafish, as you know, I mean, even if you put any 2'-O-methyl or 2'-MOE, it will simply die. And that's what we saw. So this is a comparison with, well, I mean, what we have found in zebrafish. So we found TMO could tolerate, but when we used 2'-O-methyl and or methoxyethyl, I mean, we could not find any live or viable zebrafish. Okay, so the manufacturing of thiamorphalino, we are trying to do it through Syngenis at the moment. Okay, so that's about TMO work, and I also evaluated the potential of LNA modified antisense oligo to induce splicing, and we found that LNA could induce efficient splicing even at a 14-mer construct could actually efficiently yield splice switching. Together with Pete Herdwine, we evaluated the potential of HNA and CNA and ANA, and also we evaluated the potential of 2'-fluoro and various other chemistries as well. So I would like to stop there for today. So I thank all of my group members and the funding bodies, and of course I thank you very much for your attention. Thank you so much.
Thank you very much. I'm sorry about the technical problem.
Thank you. So I
thank you so much.
Thank you, very good presentation.
Thank you.
So about your TMO, so I see you use the next injection with IG.
Yes.
So about 15 milligram kilo. Milligram kilo. So do you think about to liken with penetrate peptide?
No, we haven't used, it's just a naked administration, so we haven't used any cell-penetrating peptide. Obviously, we used a very high dose just to see the tolerability in mice, how does it tolerate, and that was the intention. And while obviously to see whether it works.
Yeah, because I see your dose is very high.
Yeah, it's very high. Yeah, that's on purpose, yes.
What muscles like to penetrate?
Exactly, yeah.
What's your comment about recently the ability
yes.
and diet they use the antibody,
correct.
Which conjugate with the oligonucleotide AOC.
Yes.
You can IVRF remember around 3 milligrams per kilogram.
Yeah, I mean, that's the direction that we are also going, not with the, the antibody conjugate, with different approach. So delivery is key, and that we are exploring, we are progressing with our delivery cargo with type 2.
I think your sequence modification is very innovative, but I think you need a ligand to make a muscle.
Yeah, very true. We are actually exploring that. Thank you very much.
Rakesh, nice work. I wonder if you have explored reducing the phosphatidylate load. So more and more companies are looking at reducing the number of the thioates in the molecule.
Yes. I'm glad that you asked that question. So I was in Canada last week, and then this was my presentation. So we have, that we will publish that work soon. So we could bring the thioate down up to 11. So 11 thioate, and the rest are conventional phosphate.
The rest is, you're still going with 18 mer or?
20.
20 mer.
Yeah.
Okay.
So it works very nicely.
I see. And
Yeah.
do you have a motif which works better?
So-
So is it scattered or you put a 3 prime 5 prime end?
Yeah, I mean, it's ideally either the ends, like even at 5 prime end or even at 3 prime end, it works very nice. But if it's in a mixmer format, it can still maintain the same efficacy. But if it's in a gapmer format, no. If it's actually the position, these ones, I mean, we've done a systematic analysis.
Oh, I see.
Yeah. So a systematic analysis, starting from the 5 prime end all the way to the 20mer, and from the 3 prime end all the way down to the 5 prime end, and we see the trend, how does it work. And plus we did the gapmer and the mixmer approach separately
So
in
the
comparison.
follow-on question would be the affinity. So have you looked at the
Yes.
TM of the best molecule?
Yeah,
Does it correlate with the high affinity?
Mixmer does, I mean, with the DNA, the mixmer approach, it gives you better TM.
I see.
Yeah.
Great.
Yeah.
How it's parallel with diagnostic approach? I mean,
Yeah.
this is actually fields having application that how many people can get diagnosed? For sure, you have some applications.
Yeah, we haven't used thiamorphin for diagnostic applications as yet. I mean, diagnostics, obviously, the key is affinity. So splicing, I mean, the slide, if you remember the TM slide, it's not, the candidate with very high target affinity to RNA or DNA compared with the other chemistries. So in diagnostics, to be sensitive to pull down, so you obviously need a candidate with very high affinity. So I would say PNA, for example, still very high TM, and yeah. So we haven't explored that. It might be interesting to look into that aspect as well. But for aptamers, obviously, could be useful. Yeah, that's something you can explore.
Okay. My name is It's very trivial question. Can you tell me something more about the relationship between TMO and the fact that you have a less of target?
Yeah.
Because, okay, I can think about it, but there's nothing really obvious now, I think.
Yeah. Maybe one aspect could be the TM difference, but the other, we absolutely don't know. We are still exploring why it actually did not induce any other, like PMO did, and 2' or methyl or methoxyethyl, especially the gapmer actually induced off-target.
Maybe there is a condition is more based on the base and there is some strange
Yeah, I mean the target recognition and the mismatch recognition. So all of these are, currently underway. So I think those are the areas for investigation to, shed more lights around that. Why does it induce off-target binding?
Thank you for a nice discussion. Thank you,
Thank
Rakesh,
you.
for one.
Thank you, Alex. Thank you.
We're switching the format. It's a big pleasure and both honor. Professor Zheng Shi from Nankai. I think, after you.
You try to help me to open up. Yeah.
Yes, absolutely. Thank you so much.
Okay.
You're not there.
Yeah. And thank Yanis for organizing this wonderful nucleic acid family gathering. And we know that Jyoti has been my mentor for. I joined Jyoti's lab in almost 35 years ago. I don't need this, yeah. Almost 35 years ago, I read a letter to Jyoti, and he immediately responded that welcomed me to join his laboratory. So that time is now email by snail mail. So the next year, the beginning of 1990, I joined Jyoti's lab and surprised him because I don't understand English and cannot speak English. And Jyoti say, okay, you have white paper, and write down on a piece of white paper, you have white paper, so maybe we'll try to say, stay a couple of years with me, they say what kind of things can come out of it. And by that time, actually I have no idea what is nucleic acid, and of course forget about central dogma of molecular biology, so basically has none, zero experience, zero knowledge, because I was working with my master degree for the organomechanical chemistry. So that piece of work is far away from any chemistry in life science. So basically, it's inorganic chemistry for the coordination chemistry. And from that moment started, and actually opened my eyes. So I say, okay, the life science actually is full of the chemistry and so much interesting things to go on. So I'm going to stick to this field. And that's how it started. So with the modification of the nucleoside chemistry started with it. And because that time, and that's about 35 years ago. So in China, we don't have any training on instrumentation and software, no computer. So everything started in the lab, then learn how to use NMR machine, how to use HPLC, and how to use mass spectrum. And Jyoti is so helping by demanding in a very short period of time, almost in 3 months, actually I produced, learned almost all everything. So I remember that time is, I'm the last one leave the lab, but the next one is Jyoti. So all the rest people already go home. So so we stay almost night by night. Yes, yes. And I'm the only one in the lab, and then normally he took me to the bar and have a beer. So for that time moment, actually I started learning English, learning the biochemistry, nucleic acid chemistry, of course. Also know how to treat the life, so with a good attitude. So today I actually take this opportunity to thank everyone for coming for the celebration of Jyoti's 75th anniversary. Okay, so my give a talk is from bioorganic chemistry to biomedicine, your journey initiated with Jyoti. That basically I'm trying to talk about today is a recent work we tried to think about the genome therapy. I gave a name on it. So maybe I don't know if it's correct. So anyone welcome for any suggestions. The central dogma for me is now when I say it, it's not just a message, information transfer, it's also the material transfer. Along this line, actually the sensitivity is totally different. So if you have anything targeted on the beginning of the nucleic central dogma, like a DNA or RNA, that'll be much more sensitive. Okay, that means the dosage will be lower and also with the precision. So everybody knows that. So we think that is much more sensitive for the gene regulating elements for therapy. And over the years, when you look at the regulation tools targeting or using nucleic acid, it's lots of things comes up, right? As a genome editing, gene therapy, antisense, and microRNA, and also RNA, and of course, riboswitch enzyme, not also including the aptamer ribosome. For example, like today, we heard about the G4. In my mind, G4 is like a structure switch, so for the elements. So basically, it's not in one. Maybe it's a grafting with a different degree of the interaction, so that it's a dynamic control of the gene regulation. Probably that's the element. Then how to make the full use of elements, and people always think about this. So almost 40 years from 1978, so to the proposal for the antisense therapy, but until they really become the drugs, takes 40 years, long way. And basically what is inside is not the principle. The principle is everybody thinks that's right. But the way to deliver to the really targeted places, always a trouble for the nucleic acid therapy. So that's basically is the things we're thinking about it. And we know for the RNA, the mechanism for this audience basically is very simple, okay? Everybody knows that. So take the risk in the AGA2 and then make an mRNA cleavage. So basically you can use microRNA also do in this same pathway. You can use in the viral vector, and also your chemical modified siRNA put in it, and also you can use in liposome, nowadays using LNP. Basically that's for transferring of the targeting. And we know this expanded the target than normal protein-based drug development. So because they're targeting RNA, it basically expanded the druggable and non-druggable protein targets. So basically everything, nowadays also the linker RNA, the non-coding RNA. So for that one, actually, we thought this will be 2006 when Fair and Mellon get the Nobel Prize. So thought maybe it's an opportunity to set up a company to doing that. So me, Professor Li Zhang and Zhichai Liang in Beijing University, I'm from Nankai University. So we co-founded Pseudo-Rabo Life Science, and now it's become the leading siRNA company in China now. And we actually have about more than 350 people, employees, and right now has 6 candidates in a clinical trial, and have ability basically from the target identification, push the whole through, including the CMC, so less than 10 months, so for every candidate. So right now, probably we have about 40-something different drug candidates and pushing. We just desperately need money for that. So this year, at the beginning of this year, January, so we signed a contract with Boehringer Ingelheim for $2 billion. And also last year, we sold one product to the one Chinese drug company for $0.6 billion for support. Right now, we also last year, Jyoti we set up a new R&D center in Gothenburg called the RiverQ. So it's established for the clinical trials part. So we set up that one, and now we have 4 sites. One site in Suzhou, one site in Beijing for the research, one site in Gothenburg for the clinical trial, and also one for the production, CMC production in Tianjin City, okay? So that's basically, we started for that part. And now the company actually has different lines on the clinical trial and has the ability to push the siRNA into the therapy. And then from that time, I'm thinking about it, so what should I do? Because that's a company that already have so many people doing that. So what kind of things is for me to think about it, using the nucleic acid to become some new type of the therapy part. So that's what I'm thinking about it. So what is it like for me? Then when we think about it, the chromosome, actually, every life process has been regulated by chromosome, genetically, epigenetically, right, with precision, and spatial control, temporal control. So if we can have the chromosome deliver into the places we want it, basically we can cure any disease, right? That's basic principle is that. But think about it, but the chromosome is too big. If, for example, like a human, the longest one, we have a 250 million base, and have about 250 micrometer, and that's why it's too huge for the human cell to penetrate it in it. And then can we think about it how to mimic the chromatin, make a chromatin-like particle which control the size will be penetratable for the cell surface. And if we can make things like that, maybe we can, it's done? You haven't started yet? Okay. Okay, good. Yeah. So how to make this one? Basically, that will be 2 things. For the gene loading capacity should be high, and also we need to resolve the delivery problem. So the particle size should be controlled. Because we know the particle size control the viral vector or non-viral vector, they don't have precision with chemical defined precision. And they will know once they are around 100 or 200 nanometer, basically it can be absorbed by the cell. So the cell penetration is no problem for that. And then they come out with the things is the nano size will be around 100 to 300 nanometer. So how to generate that kind of particle, and also with gene capacity as large as possible, okay? the virus, the largest virus can deliver is about 5,000 kilobase. That's what we're using AAV. And for this one, we think about the mathematics. So any nanoparticle for me basically is an Archimedean solid. So I go to the mathematics department, ask a mathematician, say, how to build out Archimedean solid as a minimum number, okay? And then after calculation, he proved that if with the 3 branches stuff, and you put them together, you only get a 4. I said 4 is enough because we can control the condition to make them become one size of nanoparticle. And with that one, we tried with the combination on the siRNA, yes, they show the pick up the one you see, highlighted one, and they're effective. And the size is really controlled like 30 nanometer. But that's a pure double-strand siRNA. So we use that one attachment, so we can easily put the ligand on this kind of bridge. And then they have a very good specificity to target the cell without the liposomes help, okay? So you don't need liver factor, I mean, things like that. You just use this one, you can construct. But that's only for the RNA part. Then we think about, if this way can do it, then maybe we can make a DNA or RNA hybrid, whatever things. So that would be just doing the PCR, using any DNA template, using a branched primer, so I call it branched PCR, and then they will come out with a nanoparticle. Yes, it is. So the size actually, when you increase the base pair, so they increase the size, but then once you reach a certain level, the size will be decreased. Because in my mind, so we probably can using the double helix parts, and then once it's longer enough, they will have a nucleosome helix part. So it will be compressed. And by that size, so the size becomes small. So for example, you can see once you reach 7,000 base pair, basically the nanoparticle size is not that big micrometer, it's reduced down to the 100 nanometer. Okay, that's how the principle. The rest of the things is will just pick up, because with this kind of particle, for one lane, one edge, suppose you got 7,000 base pair, the whole particle will reach in 250,000 base pair. So that's why you drop the DNA loading capacity problem. At the same time, you control the size, it's still cell penetrable. So with that cell penetrable size, so that will be good for the penetration. And then I call this whole things, we can make a regulation on the different level with gene expression cassette or RNA therapy cassette. So basically you can make different levels of regulation with this part. I call then the different levels of regulation is a genome therapy. So that's why I gave the name on that. And for example, we can pick up the cancer tumor growth singular network, and then you pick up the one overexpressed p53 or silence at the same time silencing CMAC. So see the cell growth problem is that. And you can see the construction is easy. Just put a template and then doing the PCR, then you get a nanoparticle, and the size is about 130 nanometer, which is penetratable. And also in the cell, you can see the dosage response for the overexpression of p53, and also dosage response for the silencing of CMAC genes at the same time. And also for the apoptosis, you using that stuff, you can see that basically generated good apoptosis for that. And also for in the mouse model, so we're using the breast cancer cell. You can see the red line basically, once you have an injection of that, the tumor stops growth. Yeah, okay, finish that. And all right, probably people worry about the most is maybe this kind of things have immune response. And then we check it out. Basically, they have no other immune response. And also the histochemistry showing everything is normal. So with this one, we are pushing this one into, say, put a protect things like a molecular glue, but using the overexpression of the RNA or DNA parts. So to do the same thing, mimic the protect. So that's what we're going on with this one. Okay, and the last one is hope that everybody are welcome to visit Tianjin. I mean, city. The city is a beautiful city. Beijing is the capital, and by the seaside, this is Tianjin city. Okay, thank you, everyone. Yes. I didn't know.
I wouldn't be too stressed because Sandita does not make it, right? You know, so we can shift a little coffee break and with apparatic grace, you will have his turn, her turn, so we can have some discussion. Go back.
Nice idea.
Yeah.
Nice idea that you want to use the cargo in one go. But if that cargo called chromatin
Chromatin light.
has a chromatin light, so just a chromatin and chromatin light.
Yeah.
Make a distinction here.
Yeah,
Chromatin has the control
that's right.
for gene expression.
Yes.
All genes, all DNA sequences are not expressed equally, born equally.
That's right.
Not expressed equally.
Yeah.
We have got, for example, the latest paper that came out last week in chemical communications. Fine metal C. Fine metal C
Yeah.
occurs.
Yeah. I see that paper.
Controls your synthesis.
Yeah.
Yeah, it contracts.
Yeah.
And gene expression goes whoop.
Yeah.
Large.
Yeah.
So the thing is, this is controlledness that epigenetics has given to our system.
Exactly,
So
Jody.
the expression of genes is just too finely tuned. Stop your comment.
Exactly as you said. Actually, for the that's called the epigenetic part of it, and the promoter area regulation. So you basically you don't need to go into the cell to do that. You can use your knowledge preset outside after PCR. You get another particle, you make a modification. Then they will have a tumor specific initiation for the things you wanted, the gene of expression. But then you go to the normal cells because they don't have the promoter region on that places, so they don't function anymore. So that's what we actually is going that direction. Yes. Yeah.
How do you do that outside the cell?
Using enzyme do it.
Using what?
Using enzyme.
Using enzyme.
Enzyme.
Okay, you chop it up.
Yeah, you don't chop it up. You just make modification directly. They have this enzyme.
Okay.
Yeah, for example, on a mRNA 6 metal group, so you just put the methylation on it.
Knowing your work,
Yeah.
you have done some of this work in the plant genetics, I know.
Yeah.
But tell me about that part. Just in a nutshell.
Oh yeah. But Jyoti is asking me what's going on in my lab. So this is a small part. Okay. Yeah. My lab actually now we're focusing on the agriculture for the pesticide discovery, and also for recently I put the whole group into the crop yield increasing agent. So it's not just like a plant regulator type. It's just increasing the yield of the crop. Basically, the principle is very simple. Try to do the opposite way of the tumor, so make them grow faster and also get more yield. So for example, you can silencing a little bit on the mitochondria, so that the metabolism is going slow, and then actually the life cycle of the plant is going longer, and because with the longer life cycle, basically you increase the yield. So normally you can increase about 40% around that places. Yeah.
Non-trivial.
Yes.
Huge.
Yeah.
Unless there's further question, otherwise let's thank Zen again.
Oh yeah. Sorry for that. I thought 30 minutes, so I didn't say the time is running up. So sorry.
Don't worry about it.
Yeah.
Sandita has helped us. Otherwise, I can interrupt. You're next year, so really, please. Well, it's a pleasure to introduce next experiencing sales point, former student of Jyoti.
Hopefully the
Chemtra will work. From IIT Mumbai, India. Probably we are looking forward to hear from you.
Yeah.
Please note you have 10 plus 5 minutes.
Yeah, hopefully.
Generous today.
Okay, thank you, Anas, for this kind introduction and also the invitation to this meeting, and thank you all for coming. And it has always been a pleasure to come for Jyoti's birthday related meetings. So this is in 2004, just after I submitted my thesis. You can see that we are cutting the cake, and Jyoti is shining there, and Sandeepta is here, Andrash is here, some of the former students are also. Was in 2018. Me and Yanas visited Jyoti at his house, and so that is like, So in a nutshell, I want to say that whatever little nucleic acid chemistry, what I am doing at Indian Institute of Technology, Bombay, is all I learned from Jyoti actually. So I did the postdoc mostly, that was mostly in biochemistry, but the chemistry, it was the solid background which I received was from his lab. So, and these are the type of things what we do at Bombay. So we have different projects. So here we are looking at some modification, especially bifunctional modifications, which can be incorporated into therapeutic nucleic acids. And also not only we synthesize these modifications, we also look at how these enzymes involved in this process. For example, in the case of siRNA, human organoid 2, and in the CRISPR-Cas, we are looking at the Cas9, how these enzymes are tolerating these modification with the help of long molecular dynamic simulations actually. So then we have a very active project on quadruplex. Today I'm not going to talk about that, where we synthesize and screen molecules which target quadruplex structures, which I'll be talking in the ANNA meeting. So we also try to discover some aptamers against proteins which are involved in antibiotic resistance. And today's topic is on DNA damage. Yeah, this is the problem, I think. So the figure is not coming. So it's okay. So the DNA damage, so DNA is always under attack, and if these damages are not taken care, so it can lead to mutations, and also that can lead to cancer and also cell death and aging. So these are the kind of damages caused by chemicals and also natural products. If you see here, this is the simple ethyl modification, which can be generated through the ethanol oxidation and reductive amination reaction at the guanine. So these are the molecules, the damages we have synthesized in the lab and studied for a process which I am going to explain in the next slide. And these are basically natural products actually, naturally occurring dyes, flavoring agents, all these kind of modifications, because they have been isolated from cells. So that's why I say it's a naturally occurring DNA damages. So if these kind of damages occur at the time of replication, so at the replication fork, so these normal polymerase cannot read through these damages. So the replicate polymerases stop at these damages. So then we have the system doesn't want to shut down. So there is a rescue mechanism which is in place. So the cells will recruit a polymerase called translesion polymerase, which is a low fidelity polymerase. I'll show you the structure. So which can add few nucleotide across this lesion, and then there is a polymerase switch mechanism happens, and then the normal replicative polymerase will come and continue this replication. This whole process is called translesion synthesis. It's a DNA damage tolerance pathway, it's not a repair pathway. So and if you look at the structure of this normal replicative polymerase, this is the normal replicative polymerase. You can see that it has got an exonuclease domain and all other necessary domains for polymerase action. But when you come to a TLS polymerase, one thing you can immediately notice that it has got a wider active site. So that is important for accommodating this adduct. And also the proofreading domain, which is present in the normal polymerase, is absent in the TLS polymerase. So, and instead of that, it has got a little finger domain which will help to accommodate this DNA damage in the active site. So these enzymes are present in all domains of life. So we have a set of TLS polymerases, then bacteria and yeast also have these enzymes. So today's topic, I am going to focus on one particular adduct caused by a natural product called safrole. So safrole is present in a lot of spices and also present in a leaf called a piper beetle. So piper beetle is a popular leaf which is used in Asia. People chew it, this piper beetle, and it has very high quantity of this safrole present. So and these safrole can cause these two type of adducts. So one is N2 safrole adduct, another is N6 safrole adduct. So, and they have been isolated, these adducts, from the oral tissue of the patients having cancer, and because of this International Association of International Agency for Research in Cancer called safrole as a class 2B carcinoma. So what we want to check is that can this adduct be mutagenic in humans? Is translation DNA synthesis across this adduct, whether it is error-free or error-prone? So, so to do this, we need these kind of components. So adduct-bearing DNAs, which are oligonucleotides, and TLS polymerases, and what we do the study by simple primer extension assays, and also to rationalize the findings, we use molecular modeling, and sometimes X-ray crystallography in collaboration with other groups. So how do we access these adducts? So I'm not going to the all steps, like key steps I'll mention you. We make an amine of this safrole moiety, and then what we take a protected bromo nucleoside and we do a Buckold-Hart coupling reaction. So that way we can install this adduct directly at the N2 position, and so then we can do the conventional protection chemistry and end up with a phosphoramidite building block. For the N6, we do a different type of chemistry. So here we take a N6 acylated adenosine, which is completely protected, and then do a Mitsunobu reaction, and then do the coupling chemistry. So then make the phosphoramidite. So, and after making these DNAs, so we simply check the melting temperature of the modified versus unmodified. You can see that they are more or less same. It doesn't decrease the melting temperature, and the adduct doesn't also affect the helicity of the DNA duplex. So then we come and check how these enzyme tolerance, we express and purify two enzymes from humans, recombinant enzyme. So the one is polymerase K and another is polymerase eta. So they are both are TLS polymerase. So we do a very careful assay called single nucleotide incorporation assay. So you have a template where the modification is placed here, and this is a FAM labeled primer, and then we individually add DNTPs to check whether this enzyme is able to read through this adduct or not, or bypass this adduct. So you can see that this enzyme is quite faithful in a way that it adds only DCTP. This is a G, modified G, and it adds only C across this adduct. So, and this is unmodified versus modified. So this is a normal G, and this is for the modified, safrole modified G. So, and same thing, we checked with the polymerase eta. Polymerase eta is a widely known TLS polymerase. It's even involved in bypassing this TT photodimer. Professor Thomas Carroll has done a lot of work on this polymerase eta. So, and so you can see that again, the efficiency is very low, but it is able to bypass. So this is known in literature that N2 adducts are not well bypassed by polymerase eta. So then, so some gels are missing. So then we have done a full length extension assay. So we added all the NTPs and check whether these enzymes can bypass, can make the full length product. So these enzymes are known to have low processivity. So basically they are meant for adding few nucleotides, then the next replicative polymerase can rescue these things. So you can see that polymerase eta is very less efficient. It is able to make some like less than 5% of the product, but polymerase kappa is able to make the full length product actually. So this is, that way kappa is more efficient to make the full length product compared to poly eta. So to look at how these enzymes work, so earlier we had reported a crystal structure of this polymerase kappa with the different N2DG adducts. We took that structure, so we replaced the adduct with a safrole adduct. So then we ran a long molecular dynamic simulation, 500 nanosecond MD simulation, and we looked at the active site, how this enzyme is able to accommodate this adduct in the active site. So there is to be a video, but it's nevertheless it's fine. So two things we have observed. This when it binds in the active site, there is a perfect Watson-Crick base pairing between the template, the modified site, and the incoming DNTP. So the Watson-Crick base pairing is not affected, and you can see that this bond is rotatable bond. So this torsional angle changes. So the adduct rotates, and it has a very nice interaction with amino acids. You can even see a kind of a CH pi interaction between the adduct and a phenylalanine residues, and there is a serine which is very critical. If you mutate the serine, the enzyme activity goes down. So it makes a kind of nice interaction with the adduct, and that way it stabilizes it, fit into the pocket without altering the active site of the enzymes. That's why the enzyme is able to bypass read through this adduct. So yeah, so to summarize, my time is also up. So to summarize, we have used a chemical biology approach to study this tolerance of these N2 adducts by these enzymes, TLS polymerases, and we have shown that H-pol kappa is more efficient in bypassing this adduct compared to pol-eta. So the conclusion here is that we were looking for mutations, whether they make mutations or not. We can confidently say that these two polymerases indeed can reduce, they don't make mutation, can reduce carcinogenic potential of safrole, but that doesn't tell you the story, complete story. So there is an enzyme called polymerase zeta. So that clone we don't have, so that zeta could be involved. They are known to make mistakes while reading through this adduct, and they may be involved, okay. So the N2 part is published, the N6 part is under revision. You can see that this is a recent JOC paper. With this paper we have dedicated to Jyoti on his 75th birthday actually. So yeah, so all this work is done by motivated graduate students. Most of the work I had shown on these adducts are done by Sitaram Bagle. So Sitaram is sitting here, and Priyanka Deshmukh, she has graduated and left. So, and all the modeling is done by these two students. Shruti is here, and Akhil was a master's student. So my collaborator for this project are Kiran. So my student goes to his lab to express and purify the enzymes, and his own students. And I thank the funding agency, government funding agency, and our institute, Indian Institute of Technology, Bombay is considered as Institute of Eminence. We got additional grant from the government, so we could procure a lot of equipments under this scheme actually. Thank you all for listening. So.
In a way, I feel sorry that you shortened this time so much. Presentation is open for discussion.
So I mean, regarding the pol 4,
yeah.
You have the serine 132, and then you have the adult, right?
Yeah, right.
Yeah. So what happens if you make the mutations there, site-specific mutation on one of the residue or one of the amino acids in that region? Will you see some differences?
Yeah, so the kinetics drops actually. The efficiency of bypass goes down actually. So, okay. So yeah, because that contacts are very important. So they are hydrogen bond, critical hydrogen bonds, because those residues help in stabilizing the adduct, stay in the active site. So there is hydrophobic plus hydrogen bonding interaction, and some stacking is involved. So if you alter this, the phenylalanine, if you mutate, the activity almost drops actually. Okay. Yeah. So we have shown this for a different adduct actually. So not for the same adduct, we have shown for a different adduct. This one. DINB, yeah, exactly. DINB is a ortholog of this one.
But is that essential? Like, remind me. Is that essential?
Essential for?
Essential for growth.
Yes, it is, because then the damages can accumulate, no?
Okay.
Yeah.
So that would be, then you will be able to select for mutants.
Yeah.
And use that as a...
Right. So, but these are human enzymes.
Yeah.
Okay.
Yeah. So you can go to E. coli.
Yeah. So the E. coli has pol 4 equivalent. Yeah. So.
Okay.
Yeah.
It is excellent paper.
Thank you.
Except how I turned this beautiful work into Jack's paper. How come that the whole thing into methyl derivative? And that way I prove the importance of stacking by safrole moiety vis-a-vis into methyl and the native. Polyenzymology, Jack's paper. But excellent idea.
Okay, thank you.
Only you have to do it.
Yeah. So.
But you have got everything else ready. Just one molecule finish.
Probably else on drink. But he doesn't drink, it's hard to talk to him. Some other comments? Are you all craving for coffee? So let's thank
Thank you.
We have a little bit of break. As you realize, you can have coffee on this floor, or you, if you like, you go downstairs. Next chair is empty. This time is 4:15.
Excuse me, so probably the time to have a seat. And we starting the session now. And Sandipata Acharya cannot make this to the meeting, so we started with Parag Acharya from University of Greenwich. Okay, the time is yours, please.
Good afternoon, everybody, and thank you very much. First of all, Yanis, for inviting in this conference, and of course, well, all the giants and forerunners in nucleic acid areas that you guys are doing. I'm a bit an outliner, yeah. So although, well, long back, I started career doing PhD with Jyoti at Uppsala, and started with a lot of work on nucleoside and nucleosides, but then through careers shifted across, and currently I'm working at Natural Resources Institute in University of Greenwich, where we are also heading the Medway Food Innovation Center. So I'll come to that, but before that, yeah, I mean, I think just to be talking about that, you know, the learning that I have had with Jyoti. One thing I always remember that Jyoti used to say, that, you know, when you run for 100-meter sprint, you have to remember which direction you are running, yeah? And if you run on the backside, nobody will give you a medal. So I think, I mean, medal consists in various things, you know, it can be prize in different terms, but at least that's a very good suggestion. I always try to keep track in my life. So thank you, Jyoti, for introducing me to the whole world of science. Now, I think at that point, just going to the part. So what I would like to do is give you a brief introduction about the institutes I'm working, and also some of the work that we do. And then I will jump into this whole running, because I was thinking like, okay, how to relate nucleic acids, you know, still to the food chemistry, food technology we are doing. So umami is a very nice case. I'll come to that. But before, so I'm actually have a few hats. So I'm heading this Medway Food Innovation Center, which I've established in 2022, just after the COVID at University of Greenwich. But also very recently, we got a big grant of around 30 million from Jeff Bezos with Imperial and few others, where I'm also co-director of the plant pillar platforms. And then around also the research group that I'm representing, so heading, which is constituted around 12 people, so 12.5 in FTE-wise. But yeah, and then of course they are doing a lot of different research and other things. So in my talk, I will go through, like I said, that a little bit around the Medway Food Innovation Center, and then a brief overview about nucleic acid and food innovation, and then jump into the umami. So in Natural Resources Institute, there are several centers we have, and out of that, one of the centers is Medway Food Innovation Center, which I'm heading. And in that center, we working on food technology, food innovation, food chemistry, different areas. But there are other centers who are actually working at the interface of science, social science, natural science, food innovation, food technology, but also at the intersection of social science, economics, and other places. So what we have at Medway Food Innovation Center, we have a product development kitchen or laboratory, you may call it. It's a food grade facilities where you can actually develop a lot of formulations, products, and things. We have a food processing and analysis lab. Sorry. So we have food processing and analysis lab where we have different equipments right from extraction to processing, drying, and various other things. Also, at the School of Science, which we have a lab on food algae biotechnology. So there you have a facilities of producing around 1,000 liters, 1,000 to 1,500 liters of algae and different microalgae and seaweeds, etc. Also, what we have established in 2022 with the Food Innovation Center is the Food Accelerator Program. So the idea is that it's not only doing science, but also translating the science to application by engaging businesses. And what we have so far supported in 2 years, around 100 plus businesses through our sprint program on Accelerator, and that across the business, model development, financial models to pitching, practice them with the pitching for the VCs and other things, and also that facilitated using these facilities. We have done several new product development in terms of vegan cheese and plant-based milk and various other things. So I think that constitutes a very nice part of students. So we are also doing some MSc program on food innovation and food quality management, but then across the research and the translation of research. So with that, we also have some core research program which my research group is working on. So we have various programs across basically alternative protein-based food. So the question is that all the animal agriculture having a huge amount of impact in terms of the natural resources. And if we have in 2050, if you want to feed the population with same amount of production, it will not work. So the question is how we change our food system, which is totally, per se broken in terms of the sustainability part, and how we can change that. One of the part where we are concentrating on is how to replace the animal protein with alternative source of protein that come from plants, that come from microbes, and we are also having some collaboration with Tufts University and others on working with cultivated meat or hybrid proteins. So with that, we are, mainly on the algae and plant side, that's a core work that we are doing, but like I said, that there are various other alternative protein sources that we are exploring together. So, question is, what is the relationship in terms of nucleic acids and food innovation? So, of course, there are some connections, in terms of the crop production. There are some, GMO is one part, but there, as we say, in food, consumers are at the center stage. If you don't like food, you will not buy it. There is no point to manufacture food. So and that is the part where actually food is differentiating from life science and pharmaceuticals applications. So it's a commodity product, yeah. And that part we say, well, there are also food safety where you use PCR-based technology for the pathogen detections and other things. So there are plenty of things where actually nucleic acids and engineering microbes for producing certain ingredient sources, things like that. But the area where today I would like to concentrate or focus on is about the umami or taste enhancement. And of course, all these applications actually constitutes the whole Sustainable Development Goal, SDG goal from UN in terms of emission, going down with emission, food waste, how we actually reduce the wastage, green manufacturing, and also nutrition and other areas. So the part that is about the taste enhancement, and there are two parts, which is, one is umami and there is another one is the kokumi. And these are the two very interesting aspects of the food formulation that we are currently slowly moving in. And there is a reason for that, because of course when you try to move away from meat to a meat analogs, there are people who are flexitarian, who loves meat, but in order to be sustainable, they want something alternative. And how you can actually, deliver a meaty aroma, meaty taste in there without having meat. And that's a huge challenge in terms of taste and flavor aspects. So just giving you a brief about the flavor and sensory properties in terms of, like, as you all know, most probably from your own experience, if you get a nice aroma, if you get a nice taste, you like the food, yeah? You love the food, and that is what you buy, most probably. And of course, nutrition is another part, but there are several consumer studies have shown that actually taste that drives the repeat purchase of any food products. And in that aspects, and in sensory properties is very key. And what we need to do is basically understanding these sensory properties and try to relate with the formulation and food processing. That is what our goal is. So what is the mechanism? So the mechanism is basically when we eat, yeah. So there are the whole in the food products we have the volatiles, which gives you the aroma, and there are non-volatiles like amino acids, organic acids, which give the taste. Now, taste, we get sensation via our tongue, and the volatile compounds goes to your nasal olfaction. Now, with that, we are trying to understand, but also when you, so when you go for the taste, so that is also another part where you actually get a sensory of intersection of aroma and taste. In terms of expertise, there are different expertise, and for example, the rheology, mouthfeel, these are part of food physics, whereas the understanding the aroma, measuring the aroma is around the chemistry, and then receptor biology, how these molecules actually binds to the receptors, that is where the biology comes into the picture. So without much, this is what we have set up in our lab. So actually, this is the GC top where you actually doing the flavor profiling. And then, of course, you can also trying to understand the key flavor because, say, for example, in tomato, there are 400 volatile compounds. Out of these 400, there are only 23 key flavor attributors, volatiles which are key attributors. And out of that, there are only 8 which actually covers almost 95% of the flavor. So in order to actually profile the 400 volatiles and come down to this 8 key, you do a GC olfactory. So somebody smell it, and then she says, well, this is the aroma I'm smelling, and then the mass spectrometry actually identifying the compounds. And then, of course, you do here with the rheology mouthfeel, and then this is the LCMS where you do the test analysis, like test profile. And then we also recently bought this is called electronic tongue. So what it does is a company from Incent Technologies. So it is actually making some electrodes, which is basically mimicking the tongue, the layer of a tongue in terms of membranes. And it can actually do the flavor scoring, taste scoring in very, very correctly without even having a very costly and human-dependent sensory profile. So you can actually sort of partly replace this costly sensory profiling or human studies with this, particularly this is very key on some of the products which are not in the market unregulated, like cultivated meat. Yeah, so you cannot do a test analysis on that, but you can do without the human participation via electronic tongue. So in terms of savory, savoriness, umami, there are the compound glutamate is the major compound which attributing on the umami part. And then, of course, aspartate is another, which is much less. But, this is actually the glutamate, which is the thing. Now, this research started when actually IDEA, 1908, first put a patent on this umami because we have, that time onwards, we have 4 sense, the taste, which is salt, sour, sour, and then you have the bitter and sweet. These are the 4. And then it came that from while working on nori, he found that this taste, this 5th taste, is something somewhat different. And that's where the umami part came. However, it took almost 100 years of research to understand the real significance of umami. And in 1980, it was officially come as a 5th taste. And then around 2023, there was a Nature paper where they first found that actually this also facilitated the kokumi. So in order to have this in our products, basically what you have is MSG, And then you have these are the clean label, yeah, which is like MSG containing, but from natural sources. And then the point is why these are clean label, but these is higher price. So the whole challenge in the market is how you can derive a natural umami extract which has the same cost of MSG. So with that, that is where part of role of, nucleotide comes. So basically, in a food pairing, you can see, of course, this is the empirical knowledge that we gain. So if you combine certain food, actually your umami sensation increases. And then what we did, this is a study done before, but we did it with Etang. So if you have a chicken soup with MSG, yeah, you have some umami scoring, but that actually increases with the addition of nucleotides, and particularly guanidine and inosine also, but these are the two which actually creates a huge impact on the umami enhancement. And then just give you a brief about the curcumi. So curcumi itself is not a flavor compound. Yeah, if you take just curcumi as these tripeptides, this has no taste, no flavor, nothing. But if you put it together with umami, that actually increase the enhancement of umami. So if you take a chicken soup, same chicken soup, add these tripeptides, then you can see, clearly you can see there's a umami enhancement. And then this is another one is the fat replacement, because if you have fat is not good for certain fats, not good for health. So if you take a low-fat peanut butter, add this curcumi substance, you not only increase you can see there is a clear increase in the fattiness and thickness, because fat sensation in the mouthfeel is the thickness that you sense, and that you enormously increase. So basically, if you want to formulate some natural low-fat products, you can actually create that with the same taste parameters having curcumi molecules. So with that, I would like to end, but before that, I just want it's a bit of advertisement. So we're looking for a postdoc who in the food rheology at our, in the collaboration with 3 other partners. And thank you for your listening to presentation.
I want to save some time for your Okay. All right. So let's thank you. Thank you again. Yes. Next speaker is Ali Bazin. Actually, I got here in the last 5 years. Yes. Something like that.
Okay,
thank
thanks.
you. Having you.
This one is okay. So first, I thank the organizer for giving me the opportunity to speak, and I will present some work on opium label nucleotides. Yeah. So I did my PhD with Jyoti, that was in '87, and then I started to work in industry. First in a Robert Theul lab doing some oligonucleotides. Then I moved to another part of SysBio, and then I work always in SysBio all my career. So I have been doing some CMP labeling, which was used for quantification kit of CMP. Then I worked, I will see later on opium cryptate label, oligo and UTP. Then I work also on inositol 1-phosphate and labeling of inositol 1-phosphate for doing also some quantification kit. And then I have been working later on a detection kit on protein implicated in mitophagy and apoptosis like HMGB1 and phosphoserine ubiquitin. So I have to thank some people here. So first, Annie Grouillet, who was one of Jyoti collaborator, and she sent me, first I have to thank her because she sent me to Jyoti's lab, and then also to Jyoti, I have to thank Jyoti who welcomed me in Uppsala for a very exciting 4 years PhD and fruitful discussion. Here is Jyoti in 1986, 86 with his new baby, very proud of it. And when I remember this time, one molecule which I have been working is the labeling, the methylation of demethylryosine to ryosine, and that was very, how to say, puzzling at that time, because using methyl iodide or diazomethane, it's always N9 methylation. But it was reported that using diazomethane, some people get some ryosine, but it didn't work in our hand. And then we realized, and Jyoti asked me to try to block somehow this nitrogen with some metal salt, and I try iron, copper, zinc, alumina, and so on. And we realized that using zinc iodide together with diazomethane, we got almost exclusively the ryosine. And in fact, we realized at that time that it was due to the formation of a Simon-Smith reagent, which was made in situ. And that was a good recall of my PhD work. I would like here also to remind one people I have been working with Professor Théoul in Grenoble, and I wanted to remind his pioneering work using phenoxyacetyl group for the protection of purine bases and acetyl group for cytosine during oligonucleotide synthesis, and also introduction of phenoxyacetylenediol as escaping reagent. And some 30 years later, these ultramilde potentiating groups are still used, and here is extracted from the Glenn Research Catalog this year. Phenoxyacetyl A is still in use, acetyl C still, and isopropyl phenoxyacetyl G as it was used earlier this year. In this session, it was discussed. Using this mild deprotection, we could do the synthesis of a natural tRNA, complete synthesis of natural tRNA with its minor bases, and using diazouracil and also pseudouridine. And we could, using this mild deprotection approach, synthesize the complete tRNA, and we could also show that the biological activity of the synthetic RNA was almost similar to the natural tRNA. So that was to show the power of the protocol. And now I will move to another field, and I like very much this structure because it kind of link between my work in Jyoti's lab on nucleoside chemistry and the work on europium cryptate that I have been doing for many years afterwards. And this was done by, was synthesized during Beatrice Alpha PhD work in the Jean-Marie Lenz laboratory, and it's still in use in SysBio. I will shortly explain how works the time resolve protocol using HTRF, which is called HTRF, and which is using the cryptate, europium cryptate here. So europium cryptate is characterized when it's excited by UV light. It's characterized by almost a single line at 620 nanometer with a very long lifetime, so almost 1 millisecond. And compared to other classical fluorophore, which are excited. Once they are excited, they have a very short fluorescence lifetime, which is in the nanosecond range. So, for example, APC, allophycocyanin, give a fluorescence light, which is at 65 nanometer, and there is short fluorescence. But once those two molecules are in close proximity, there is possible of a fluorescence resonance transfer between them, and during this process, there is the APC now is emitting with a very long lifetime emission, up to 500 microseconds at its nominal wavelength. So if you can extract this signal, it's a specific signal, and you can use this protocol even if complex medium and medium where there are other fluorophore. I will show that just after. Yes, in using this time resolved fluorescence, you excited all the medium, and all the short life fluorescent fluorophore, there will be extinguished, and then you start to measure the fluorescence of your probe, and then you get very specific signal. So this HTRF protocol over almost 30 years became the gold standard in drug screening, and it has been applied to many pharmacology protocol test, and as GPCR, kinase, receptor ligand, protein-protein interaction, and also cell-based assay for cytokine interleukin quantification. And also it has been used, we will see that now, on oligonucleotide and RNA DNA business, and also on DNA protein interaction. So HTRF is best to probe interaction in complex mediums such as cell lysate with good specificity. And the cryptid business nowadays is about to give job to about 107 people, and with a turnover per year of 45 million euros. Shortly, once we synthesize the labeled cryptid labeled DUTP, we can detect through that using a biotinylated primer, and polymerase will be extension, and then we incorporate the labeled DUTP moiety. Using streptavidin linked to APC, we can then observe a threat. Once you excited the europium, it will transfer one part of its energy to APC, which will in turn emit a long life emission at 65, which is specific of this interaction. We apply that for homogeneous time resolved fluorescence detection of telomerase activity. So using here biotinylated telomerase substrate primer and a reverse primer. We're adding a KDUTP, the labeled DUTP, DNTP cell extract, which bring the telomerase activity, and Taq polymerase. It will add the telomere repeat. And doing that, it will incorporate DU cryptate labeled DU units. And again, if you add streptavidin APC conjugate, there will be threat between cryptate and APC, and apparition of a long life emission, which is specific of this interaction. And just to show that increasing the number of cells in the lysates, you will increase the telomerase activity, and you will get a proportional signal. A second application is using a cryptide label probe to make mini sequencing of codon 248 in the P53 tumor suppressor gene. So just want to know which is the next base. Is it a G, so it's a wild type, or is it a A, it's a G2A mutation? So using DNTPs and biatylated DNTPs, you can get, if you have a A, you will get into incorporation of T, and then you will, again, you can have a threat between cryptate and the acceptor, and then you will get specific signal with long life signal. Here is genotyping of cancer patient with colorectal cancer, and then, oops, you get here the figure when it's heterozygous mutation, then you get A of so incorporation of T and C in front of G, and here is the one with wild type first base, and you can see that it's very specific. There is almost very little residual signal on this one, so it's very specific. So I thank you for your attention. I thank again the organizer and to provide such a nice interaction. And as we said in CISBio, interaction is everything in biology and in society. And Jyoti was very good for interaction and bringing people together. That was the second international conference in August 1985 in Uppsala.
So, thank you very much. Okay, fantastic talk. I think I remember I used video.
No question.
Yeah?
No question.
Okay. So, Yanis want to have a question?
I want to help.
Anyone have a question?
Hardy has a beautiful idea, but how the M3 installation takes?
No, actually, I agree with the partner, but that's very efficient for the protein-protein interaction, rather than the fluorescence and kind of control. I didn't know it was really fun. All right, so let's go for the next. The next speaker is Ching, and he is actually in charge of RNA therapy part division in Princeton Biopharmaceutical Company, and actually that company is among the top 20 in the biopharmaceutical industry. So the time, I think he joined like 2007 or 2012. Yes, please.
Sorry, I forgot. Okay. First of all, thank you. Thank you a lot, and I appreciate a lot for the Yana can invite me to attend the great meetings for the celebration of Jyoti's 75th birthday. So I'm really very thankful of Jyoti, appreciate Jyoti that take me from to this area, from a Navy boy in the chemistry, in the life, also in the science, to this platform to know the chemistry of the nucleic acid. So really very thank you. So after graduation, 2012, also I go to the industrial area directly through several companies. Now I'm in the Shanghai Junshi Bioscience Corporation. So what I did in my department is focus on the siRNA development and also the drug manufacturers and process validation and etc. So in this part, because time is limited, I will mainly focus on the first two parts, design and development of siRNA drugs,
and also the chemistry, manufacturing, and control of the siRNA-based drugs. Okay. So this is a quick introduction of our company. So our company is mainly on the cancer and the chromatobolic disease. So we have the first PD-1 antibody, which is launched in China in 2016 and also approved by the FDA in 2022 for the NPC. So it's the first antibody which is overseas into America. So we have two plants in China. One is in Suzhou and another one is in the Shanghai, Lingang. And we also have two R&D centers in America. One is in San Francisco and another in the Maryland. So our headquarters is in Shanghai. So what we did is for this different kind of drugs, modulations in the cancer disease, including ADC, or called a dual antibody ADC, and also include the siRNA, mRNA, and also antibodies with different targets. So I just started with my focus, the design and the development of siRNA drugs. So yes, before starting, we have to say, I have showed what I learned in Jyoti's lab. So which is the fundamentals for the nucleic acid therapies. As Sugimoto said, the hydrogen bonding, the base stacking is the, oh, there's some picture lost. Some pictures cannot find it. It's a basic of the nucleic acid therapy, also including the Watson-Crick and the Hoogstin and the G conjugates. It's very interesting. Also in our company now we have one immune modulator which is use CPG. They have the 4 continuous G in the 5', 3' terminals, which have this G contrast and give the multipolymer. So it's a very interesting structure. It's already used in the pharmaceutical development. There's a lot of picture cannot show. Maybe you can use my computer. So this is genetic central dogma of the life. So it's very easy. Most people know it. I just want to show here is for the nucleic acid therapies can be use SO, use siRNAs, use nucleic acid aptamers, use SARs. So which is treated with yes, this one. So we start from here. So it's the central dogma of the life. You see that our nucleic acid therapy can be used in the different pathway of the DNA, RNA translation pathways. So you can use SO to target with pre-mRNAs, also target with mRNAs. You can also use siRNA to target with mRNAs in the cytosome. You can also use SARs to target the DNA to upregulate the genes. We can also use nucleic acid aptamers to target the protein as a drug also. So it's just a quick introduction.
Yeah, just use an arrow.
So now we give you a comparison of this siRNA versus SOs. So some people, they working on the SO area with the, like Ionis, they use this antisense oligonucleotide to treat the disease. But nowadays, most people would like to use siRNA to treat the disease, especially downregulate the MIs of genes. But on my point of view, these both modalities have their own advantage. For siRNA, for the downregulation of the genes, they have more good IC50 activities, normally from picomole, PM. But for the SOs, normally they only have micromole to nanomole. That's why we found that for the SOs, they can injections at maximum two months projection. But for the SIs, we can have a duration as long as 1 year. This is because of the activity or inhibition potency of the SIs. But for the SOs, they have one advantage I found recently is they are more easier to pass through the cells because the SOs, they have one single strand. The base of them is outside of the strand. So they're more like catalytic. They're easy to touch with the cell membranes. So that's why the first generation or second generation of the SOs, they can very easy to center the membrane of the cell without any ligations. But for the siRNA, because the duplex, they have a more ionic part charge in this backbone. Therefore, it's very hard for them to touch with the surface of the cell membrane. So they need a ligand. They need GalNAc, they need peptides, they need antibodies, they need all of these kind of delivery system to enter these bodies. So nowadays, if you're thinking about hepatic delivery, we use siRNA plus GalNAc or LNPs. But if you want to think that we want to deliver our molecules extrahepatic, so we have to thinking about SOs. Because SOs have this kind of capabilities to into these tissues without ligands or more easier to enter the cells. So what's the main challenge on drug ligases of this nucleic acid? Actually, people when thinking about nucleic acid as a therapy, it must be a very good dream for the drug futures because it can theoretically target any gene of the human bodies. But problem is, our nucleic acid not like small molecules, not like antibodies. For us, it's very hard to enter these biobarriers of the human beings. So we have the charge, lot of charge in the nucleic acid. We have to solve a lot of problems like the nucleic acid stability, how to prevent from this different lot of enzymes in the blood circulations, also in the cells. Also, we need a drug delivery system to let them selectively, accurately into these tissues of the human beings. These very important things. Also, of targets, in fact, really exists because you will see AS versus SS selections is very important of target, in fact. Another is microRNA-like pathways interference, which means that in the 3' UTC, you will find the C region of our molecules, MIs, will be targeted with the genes. So these kind of things can be avoided by the very accurate or very good tuning design of our chemistries. Also, the immunogenesis of our molecules. It's also a big problem, but now already solved. We will see how to solve it later. First step, when we want to say siRNA design, we will start with the sequence rational design. In the old days, in the previously, like Analam, I know what they do. Because for normally mRNA, they have 4,000 to 5,000 BPs. So it's very easy. You just think the full library of these siRNAs, also 4,000 to 5,000 of siRNAs, then test them in vitro for this kind of different cell test tools. But nowadays we have very good the calculator or the human computers. You can see they have a lot of scorings. So we use these basic algorithms trying to shorten the scope of the siRNAs. But I know just the key point is that just make the thermal instabilities. Means like you will make the 5' of this AS less thermal stability. That means like AU more. And in the 3' of the AS, GCG more. That like the AS will be preferentially dissociate. Then we will target with the risk proteins first. This makes the AS versus SS. This is the key point of this algorithms. Now the second part is trying to make reasonable delivery systems. Old days, or not say old days, previously the first drug which is launched in the market, SI drug launched in market is patisserin, which is developed by the NLM. They use the AMP to deliver this SI into the hepatic. But AMP has this toxic problem because still is a big molecule. So now they try to research on this GANAC system. Because how can we find this system? It's really a serendipity. Because the ASGPR receptor is you see in these human beings, you have very high express in the hepatocyte, 0.5 to 1 million copies per cell, very high rate of uptake. Also, it's very easy to synthesis. You see, normally tri molecules, sugar ring is the best one. Maybe more than 4 is also good. But mono or bi sugar is not very good. So nowadays, most people in this area, they use GANAC to deliver SI into the liver system, and it's now already very successful, very successful. Then the next part is what I want to say mainly is what I learned from Jyoti's lab, the chemical modification. Chemical modification is very, very, very important in the SO and SI designs. But actually, which is used in the clinical trial is not so much. We found for the backbone modification, normally people like to use phosphate. But nowadays they have this another modification called extended nucleic acid, which is also very good in the 3' exonuclease protection. But now they can use extrahepatic SI designs. Also, one thing we call the vinyl phosphate. This molecule is also very good because for the SI when you into the body, they first will be use the 5-phosphate kinase to activate it. But this one he just notes that you have already the phosphate on and also have the vinyl group which is nucleus protective. So this one nowadays used in the brain injections of the SRAs because in the extrahepatic inhibition of this of the MRAs, this 5' EVP is very important. But for the normal SI, we normally use 2'-fluorine and 2'-OME as the modification. Only one more. Oh, okay. And also use GNA as a seed region of target, as like that. This is talking about the chemistry part. We have thinking about the combination of the chemistry. In which position the 2'-fluorine and 2'-OME combination gives the best duration of this SRAs. Here is in our lab, in our company's work, we found that the sequence will give you the, how can I say, the span of the knockdown. I mean, this depends on the sequence. But for the duration of the drug, the chemical modification is very important. So it means you have to use proper combination of the chemical modification, especially in the sense strand to increase the duration of the SRAs. Okay. This is just SRA secretion strategies and the normal strategies. Most people they use it first in silico rational design and MI knockdown, and then sequence modification, and then lead validation. We will through this in vivo and in vitro models. And this is the ADME pathway of the SRAs. This is the PK metabolism of the GANAC SRAs. We found that this is very important. The PK and PD relationship of GANAC SRA is different from small molecules. you will find that this in the monkey plasm, normally in the 2 and 4 hours when you injection these siRNAs in the blood circulation, they will disappear, which means it's internalized by the hepatic tissues. So that is more correlated with this risk concentration of siRNAs, which is the protein reduction is very correlated with this risk concentration of siRNA, not with this blood serum concentrations. This is just people. Now I have 21 ASO siRNA aptamers launched, approved by the FDA. A lot of people talk about it. This is a representative siRNA deals. Nowadays, siRNA can be used into not in the rare disease, now already extended to the hypertension, diabetes, and also the lipid, the hypercholesterolemia. How many minutes left? No minutes.
You do not finish that last scene.
Oh, yes.
See, we'll have dinner.
Okay. Just give me 5 minutes.
No.
Okay.
Please.
Okay.
You quickly go to the point. Well, actually, I don't want to say the CMC. I want to say the actual medical delivery. So that's the part. Do you have it?
No. It's just CMC part. Okay. Just keep.
Go quick.
This is a solid phase synthesis with a 3' GalNAc as a single strand RNA. Normally, if you want to synthesize this one, we will use this GalNAc, which coupled with the solid phase as a starting materials, and then make this synthesis, which is similar with the phosphoramidite chemistry, and just a bit different with parameters. That's okay. I think it's too much.
No, it's not too much. It's just time is too short.
This is about the raw material, the starting material, phosphoramidite impurities. Normally, I was thinking about this pharmaceutical manufacture of the siRNAs. We have to first thing thinking about phosphoramidite impurities. We have 3 kind of impurities: non-reactive, non-critical, reactive but non-critical, and reactive and critical. Normally, we have to focus on these reactive and critical impurities, which means it can be reactive during the solid phase synthesis. Other 2 impurities just will be washed by the acetyltonitrile. That means that P3 phosphoramidite will appear in the different part of the sugar ring. This is just an example. This is a typical phosphoramidite specification, which if you want to develop the drugs, you have these specifications. Very pure, 99%. This is the oligonucleotide specification also. This is the oligopilot scale equipment line. So normally we use the equipment from ACTA if you want to make the 102 kilograms siRNA. This is just quality control for the GMP, oligo GMP campaigns. This example of our triphosphamide RNA duplex synthesis. This we are finished with several hundred grams of compound scale with a purity of one sentence is 45, another strand is 93 to 94. In Wuxi Aptar, my previous company, we already founded a GMP commercial scale equipment. You see we normally use DCS control system, this like that. This we can one patch can create around 2 to 3 kilograms of the oligo API compound. Okay, that's finished. Okay. Thank you.
So thank you, okay? Yeah. So next time I'll give you more time and I can talk a deep.
Oh, okay. Good.
And now, please, bring your own computer because we don't want to mess up. So the next speaker is Chuanzhen Zhou. Actually, I forgot when did you start with Jyoti's lab? It's 2004. Huh?
2004 to 2010.
2004, right? 2004 joined the Jyoti.
The time is yours. Keep your time, all right?
Okay, so thank you very much, okay, Yanas, to organize the symposium and provide opportunity for us to get together and celebrate the 75th birthday for Professor Jyoti Chattopadhyaya. So I pursued my PhD with Jyoti from 2004-2010. Actually, before I had my master's degree with Professor Xi and in Nucleic University. So Jyoti is Jyoti and me to the field of nuclear acid chemistry. And today we celebrate the birthday of Jyoti, and also this moment and prompt me to recall the period I spent with Jyoti in Uppsala. So frankly speaking, the 6 years spent with Jyoti in Uppsala are the most important periods in my life. So I come to Sweden and from the Chinese village, okay, and witness a completely different, okay, Western world, okay. So I got married and had my daughter during the period, and carried out the cutting-edge research and published 18 papers. So I grew from a shy guy, okay, right? So this photo taken in October 23rd, so exactly 20 years ago, okay? So he's a shy boy, okay? So after that, in 2010, okay, I grew up with a confident scientist, okay? So thank you, okay, Jyoti. So on our side, I think Jyoti deeply influenced my research interest and taste. Okay, so at present, my lab is still focused on the nucleic acid chemistry. So, and several projects are still related to my research experience in Jyoti lab. So today, I only have several minutes. I just briefly give some examples. Okay. So the first project I carried out in Jyoti lab. Okay, so I collaborated with scientists, right? So at that time, Jyoti proposed the depolation of the guanine, okay, will modulate the electrical character of the phosphate. So that's when we'll modulate the stability of RNA, right? So Jyoti asked me to synthesize the methylated, okay, the guanine and test the kinetics of the ion cleavage and the basic condition, right? So, okay, I sense the building block and incorporate the ion strand and measure the kinetics of the ion strand cleavage, okay? Jyoti is correct, okay, so this, the electronic effect of the nuclear base, okay, modulates the kinetics of the transfer isomerization of the RNA. So after that, my thesis, okay, the work actually focused on synthesize the conformation constrained, okay, nucleotides for therapeutics, okay. So after that, I think about the question, okay. So the ribose conformation could be a more important effect to modulate the 2' hydroxy involved transition reaction in RNA, right? So everybody knows the mechanism, right? So the 2' hydroxy attack the phosphate to give a trichlor and bipyramidal transition state, right? Pseudo rotation, okay, step is involved in this process, right? So actually, the intermediate is a bicyclic structure. So that means this transit can occur from the north conformation transit state or south state bicyclic transit state, right? So the barrier should be totally different. So that means I think about the ribose conformation could be more important than the nuclear base. So after in 2014, I come back from US to Nankai and set up my own lab. At that time, I found in Professor Xi's lab, he synthesized this 4' methyl modified nucleotides for therapeutics. And the students show me the map, the structure. I found the coupling constant of 2' and 1' proton is 8 Earths. Okay, so that means this methyl modification constrains the nucleotide in south conformation. So I collaborate with Yanas and we proved, okay, still, if we incorporate this modification to the strand of the RNA, still constrained in source conformation. So that means this model is good idea substrate to study the ribose conformation effect, right? So also since it's another one, constraint replicate, right? So we incorporate to RNA strand where we do the catalytic, the alkaline catalyze RNA cleavage. So we did find, okay, so the source constraint cleavage is 100 times faster than the source constraint. Okay, so the native one is just in between. Okay, and we also do the calculation. So we found, okay, so the ribose actually prefer the loss conformation, right? So, but it transfer to the source conformation, and then the cleavage occurs through the source trans state, and it's kinetically more favorable. Okay, so finally we published this paper in GX with Professor Xi and Yanas. Okay, but I have to mention, okay, during the review of the paper, okay, the review number 2 gave a very good suggestion. Okay, he said an serious problem in this matter is that the authors make a serious overstatement in this matter. So the statement is like this, okay. Unfortunately, the effect of the ribose conformation on RNA internal transfer replication has not yet been addressed. He said, okay, so this is not true, and gave a reference. The reference, okay, is Professor Jyoti Charbaya published in 1994. Okay, he studied the self-kinetics of the RNA self-splicing. Okay, he already found the ribose, okay, can modulate this kinetics. Okay, so that means after, okay, probably 20 years, we just, okay, to experiment and prove, okay, give additional proof, yes, the duality is correct. Okay. So after that, I realized, okay, this 4' modification actually is a very important modification. Okay, this modification can constrain the ribose, right? So it's more advantage than our cyclic circles, right? So we synthesize a series of the nucleic with 4' modification. So generally, we found if we introduce electrodonating group, and the group can constrain the riboside, the ribose in source conformation, but if the reaction with your group and constrain the ribose in loss conformation, okay, so that's very interesting. So based on this modification, so we find many applications. For example, we can be used as therapeutics, and also can study the structure based on floral MR, and also all of this collaborate with Yalas, and also we use them to study the mechanism of DNA damage and repair, something like that. Okay, so we still benefit from duality's experience. Okay. So another project I carry out in Joyce's lab is we synthesize RNA based on a TAM protein group. Okay, so actually in 2010, and Chinese government founded the key project focused on the synthesis biology. So because I have experience in this lab, so I get funded to synthesize the long DNA, also the genome DNA. So now we are also develop method for chemical synthesis, also the non-template-based enzymatic synthesis of the long DNA for genome DNA. Okay. So take together. Okay. So after 15 years, I leave from Georgia lab. I still okay. I benefit a lot from my experience in US lab. Okay. So I think it's not only me. Okay. I think probably the one of the nearly 100 graduate students and undergraduate, okay, just like the need of the Georgie's academic and the tree, okay. We have always get the nutrition ideas and support from him and thrive. So, okay. Okay, so thank you very much, Georgie. So we will wish you, okay, good health and have a long life. So thank you all. Yeah.
Okay, so let's don't take the question, okay?
Okay, okay.
So we'll take it later. So we leave the final speech with Johnny. So he's out of the pocket of the day. And you got 45 minutes. You ready?
Is it my turn?
Yeah. And Johnny, Jana told me gave you 30 minutes, so I'll give you 45.
I only have one word to say. Thank you. Look, nothing is more satisfying. Nothing in the world is more satisfying for a teacher. When your students finally tell you, hey Jody, that's the way to go. That's a pleasure.
I will have to interrupt this talk. We need a USB to HDMI adapter. So any Apple guys, your laptop is too thin.
I am the adapter.
Oh, yeah. Oh, okay.
Any of you Mac guys?
I don't have a USB.
Rakesh.
Good heavens, Rakesh. You saved it. So, what I was trying to say, let me get to the point. It's always that in our business. I mean, you produce students, and they will do a role. Impart to students what we know, what we understand about the problem, and then he comes to his feedback. And that is the introduction that makes the whole thing so interesting. And I am very proud to say I have been having that all the time, including the reviewer. Choose before there that comes out, that comes out there. That's very good, interesting, Josh Johnson. Now, what's incremental science? The incremental science, that is really science. We go step by step, that we have many giants somewhere. The Apple knowledge. And we say, hey, thank you for teaching me this. So we have that. Just keep it going. Yeah, sure. That's the name of the game.
Push this button, or you want me to push it? You want to like space?
Yeah, that's it.
Okay.
So,
You see, it's better I can do it.
Okay.
You just say let's.
One before.
One before is the first one.
Yeah. So, find alternative strategy, that is science. Learn from mistakes and move on. I'm a good example of that. So many mistakes, but every mistake has been there to teach me things, and don't do it again. Maybe you can do that or this, and you learn from the mistake. More than your successes. The mistake teaches you much more than your success. But don't be excited by your success. Look where things could have gone better. So that's my lesson for life. Always I've kept telling myself all along, don't make the same mistake twice. Next one. So this is one of my heroes, Louis Pasteur. His birthday was last year. He taught us the art of experimentation. He's the first philosopher of science who transcended to experimenters 200 years ago. And you look at a long list of things he has done. The medical microbiology, most probably he's the discoverer of pathogens, science, technology, medicine, pioneered the molecular asymmetric hierarchy, molecular dynamics. The whole world is running on that, asymmetry. Even the particles, some fundamental particles have that preference one over the other. So he's the one who started, and that of course, went on with the wine industry, tartaric acid, and all those things. He saved the beer industry, wine industry of France, and the world, and developed vaccines against the anthrax virus. So I think it's about, I'm 75, so I'm here out to say thanks to people. And he's one of those. So this is basically the same thing. He's trying to say you need the pH control of the wine, otherwise it will catch. Such a simple thing that we do to that. I was telling Harvey, I was in Avenue, and Susan and I were driving through this vineyard, and I saw this beautiful grapes for which one? Fortunate people. But very well, you see that's what the brain does, you know, as you grow older. The right word doesn't come. And Nicholas Susan stop it. This is wine. The wine isn't there, but the wine is precursor. The grapes are there. So it's right there. It's just power. And then I figured it out. The way these vineyards actually harvest their wines depends on the pH of the juice from the grapes. And that we heard also yesterday in this wine industry place. He was talking to him. He was telling me, you know, between 3.4 and 3.45 has to be done that day. Rain or sun, you go get that. So it is as critical as that, the pH. Okay. Go to the next one. Yeah. And then, of course, my friend, colleague, and teacher, Colin Rees. His reasonings were very simple. You've got a molecule, you've got a heterocycle, you have got a hydroxyl, you have an amino group, and you want to understand what is the potential of that group. He simply said, that chemical reactivity will figure it out by looking at the pK. He's a master of pK. He could say the pK of that common variance, common acids, you know, the tip of his tongue. So he not only taught me that, he taught me some other things. He taught me don't run your own in the wrong direction that somebody said here. How true is that? Absolutely true. You know, you can go a step backwards, but you must watch out how you're going. Because running in the wrong direction doesn't make sense. It's time to reach it. And he taught me that. Go back. That was the wrong. Okay, go back. I'm not finished with college now. I owe a lot of gratitude to this gentleman. And I was telling Steve yesterday. I remember that corridor, huge corridor. 6th floor. What it is to see in 616, I think my dad is in 614. And we'll bounce on each other very often. We discuss chemistry, we discuss a lot of things. And it's amazing. And for the progress of life, much easier. So thanks for it. So, now let me summarize a few things about he's still here? Yes. Reasoning the electronic information content in a molecule and its chemical reactivity, which pK shows the potential. That's what I say. So we move on. Yeah. So, when I left college now, I came to Uppsala and the group, and then I see all the products from that group, and it's so pleasing to see them growing. They're going rather fast, turning the pages of new directions, and whether you start crossing. Where's my last PhD? No. Where's my last PhD? You were my last PhD, were you?
Chin.
Chin. You heard Chin. But Swanson was before that. Swanson was not spectroscopy physical telescope. You saw that Swanson's work is a good thing. Now, here is the group 1, group 2 catalysis. I'll tell you why I'm showing you this slide. Is about, can you show me, give me a slide? Okay, good. This exon 1, exon 2 excised out at that position, branch RNA is formed. There, the lariat is formed. You see how the editing taking place in the RNA. The exon 1, exon 2 with the help of magnesium are put together in the second step and give you processed RNA, exon 1, exon 2. But that loop formation is absolutely mandatory for that to ligate. And that was a big curiosity for me, and I came to do this work when I was sitting having my dinner by the side of Professor Phil Shaw, who was a Nobel Prize and group to RNA hypothesis. And he said, Tony, do you see that? What do you think about this? No idea. So one challenge that came up to us is how to make this guy. Next guy.
It's in your hand.
Oh, it's in my hand. Okay, so this is the summary of that thing. The E1, E2 introns intervening sequence, and that is the branching site, and that's the thing going on together, the ligation event, and that's how it is processed. Wrong ligations, serious problem. Your health and disease. You see, our biochemistry, the biochemistry of RNA is so unique. That tells you a simple thing. That tells you how often that thing is cleaved to give you this and back to that. Equilibrium constant, 1. 10⁶, or maybe woof, goes back there. How the integrity of the genome is maintained. That's a simple equilibrium. Second, solid biochemical work. So that thing is important. That is the cleavage reaction, and that cleavage took place, as you saw there, a hydroxyl attack, a cyclic phosphate. So the natural question was, when the group 1, group 2 then which situation cyclic phosphates form the intramolecular neighboring group effect, and the other one would be intermolecular, where concepts were one thing concept, we do a transition. So we go. Chemists invent, reinvent, create their own problems. We are chemists. Also see the tip of the iceberg, we always like to go down what is under the iceberg. And in the process you have to do the reinvention, creation, and we always do that. And because I wanted to make that variant, the answer to Phil Shaw's question, so I spent some time with my colleagues. So look what is happening here. So I made a simple dinucleotide with this guy. Patak, we published in Actec and Scan, that if you want to put a second phosphate here, the first is here, the second here, so you have to put a protecting group. So we put the pixar, it's a simple about protecting group. And the moment you protected that, it broke down in several fragments. So that traditional strategy doesn't work for the branched nucleotide. The branching of the ribonucleotide is the very essential stepping stone for the RNA fidelity control. So again, trying to remind you what's happening in exons 1, exon 2, and this 2' hydroxyl is attacking the other side here, and to give you the processing process message. So this is the chemical part, that is the process. Here's the 3' 5' phosphate, and here's the 2' 5' tail, and the cycle is complete. That's a minimal description of a lariat RNA, and it was dancing in front of me and put the dance in front of my students. See if you can make it. So that first thing did not work. We could not put the branching. So we went ahead and tried to do the others. At the end we did it. We summarized that in one slide. At the end we did it. And how we did it, it's a long story, but maybe we will not go into that. But that we made barriers of different sizes. Lo and behold, what happens? When it comes and forms a lariat RNA of certain size, it undergoes the neighboring group attack of the bicycle by the bicycle hydroxyl. To give you the first step, the next question, Swanson will ask me, what is the conformation of the cleaving junction? Where are you, Swanson?
Here.
Oh. So, Swanson has done a fantastic job here. And so that was the question, and we did a lot of NMR with it, and to show, hey, look, this is a south type, that is 3' endo, 2' exo, 2' exo, 3' endo conformation here, the south of the guanine, and that is the departing group. So I go to the next one. I won't discuss the detailed chemistry because that will take a lot of time. And it's all documented in the literature. If you want references, that's all available in the Google Scholar, ResearchGate. You'll find my whole story, except my date of birth. So I will discuss that. So just a short one. We create here a branching point. You see here in the vicinal phosphate is created. And that's the one we wanted. Then we do the cyclizations. Then releasing the tail. Okay, and then it undergoes selectivity. We'll go, this is the final one. The same story. So, here I answer the question with my colleagues. I think the guy who took this NMR was Peter Robert. He did his PhD then. Oh, when you sponsor.
Just after.
Yeah? After you, yeah. He said, hey Jody, we know how it is cleaved here. That a cyclic phosphate is formed. And here it is at 21 ppm downfield. Cyclic phosphate. Wow. We've answered the big question of self-catalysis of our life. Everybody without hand waving here, including Tom Chair. Yeah, Tom, he doesn't have any clue, except showing me a page, hey, class 1 is formed. But here comes when synthetic chemists gets married to spectroscopy, that's what happens. He's both important. Here's the bullseye, and here's the cyclic phosphate. So, there you go. We did a whole lot of modeling work. We did the whole 500 600 we got all the visible coupling constants out. We got fluorine phosphorus coupling out, coupling constant out, carbon 14 phosphorus coupling constant out. Use all these coupling constants as constraints to understand what the geometry of the cleavage site is. And that's the geometry of the cleavage site. You see here, this is the 2' endo sugar, 3.8 angstrom here. At the moment you go from alpha plus to alpha plus, okay, but zeta plus to zeta trans, just make a rotation of 90 degrees, it comes from 3.8 angstrom to 2.8 angstrom. Lo and behold, axial group departs, thanks to Westheimer. Trigonal bipyramidal phosphorylate here. We finally produce the ab initio optimizations. story. That is more interesting because here the paradigm shift has taken place. What is paradigm shift? I will go into that. The first paper is with Leo Cook, and I don't see him here. I will try to find out about him. The thing is this here. If you take all the coupling constants to hand and do a proper pseudo-rotational analysis, and you do a Van Hoff plot, simple north versus south, equilibrium of the function as a reciprocal of temperature of your function, you get linear line. What does it tell you? It tells you that pseudo-rotational wheel, which was the central piece of north-south population as just a crystallized out. So they're the ones crystallized out. So there must be the two component equilibrium, north-south equilibrium. But we show that this equilibrium is interconvertible from north to south, south to north. And simple temperature dependent studies show that we derive all thermodynamics of it, and that has been the world. The honest thing, when people figure there, when you have a crystal figure there, you have a key figure there, you put that in your cool figure there. And you must take at least 10 years of continuous work to understand these interconvertibility of the pseudo-rotational cycle, that the energy barrier from one to the other, north to south. We found out this energy barrier is too small. Therefore, it interconverge. In the hexaparallels, this is not possible because the energy barrier is too high. And these low energy barriers of the transition state potential is the key of flexibility of DNA, RNA, because it can react to the environmental changes. It can react to the environmental changes. It put Manala, B goes to CDNA, to salt here. That was already on full of work. But that again, that was not really master. He taught us quite a few things. So, having seen that low energy barrier, obviously dawned upon us, we must understand this better. And that equilibrium is 14, there are cases which come to 17 to 14 kilojoule, but mostly there are even below. I won't go into the details, but it's again available. That is the first paper where you say Canadian chemistry, but it is not that high. It is more like 2.5 and 5. And how do we know that? Well, we know that by doing this. Make different molecules. This is what it is. You ask a deep question about why DNA, why RNA is fed to Forerunners. Why not hexaparallels? The sugar selection in the nature has made you and me what we are. The sugar selection. And sugar selection, that means you need a sugar that's flexible. It can go from one to the other. It can bind to proteins. Induce fit, somebody said today. Those are the criteria that makes our pentose sugar in the DNA and RNA so unique. So, as you see here, we make a lot of compounds right from the dideoxy to the phosphate. If you go from that called food side. Oh. What is the story?
One last page.
Yeah, yeah. Thank you, you see. Thank you. So, From that dideoxy sugar, then of course we had abasic sugar to understand the role of purines. We had different substituents of the sugar. All these things, and we did a detailed thermodynamic analysis, and there is a monograph that's circulating in the literature, is that stereoelectronic effects in nucleoside, nucleotides, and the structural implications. You can download it free of cost, and you will see some of the efforts that we have made to understand what makes pentose so mobile. Today we're doing all kind of chemistry. I thought it's a challenge for us to understand the reason, the stereoelectronic reasons of pentose flexibility. All right.
Go ahead.
Okay, so I'll give you the summary. Anomalic effect, Gauss effect, interplay. And then that our work has shown that Gauss effect is stronger. I'll explain to you in a second what is Gauss effect, what's the anomalic effect. Gauss effect is always stronger than the anomalic effect. That brought us directly to the single-strand RNA pre organizations. We heard the nearest neighbor effect from Naoki. It's a double strand. But that intrinsic quality of what a double strand is, I will reveal very shortly. Talk about conformational cooperativity, we talk about transmission of that glycol to the sugar to the phosphate. It's like this. It's like this. You have a switch here somewhere. You press that, and the lights are on far away. And that transmission we're talking about, I'll give you some examples of that. So again, I won't go into this molecular orbitals, but summary is this. That's the anomalic effect stabilizations here, and that is the Gauss effect stabilization here. One gives the north type sugar, the other gives the south type sugar, and these are the Newman projections, and that we have put our heads together and make sure that's correct. So they're all in the literature, and they stand as a foundation for understanding our pentose transformations through information transfer. Remember, this is here information transfer. So if you have got something here, and how that information is transferred to here the phosphates here, at the 3' phosphate. That is the key. When a ligand binds, when the base is methylated, then sugar changes, phosphate changes, backbone changes. That is the name here. So I go back. So we do this, the Gauss effect, which is stronger than the anomalic effect. I'll come to answer some fundamental question on that. Now, if we took simple molecules, again, the models are so essential to understanding physical processes, polymeric molecules. So here we start with a simple, model. 5' phosphate, 3' phosphate. We have a sugar with 2' hydroxy. We have a base that is substituted that with different bases. And then we ask a simple question. I change the nature of this base, how the conformation of the sugar changes, and how that conformation is transmitted on the phosphate level. Look here, it's the ethyl phosphate. It's a dinucleotide mimic. Because it has got all the torsions necessary for dinucleotide. You know, that tells you. The more I do this.
Time flies.
Time flies. So I'll get there. Bear with me. Yeah. So there you see here, and now, I think it's a different work or Forerunners work. Well, they did it because literally 3 times before I take them out in my slide. Tell you. And some of them get pissed off with me. Don't you trust me? Some PhD student asked me that question. I put up with that question and said, no, I don't trust you. But does science trust you? That's more profound than anything else. So, if you see here, I changed the pH and I look at the chemical sheet. And the inflection point is a pK. And that I did with HHG, HHA, H2A. When I say I did, forgive me, this is your slide. I know that now. And that tells you about the pK. Now the question is simple. I go to the next slide. So here I'm looking at the free energy of conversion of that guy, sugar, into one state to the other. So I do a simple thing. I look at the north-south ratio here as a function of PD, and the inflection point, the pKa of the nuclear base is showed up with the delta G of north-south equilibrium. What is telling you? It's telling you that information, that correlation equilibrium at the nuclear base is transmitted to the sugar. Now we go to step 3. Here. So now we look at the epsilon plus and epsilon minus ratio and the free energy of that. Look what is happening here as a function of pH change. The inflection point gives you the pKa that you get directly from the nuclear base. You know, this is a transmission. We're talking about transmission of information. So there are various Gauss effects, and I will give you a bottom line of that. The 3' Gauss effect gives you the 3' endo conformation, 2' endo conformation, and 2' Gauss effect gives you that conformation. That understanding has been, I thought of late DNA, and DNA to be a molecular life. So that boundary between DNA and RNA disappears with chemistry. Nature has done a rigid transformation to So, we'll show you that understanding of the Gauss effect, which is stronger than the anomalic effect, come to the implication of that Gauss. Third thing. Yes, sorry. So that Gauss effect, that Gauss effect, 2' Gauss effect is this one. How it wants to be Gauss, that guy, that substituent wants to be anti-periplanar with this lone pair here. That's the Gauss effect we're talking about. And the 2' Gauss effect is through that. That also you will learn from Schwarz's work, how he produces substituents here in order to do the Gaussian engineering here. And I'll show it to you that this Gaussian engineering is the one that's important because that takes away that partition between DNA and RNA. Here, when you put the fluorine down in this, then this wants to be Gaussian with that, and that is what anti-periplanar. And as a result, what happens? You have 2' fluoroRNA which behaves like a ribo. 3' endo, 2' endo. But you do the contrary, invert the configuration. Invert the configuration here. This is the ribo configuration, this is the arabino configuration. But still the fluorine wants to be Gauss with this oxygen, but it also wants to be periplanar, anti-periplanar. So as a result, sorry, what? Can you quickly done this?
Eh?
No, okay.
You want to go back to to the.
That one we have done.
Yeah, I know. You want to hear?
Yeah, that's the one.
Yeah.
That's
Huh? Let me control it. So
Yeah.
I can go faster.
So you say, you hear that? He was faster than me. And I'm not contesting that. There are many students who are running faster than I do, and I'm proud of that. Nothing can be more pleasing than when you see the student is more responsibly from there to the finger. That's transmission of information. How fast can it go? So if you see that guy on the right circle will be south confirmation C2 prime end of yeah.
Not on the arrow.
Okay. That guy, the C2 prime end, that's a distinctive feature of the DNA show. And this is a distinctive feature. Well, look, I'm not touching
That's
it. Yeah, what is it? But that's on the left, you see, there's a long sugar, there's a RNA sugar. Now, that dual character, first it was to be lost, second it is only possible with anti-variable. So, by inverting the configuration of the four, you have achieved that. And there are many examples of. Dama has done a fantastic job on that. Not only Dama, Mono has done a very good job on that. IC has done a good job on that. Just this thing, just the Gauss effect engineering. Next one.
Next slide.
So, the other implication of this is the DNA strand to behave like an RNA. As for binding, RNA is recruitment, the DNA nucleus, RNA nucleus will not recruit the RNase properly, but RNA will do. Cellular nucleus stability, engineering messenger RNA vaccine stability. These all have implications, and the implication is not only that, but the mother of all these things is understanding the Gauss effect and the Nucleic effect, and the energetics thereof.
Sorry, you are revealing the secrets now. So because that's how we make a better introduction.
Of course.
So you tell everybody.
Good. You know, this is the beautiful thing about science. Nothing is a secret. Once it's published, it's published. You talk, you communicate, you converse. This is science. And that spirit we live. But I'm sure
that's how we make the RNA therapy last longer. Is through the Gaussian effect. Okay, so go ahead.
One minute, that's all. So that came, I think this is perhaps at this point, it's important to say, how many papers we published together? 35, 36 papers? About 30 papers we published together on that. Deciphering the crystallography is great, but you're doing what crystal is done. But when you play them out, you see the dynamics. So this is the point. Where are we?
Waters, Joseph.
Sorry?
Water.
Of course, water. And your DNA is in water. It's not in like our. Okay. So what you see is a PED dependent north-south equilibrium. Again, it's the same work I showed in a different way, but I won't go into details of that. This is northeast, the phosphate and the sugar conformation on the top, phosphate and sugar conformation on the top, and how they are cooperating with the free energy and the function of phosphorus on chemical shift, and so on and so forth. I won't dwell upon these things very much longer. Okay, now we'll show you, take it to something else. This is the carbon work. Carbon work that showed modulation cleavage of target messenger RNA with CARB RNA. So you see that we have blocked it by free radical chemistry. We are the first one to get a patent on it. And a couple of Jack's paper on it. And as a result of that, we have got here an RNA skyrocketing here. And I would, in the next slide, try to show you that if you place that properly into oligonucleotide, here, if you place that properly in the oligonucleotide, this is the deoxy, and that's the R ribo. So on DNA RNA, what you place this underscore C is the CARB RNA. And then you can control where the cleavage site is going to be. So if you can smartly place that, CARB RNA, and then CARB RNA here, in a DNA strand, RNA, you have one site of cleavage, and the rate of the cleavage is several times higher than when it's cleaved all over the place, because RNAs have to work on these things in indiscriminate fashion. But here it can do the discrimination, and it's a single site cleavage. And as a result, you see the single site cleavage here compared to that guy here on the left, and this is the right one. Now this is a simple way we say, in this work, if you put things in the correct way, then we can get the RNA cleavage at a much more enhanced way. Lo and behold, that is what we do. And the same story basically with the higher oligonucleotides. Now, if you want to cleave in two places, you can do that by putting things, by choosing where you put it, where you are going to put the CARB RNA. Here is no cleavage at all, because you see, I have made the DNA to behave like an RNA, because RNA does not cleave it anymore. Look here, no cleavage here. And then no cleavage of RNA strand in heteronucleus here. So it is possible to engineer the enzyme specificity in a specific manner by altering by choosing the modifications as well as the site of modifications. Okay, I will go into that. It's basically more detailed work and that. And now, a single-stranded adenine-rich DNA and RNA retains structural characteristics of the respective DNA. That's for you. Now, because he did the work, he put it so nicely about the double-stranded work. Very interesting. And I am trying to show here this nearest neighbor particle blocks of RNA in single strand RNA and DNA, because cosmic evolution of PK. So what you showed is just superb. But before I started this work, but when I realized this is what it is, yeah. Now let's see if it is also possible to single strand. And so that's the idea. So this NMR told us when you look at the aromatic proton here and the aromatic proton here, that network tells us what is DNA like, the C2' endo conformation, and to do the same story, you go through the crosswalking and you find what is the RNA-like conformation. Okay, we know that. Having known that, we do a simple thing. We do a detailed NMR study, of course. We use the medical strain, of course, and then we do simulated analytic experiments. And the result, I will show it to you. I will discuss these things, but I can talk about it. Is this single-strand DNA and RNA are stacked. No key. They're stacked. You don't need a double strand to stack the nucleic acids. I will then finally come to what's the base pairing paper. We measured it, 657 words. And that shows it is stacked. Is a right-handed helix. Exactly like a double strand. Single strand, okay? The paper is biochemistry paper. It's been reviewed by 7 reviewers. They didn't believe us. We showed the origins of and they took it. Okay, now we go to the next one. Okay, so this is, we do the dynamics, but look at me. As I age, I cannot fix this problem of rotation anymore. Previously, my co-workers used to fix it. Now I cannot fix it anymore. Forgive me, forgive me. But we take what is happening. Okay, I'm there on the top. Yeah. So we overlay, we do the detailed molecular dynamics, we take samples from different trajectories, and we overlay, and this is the overlay single strand DNA, single strand RNA, and just single strand, and it's all due to the stacking, because we go through these stacking parameters here, all go to the stacking. You see the nature of features of the purines and pyrimidines and the electronic properties. Pyrimidines become the 2 nitrogens in the system and anti-profile. The aromaticity of purines and pyrimidines. The 2 nitrogens in the system is deactivating purine out electron from the pyrimidine. And purine is more complex because it is all electron rich part and a pyrimidine electron deficient part. Together. And when you have the stacking, you stack the electron rich part, the electron deficient part, and so on. And you get a helix that way. That is what we are doing. And therefore it's taken 8 reference, but 9 reference, that's okay. They took it finally. And that's what happens, okay? And that gives you the helicity. So the helicity doesn't come from the hydrogen bond property. Helicity comes from the okay, we go further. These are all documented. So this is the final bottom line. Single-stranded RNA, however, lacks such three-dimensional character. Therefore, only specific interactions through RNA bases can determine its specificity. Given the limited number of variants on the 4 different nucleotides, specificity would require long RNA segments of specific sequence with relatively weak protein interactions at each single nucleotide within such a sequence in order to avoid non-specific binding. That came out from current opinion to structural values. That's what they say. That's what the peers say. When I say no. Here is the story. In contrast, our NMR data shows that the origin of the helicity is in fact in the single strand arising from the electrostatic forces stacking. Double strand merely strengthens these by hydrogen bonding because it's like pre-tuned by stacking and then hydrogen bonding comes and locks it. That's biochemistry. Now, to provide another line of evidence here, to cross-couple the base in single strand. The sequence context-specific genetic code. I go that far. Oh, they're all Jack's papers that I thought before coming up with a new concept, the best thing is that you let the community see, you can say, you butcher me every day, every morning, and that's the best way to learn. The negative reviewers come and always stepping stone to better work. So, I just have that's my philosophy. I just take a little drink here because so the crosstalk. This crosstalk among the same strand. So this is an experiment done by Sandhita, Parak's wife, and I should not identify Sandhita as Parak's wife. Sandhita is my student. Identifying that as your wife, I just put it down. No doubt. Good. So, it does work. Before I go to that, I show you something else. And that's also Forerunners work. I show you something else. I go. Oh shit! I just missed that slide. Then help me.
You want to move it? Yeah, they already don't move. Okay. You see, already back to the first slide.
I'm frozen.
Yeah, you see, it's already back to the first slide. See, don't touch anything.
No.
Okay, no, it's okay.
Go on.
I know. No. You want to talk about the.
Further down. Move. 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 Move.
Yeah.
Move. Move.
Further, okay? It's go? But Georgie, you need to speed up a little bit. It's already 6. Puck. Yeah. And also the restriction part. Yeah. Here. Just a second. Yeah, I know. It's frozen. It's frozen. Because this one is too big. What?
Was it a video file? Yeah. Check off your that. It's very English. Go for this.
It's not.
That's the one. That's the one. 71.
This one.
Yeah. You see, this is the first. It's
too big.
Easy. Put this on my table. Hey, Johnny, look here. We do the titration in 2 different pH. So you can see for 2 different pH, and this is the acidic pH, which is normal. You look at the APU, which has got a correlation sign. You get the pKr. No surprise. And you do the same thing now with the H. That's the H8, and then you do that with H5, H6 up pyrimidine, the same dinucleotide. You get the pKa there also. So you get the pKa both to the purine as well as pyrimidine in acidic pH, because that guy gets pyrimidine, and that information is transferred to neighboring nucleotide, pyrimidine. Okay? I saw that, but I didn't understand it. I told you, good students always will teach you something new. So I kept that thing for 3 months on my table without doing a thing. And suddenly someone comes, Johnny, what happened to that? I said, I don't know. And when I understood that, I see something very brilliant there. Because look here, now changing the pH to alkaline pH here. And I see the pK of uracil, but I go to the adenine. I see the pK there also. What it tells you, this ionization, deionization of equilibrium information, the free energy of it, is transmitting also the nearest neighbor. Now this is very essential to understand the communication between 2 bases. And then I will build up the story with large oligo to show this transmission of through electrostatics also applies to larger molecules. Let's have a look.
This is the last one.
No, go up. Up. Yeah, that one, go up one still. Okay, okay. This is a good summary slide because everybody is doing commentary and doing the other one. Yeah, and I want to. Okay, fine, we'll come to that. Now, if you see that one, we designed oligonucleotides. We designed oligonucleotides with G in the center. With G in the center, and we had bases. Here is the dinucleotide, trinucleotide, 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 with different substitution of bases. And we deprotonated guanine. And what do we see? We read that deprotonation equilibrium on the neighboring bases. Look at that couple. Those two are coupled. You see? And we go further. Then we go forward.
No. You're going back?
Yeah, going forward.
Going forward or back?
Yeah, go to that. Stop it.
Yeah.
Go further up.
Huh?
Further up.
Further one up?
Yeah. Okay, these are the titration curves, but I won't show you the titration curves, but I will just give you the summary of this titration curve. This is simple 1 year and a half. Nothing more tricky than that. We are not talking about rosy combinations which have done for the hydration stuff. I will not talk about that. But we'll talk about this guy. So we have got single strand RNA, and we went up to from dinucleotide, di, tri, tetra, penta, heptanucleotide. And we have only one ionization site here in the alkaline pH, which is guanine in yellow. And you see the transmission of that information, the free energy of it, protonation, deprotonation equilibrium is transmitted all across the HHG, HHA, H2A. Now, this is serious. This is serious that your dearest neighbor is looking at you. Who is the next? Now, how much information I can get because of this ionization, deionization, and the ligand binding? Those informations are complete. So people who think by doing a single modification they have mutated a site, they have to rethink the whole concept. Now, okay, I will show that. I will show this. I will not show. So, basically, if you have a oligonucleotide C5, A5 with U3, 3 nucleotides this way, 3 nucleotides this way, and if you go in one ionization site at the alkaline pH, of course there is a modulation of that, the pKa's, but what it means is this. Propagation of electrostatic interaction. I want you to see that at the 3' end to the 5' end. So there is a deionization site at the alkaline pH, and this is propagated at both ends. Okay? So it's a perturbed pKa and so on. This is the concept solved in the literature. Now, here is the bottom line of that. What it means is this. If you have one nucleotide there, Q2, and you have a nucleotide there, by binding or by ionizing this nucleotide, you influence the neighboring nucleotides. And as a result, the pseudoaromatic character of all these neighboring nucleotides we have done up to heptamers changes, variable pseudoaromatic character, pKa. And as a result, the information content changes. So this will not discuss this. This is again a little extension, and I think I'm done.
Yeah. Let me check it. Do you have a last page, whatever?
Sorry, what?
This is the last page, so anyway.
Oh, this is your
Yeah, I
question.
know. Yeah.
Yeah.
So,
Thank you for your attention.
you're okay. And thank Jody, always. So he forgot he's hungry, so we can talk about science. Let's welcome Yanis to make closing remarks. Please, come on, yeah.
Thank you. Thank you. Stay here. Stay here? Please, London. You can sit down. You are not getting the first thanks. Peter, thank you very much. Everything ran smoothly. We owe you a lot. There was lots of computer trouble. Thanks a lot. Marco, thank you for keeping time. Anna Maria has left, but we all have a lot. You will meet her tomorrow, so we'll thank her. All presenters, fantastic. It was an enjoyable day. It was a little bit long because last chair was a little bit funny guy. He's really my good friend, so I have to allow that. So I hope you enjoyed as much as I did. We are off for a nice dinner, hopefully. You can walk over. I'll walk for length of taste. You'll see there, once you're there, you get a special present from us, which is very simple. It's a book of abstract, but everything present signed it. So you can enjoy sitting down, having your glass with whatever you like most. Presenter sign here. Of course, your signature is missing. Enjoy.
All of you to come all the way, and I hope all of us have made your day by giving you some new science. That's what we look for, the new science that will give our civilization to the next stage. Unless we destroy it. By nuclear threats that are all around us. If we don't, let it go on another million. What we see today is about 70 years old.
Let's have this sort of discussion over there.
Yes, I will.
With something in your hand.
Yeah, so basically that's what it's all about. How do we make the world peaceful? That's the only way. This will work.
Is it?